guys hear me? Welcome to the 2022 PyTorch Conference. I'm your host, Christian Keller. I'm the product lead for PyTorch at Meta. I'm so glad to see all of you here today, whether you're in New Orleans with us or joining us from around the globe. I'll first start with a few items for logistics. Please join the conversation following the hashtag PyTorch Conference. You can find today's agenda and speaker bios on the QR codes you can see around the rooms here or upstairs. There's also complimentary headshots that are being offered today on a first-come, first-served basis. They'll be at the mezzanine starting this afternoon after lunch. If you need anything, you can find someone with a long-sleeve red shirt, Team PyTorch or Meta, and they can help you. And finally, if you're looking for Wi-Fi, it's written on some of the screens up there, but it's the Team PyTorch Wi-Fi, and the password is PTC, all caps, 2022, exclamation point. So we have a full agenda. To kick us the event today and talk about the newly created PyTorch Foundation, we have here with us VP of Engineering at Meta and PyTorch Foundation member, Aparna Ramani. Please welcome her for me. Thank you.
Hey everyone, welcome to PyTorch Conference 2022 in the beautiful city of New Orleans. My name is Aparna. I support AI infra at Meta. I'm also the head of the board of governance for the PyTorch Foundation. And today I thought I'd share some of my thoughts around why we decided to go with the foundation, why it's good for Meta, why it's good for the community, and just where I think we're going to steer the foundation going forward. I'm really excited. This is my first PyTorch conference, and we have such a cool lineup here today. So looking forward to seeing what's up next. So PyTorch started about 6 years ago with a very small but focused mission around powering researchers. But slowly and steadily, the impact and the scope of PyTorch has grown, where today it is one of the leading AI frameworks. And the use cases really are super diverse, everywhere from self-driving cars to genetic research, all the way to human space exploration. I stole some slides from the talk that Geeta and Joe are going to give today later called The Great State of PyTorch, just to exemplify my point in terms of the growth of PyTorch. This chart here shows the adoption by the research community for PyTorch, where we have 63% of AI research papers are implemented in PyTorch. And this is growth that's happened in the last 5 years. And what's really interesting is that even though the market share for PyTorch is pretty huge, we still see growth year over year of about 4%. Let's look at the GitHub stats. And this is a really cool chart. We've seen PyTorch grow substantially this past year, with a 45% increase in GitHub repos that are using PyTorch. And with any cool technology that's sort of transforming the way that people do work, you will see jobs being created, new skills being developed. And so these are stats from LinkedIn, where you see about 44,000 professionals list PyTorch as a skill. We have about over 2,000 jobs that are listed for specifically PyTorch. And this number, the number of PyTorch professionals, is also growing about 50% year over year. We use PyTorch at Meta for everything, from VR to Instagram filters for a whole variety of use cases. And we do it at unprecedented scale. We're talking about trillions of inference operations on a daily basis across, for the billions of users who use our products. And even if you just look at the on-device stats, we're talking about a 70 billion on-device inference operations on a daily basis. But this is not just about Meta. PyTorch has grown in scope and impact, and so many people across the industry are contributing to PyTorch. And so the virtual team size of PyTorch has gotten really much, much bigger. And so we at Meta wanted to create a governance model that matched the scope, the ambition, the contributions from all of the stakeholders in our community. And we really believe that in order for PyTorch to continue to go strong, that we need a governance model that sort of matches that ambition across the industry. And so we created the PyTorch Foundation earlier this year. And we think that by moving it to a foundation, it gives opportunities for other stakeholders to contribute more, to invest more, and that helps PyTorch become really healthy, which is then good for everybody, and everybody benefits. So we host PyTorch Foundation under the Linux Foundation umbrella, and we started it with 5 founding members, AMD, NVIDIA, Google, Amazon, and Microsoft, along with Meta. And for those of you wondering how the foundation works, let me give you a really quick overview. Well, what we don't do is technical governance, and it was a really explicit principle right from the beginning that we separate the technical governance from the business governance. And so even if I really love Haskell and I want to rewrite PyTorch and Haskell as the head of the board, I'm not going to be able to do it. I can make a recommendation to the maintainers of the project, but really it's up to the maintainers to make that decision. So we don't do technical governance at all, but we are allowed to provide recommendations. What we do is we oversee what's called business governance. And what this typically means is we protect the PyTorch brand. We run conferences like this and other such social events so we can help grow the community for PyTorch. We are thinking about things like training and certifications that can be official so we can help bring more people on board on PyTorch. And when the board has surplus budget, we can also use it to promote PyTorch development through grants and other such initiatives. We're just getting started. We're taking baby steps right now to become a foundational entity. And I'm full confidence that we will make substantial progress over the years in enabling a really solid foundation going forward. There is a talk later today by Ibrahim, who is part of the Linux Foundation, who's going to talk about more how the foundation's working and the details there. So please feel free to catch that talk. OK, so now for a less serious talk. This is the 5th PyTorch conference since the birth of PyTorch. And it's really a great time for everybody to put names to faces, or should I say faces to GitHub handles. It's great to get the community here together. We have some very exciting announcements here today. We have companies like IBM and Walmart and Adobe talking about how they use PyTorch internally. We have new launches in production by various of our partners. And we also have contributions from various fields, medical research, healthcare, which brings me to my final point. I want to step back for a second and reflect on the larger picture. This is a photo of the Mars rover. And today we have a talk by Dr. Chris Mackman from NASA, who's going to talk about how we're using PyTorch in NASA for various experiments, including the Mars mission. And we work really hard every day on PyTorch in the community. I know people here are focused on benchmarking and making sure we have the best technology out there all the time. And sometimes it's easy to maybe forget the impact that we're having. AI is rapidly impacting the way the world works, right? And in an amazing way. We see innovations coming out every single day. It is slowly percolating every industry. And so many of the problems that we see today, we look to AI as at least part of the solution. And many of us here at the conference have been contributing to PyTorch. And PyTorch is such a central piece of this technology stack for the next generation, for the future. And we've been contributing in many ways, maybe in some ways contributing to the core. Some of us contribute to libraries and packages. Some are focused on training and teaching and helping grow the community or enabling new hardware types. So I just want to say that every one of you here is impacting this transformative change that we're seeing in the world around us. And I want to just end by saying thank you very much for everything that you're doing. With that, I will hand over to Soumith Chintala, founder of PyTorch.
right, can you all hear me? Yes. Okay, we have a lot going on today. Oh, it's over here. Okay, so I have a lot of talking to do, but I do want to say that none of my slides are written by GPT or generative model yet. Like my slides today are still written by a human, but I don't know about next year. The field is progressing so rapidly. So let's get started. So I want to talk a little bit about the PyTorch roadmap, where we're going. So we have the 1.13.1 patch release landing on December 15th. I think the RC goes out next week. And then I want to talk about 1.14 that we've been working on. One of the key things that has been top of mind for us for a couple of years now is performance. And the reason it has been top of mind for us a lot is because GPUs are getting faster and faster, and they're getting faster in a way that we are not able to keep up with eager mode. So like the compute flops on GPUs are getting much faster, and the memory bandwidth is not getting as much faster. And there's like, with PyTorch, with eager mode, despite all of our best efforts in moving a bunch of overhead to C++ and reducing it, we're still not where we want to be. And that's been top of mind for us for a while, and we've been working on various projects to try to get to a better place. And as a consequence of thinking about performance over the last few years, we moved a lot of PyTorch from Python into C++, where PyTorch is basically a C++ code base. And that's like, I hate contributing to the C++ parts because you have to set up your build system and all of that. And at some point, we also, apart from realizing performance, we want to like bring back PyTorch or parts of PyTorch into Python itself. So we set ourselves a plan of, hey, how do we get to 30% faster PyTorch with no change to your model, like unlike TorchScript and stuff? And how do you make it easier to write PyTorch backends? Right now, PyTorch has like 2,000 plus operators. And then how do you get to state-of-the-art distributed? We are doing a pretty good job, but like distributed is one of the most growing areas in AI. How do you scale up to larger models and stuff? And lastly, how do you bring PyTorch, or like most parts of PyTorch, back into Python? Well, this is what we set ourselves as a goal, and we were trying to think about how to actually execute on them. And so the route, like even going into more granular, like what we set ourselves as, how do you measure that 30%? Because I can say, we got 30%, and you can believe me or not believe me, right? So like, we set ourselves more granular benchmarks. Hugging Face transformers, like some of the top models in there, another 61 models from Tim, which is state-of-the-art vision models, and Torchbench, which we curated ourselves by taking papers with code and taking all the top tasks in papers with code. So you get a diversity of tasks, what kind of tasks are done within like the ML space. And then for each task, we take like the top PyTorch implemented GitHub repo and make it into a small wrapped benchmark without ever touching the code itself. So we thought this was a good proxy for measuring ourselves and whether we're actually getting 30% speed ups or not. And we want to support dynamic shapes, and that's something that is generally hard to do for a deep learning compiler, but we're like, that's non-negotiable. Our users use dynamic shapes all the time, and by dynamic shapes, I mean you can change the shape of the input you're passing into your model without having it recompile. And lastly, distributed, we want all of this to just work, like it has to be 30% in the distributed setting. And obviously, it has to be robustness to correctness and accuracy. So we've been thinking about this a lot, and we're like, okay, cool. So what's the problem? Okay, let's get started. Now, one of the things I want to break the problem down into is we know how to solve this, and this slide is actually from 5 years ago. Adam Pashka and I made this slide 5 years ago where we were like, oh, we know how to make PyTorch faster, build a compiler and do kernel fusion and out-of-order execution and stuff like that. And what I mean is just like a small, like you wrap your model in a torch.compile or something like that, and then you get a faster model. Now, the challenge has been building such a thing without compromising flexibility. And I think that's like the, that's like you don't want PyTorch to get crappier in order to get performance. You just want to get performance while keeping PyTorch like the same. So now, like, how do we think about these problems? First, let me break it down. So you have some piece of code. I call the first stage of building a compiler graph acquisition. How, can you actually like acquire that piece of Python code that you wrote reliably into our own graph format? And then the second stage called graph lowering, where you break that graph down into more fundamental, smaller pieces. And then the last one I call graph compilation, which is you actually then map it onto your big GPU or XPU cluster. So within this setting, you could, like let's talk about the first one, graph acquisition. How do you capture PyTorch graphs written in Python with dynamic shapes and stuff without compromising user experience? And that's a big challenge. And actually, like, we spent 5 years working on it. And like if you see, like, we actually built like 3 or 4 projects working on it, like torch JIT trace. It was just silently wrong if the if you invalidated the trace assumptions. JIT script, where you actually had to modify the code so much that people were like, it takes me 2 months to modify my code to be compatible with torch script. FX tracer, I think we never fully released it publicly. Lazy Tensor and Dynamo is something, 2 projects we were working on in the last year to try to do new approaches. Lazy Tensor and Dynamo did similar things, but Dynamo was a better technical approach, so I'll just focus on that for this talk. So they work, Dynamo works out of the box as is, but to the compiler, it gives partial graphs. So what do I mean? You take a piece of code, Dynamo identifies blocks that can be compiled and cannot be compiled. And then it passes the blocks that can be compiled to the backend compiler, and the pieces that it cannot be compiled, it just like runs with regular eager mode. And the way it does it is pretty cool, like nerding out a bit over here. It actually like hooks into Python, into the frame evaluation API, which was introduced in Python 3.7. And it actually reads the bytecode and identifies traces of bytecode that it actually can compile. And then it just patches that, the original code to shortcut to our compiled version if our guard assumptions are true. And Peng and Jason Ansel will talk about it later today in more depth. I just couldn't help myself giving a bit more of the detail. I think it's pretty cool. So we've been validating it, and we actually scraped like a bunch of GitHub projects, and then we ran Dynamo with them, and these are PyTorch projects. And Dynamo just works like 99% of the time on acquiring the graph correctly across like these 7,000 plus projects we scrape. And as of today, it supports 3.8, 3.9, and 3.10 of Python, and 3.11 support will come soon. So with Dynamo, we actually felt like we finally found a very reliable solution that reflects the flexibility of PyTorch and acquires the graph without having the user go through too much pain. We've been quite happy about building this, and that's something that I'll talk about more about how we try to push it into the release. And you can ask, oh, what about the gradients? Okay, like get the graph, like how do you like backprop it? And so what we did was we kind of used our Torch AutoGrad engine in like a clever way. I wouldn't call it hacky, but like definitely very, very clever, where we overloaded it. We just like we look at what is happening if you run the graph in eager mode, and then we kind of just acquire it, and then we lift it back. Is in an ahead of time mode, and we call this ahead of time autograd or AOT autograd. So the graph acquisition and backwards, that's all settled. And then coming to backend, right? So the writing, like PyTorch has 2,000 plus operators today, and it looks something like this. It's like they're legit, but half of them are overloads, and like honestly, it's like 1,200 plus operators, and then like with a bunch of overloads become 2,000 or so. And if you write a backend or a feature like VMAP for PyTorch, you have to like support this many operators, and that's like untenable. So we've been thinking about how to make it easier for contributors, hardware vendors to write backends for PyTorch. And the idea here is we want to reduce this 2,000 operators, decompose these 2,000 operators into a smaller operator set, and we want to call this like primitive offset. And so users write PyTorch as usual, and then it's our job in the backend to decompose them to a smaller primitive set. And we haven't settled on like how many primitive sets and what kind, but like that's something that we're thinking about. And lastly, I want to talk about the compiler. So on the backend itself, like with Dynamo actually acquiring the graph and then lowering to 810 prim IR, you can actually give it to a bunch of compilers, but we actually thought about building our own Torch native compiler called Torch Inductor, and it's heavily powered by OpenAI's Triton project. Torch Inductor is, we have a bigger deep dive later today, but it's actually written, it's a compiler that's written all in Python, and I think that's awesome because I can like hack on it pretty easily. And it's breadth first. It tries to cover as much of PyTorch as possible rather than saying, oh, it only works for like these small sets of models. It works on CPUs via using GCC and LLVM, and for NVIDIA GPUs, it works with Triton as our backend. And it doesn't work with Volta and anything except Volta and Ampere GPUs. So the older NVIDIA GPUs don't work. It also doesn't support other GPUs. So CPU support is being worked upon very closely by Intel. Intel has been a great partner, have been sending a lot of contributions to this backend. And for other GPUs, AMD is actively working on support, and there's some effort to try to like backport Triton to also work until Pascal GPUs, but anything before that, it's unlikely we'll see any benefits. So Triton, just briefly, is like a DSL written in Python. It's like a CUDA, but you can write like at a higher level and in Python. And so Torch Inductor uses this like low-level DSL to actually generate sophisticated code automatically. So you as a user don't have to do anything. The Torch Inductor's job is to do the compilation. And then we have a few other backends, and a few other backends in the works as well. So I will introduce all the pieces of technology that we want to deliver in 1.14 and beyond. And let me come back to this slide, right? This was the plan to actually deliver 30% performance across multiple precisions, across amp precision, which is like float 16, which generally gives higher speedups, and float 32, which is already doing a reasonably good job within PyTorch, so you're not going to expect as much more. And we basically took these like sets of 161 or 163 models and talked we were figuring out how to get these speedups. So where we are today. On float 32 precision, as of today, we get 24% speedups on TIM, 45% on TorchBench, and 22% on Hugging Face. Out of the box. Like you just like wrap your model, and then it just works. And on amp precision, this gets way crazier. Like we start getting real numbers that a compiler should see. We see 42% increase in TIM models, 86% on TorchBench, and 62% on Hugging Face. And really, consequentially, that means if your model training is running for 5 days, now it runs like 62% off. No, it's 60% faster than 5 days. It's like 3 days or something. So I think that's like real meaningful change in your productivity with this kind of stuff. And like the way we could do an aggregated speed up is like 75% of AMP and 25% of float 32. And that's something we established when we started this effort. It's not something we did post hoc. And we kind of are luckily looking at like reasonably good speed ups. Now, caveat. These speedups are on A100 GPU. If you try it on a desktop GPU like an NVIDIA 3090, the speedups are going to be slightly lower. And that's just that the faster and bigger the GPU, the more eager mode cannot keep up, and we need to introduce a compiler. So if you're using a GPU that's not that doesn't have as much like where PyTorch is already doing a reasonably good job, then like you're not going to see as much. But like I think they're lower, but they're still pretty good. So with all this, we were all pretty confident that this was a solid mode, and we are actually introducing today torch.compile within the PyTorch framework. And it is available in the nightlies today. And that's something that we want to ship into 1.14. And we have a few modes. We have a mode for smaller models, like if you just have a tiny model and it's mostly framework overhead bound. We have a mode to like purely reduce overhead, but it trades off some other things. Like it takes a little bit of extra memory, but if it's a small enough model, you don't care. And then we have a mode that takes very long time to compile, but it will give you slightly better performance. And the default mode tries to just sweet spot everything. It takes about like 10 to 30 seconds to compile on average, and it doesn't take extra memory, and it kind of gives reasonably good speedups. Now, we have a few backends, but like Inductor is our default backend, as I said. And we support dynamic shapes, but dynamic shape support is very early. It is not yet ready for like consumption, but like when we actually do a stable release, it will be. But just one cool, my slides are here. One cool graph is we actually validated it with, say, GPT-2 training, and it does look pretty impressive. It's the thing in pink. And you can compare it with a commonly used trick in the industry called static shapes as padding, where, if you have dynamic sequence lengths, you just like statically pad them. And like dynamic shapes by natively will actually make a meaningful difference in performance versus doing static shapes and padding. And Horace actually will talk later today in more detail about this. And then lastly, we have full graph mode. By full graph mode, we mean you either compile the model as a one single whole graph, or you give an error message. This is like a more traditional compiler. And that's kind of useful for certain backends, like say TensorRT, who don't like partial graphs and stuff like that. So the way you think about it, we're going to have eager, which is a default, but you don't get a bunch of performance benefits. And then torch.compile by default will emit partial graphs, and you'll get most of the benefits, except for like a little bit, like you can't export it to mobile, and like you can do some very advanced distributed parallelism. And then you have torch.compile with full graph mode, which might involve you changing your code a little bit, but it can give you that last mile 5% performance, or you can export it to various edge devices and things like that. So in some near future, and Michael Suo is going to talk about it, we will have a torch export of your model so that you can actually export it and send it out to a different backend completely. And in some far-flung future, we will have torch.compile not just wrap the model, but also wrap the entire training loop so that you can get more fusions across like you can fuse the optimizer in and things like that. So distributed works, and not only does it work, it has great speedups. These are AMP speedups with distributed data parallel. And you see some models are like, I don't know, 15% faster, some models are like 80% faster, kind of. So if you make the model faster, the communication starts becoming more of a bottleneck. So at some point, we got to figure out how to like carefully adjust that as well. But the other interesting thing is actually like if you use FSDP distributed mode and you train any of these models, like because of the fusions and like carefully like managing and reusing memory, it takes lesser memory. So like so the TIM's vision transformer large, it's taking 70% of memory compared to eager mode. So you can actually fit a larger model in the compiled mode in certain settings like these. So that's kind of cool. And even in the compiled mode in non-distributed, that's something that we expect to an extent, though it's not fully true today. So the compiler that we built, it has a solid set of debug tooling, or at least like an early solid set of debug tooling. We have a minifier that actually, like, if you have an issue and you want to report it and you have a big code base, you invoke the minifier. It will reduce your problem to a small code snippet that you can post on GitHub and things like that. Just to summarize, we are introducing torch.compile in 1.14 and on our original goal of optimizing these 163 models. It worked out of the box without any change 93% of the time. And it works 43% faster on average in the aggregated numbers, performance numbers, compared to eager mode on an A100. So, OK, first, this is a lot of new stuff to take, and the room is like, OK, like I'm overloaded. Like, can you like calm down? So let me just like step back and say this is all going to land in 1.14. It's available in our nightlies today. And we're pretty excited about that. But then one of the things I was thinking is like how actually like the way users are going to use PyTorch is going to fundamentally start changing. Like they're going to use eager mode for most things by default and experiment and stuff. But anytime they start doing a large training run, they would want to switch to compiled mode and wrap their model in the torch.compile. And this is meaningfully new experience. It's not in terms of you using PyTorch, it's not going to be the same way as before in some deep way. And I think we have a road to showing substantial speedups, and we have our initial numbers today. So I was like, why don't we just call it 2.0? I mean, it makes sense. Like, we should just call it PyTorch 2.0, and we also can stop having those long version numbers for a little bit. And so we are going to actually call this 2.0. And within the two series of within the two series of releases, we have a bunch of stuff planned around performance and compilation and scalability. We have some quotes from people who have tried this. First from Sylvain, who's a primary maintainer of Hugging Face Transformers, who tried it, and he, in his own words, he said, hey, I added one line of code, and it's like 1.5x to 2x faster in the models I trained. And that's like a good validation that it's not just us pretending to say that it works, and you have to believe in this room. Luca Antiga, who's also here, says nice things. I will let you read it for a sec. But basically, we've tried to validate it with some of our most power user PyTorch customers, and they seem to agree that this is a solid direction, and this is a nice thing that they would support for PyTorch to go into. Ross Whitman, who is a maintainer of TIM, also tried it, and he basically is like, it just works with majority of TIM models. I didn't really have to change any code or have that experience that I had with, say, TorchScript kind of thing. Now, what else, right? Okay, we're going to deliver 2.0 stable release in the beginning of March. And it's available in the nightly starting today, and you can go try it. And obviously, like, it's going to break in many million ways, and you're going to be like, oh, Soumith, like you said, it's going to work. So file away those GitHub issues. And in the rest of the 2.x series, we're going to release 2.0 stable early March. And in the rest of the 2.x series, we are working on, as I said, the stable primitives that I talked about, export mode, support for more accelerators and backends. And I think, and we know how we can get a lot more speedups than we have today. We have a bunch of ideas around compiler optimizations. And there's a bunch of ideas here, actually, that we want to do, but we don't have the bandwidth. And now that we've built this entire compiler stack in Python, and it's easy to contribute to, even though it's conceptually, it's a compiler, and it's like hard as in general, we would love you to take part. Like, come help us build this thing. File a GitHub issue on what your plan is and what you plan to improve. We have, what's my next slide? Oh, yeah. We have a Q&A webinar happening over the next month or so, where you can talk to the devs directly, maybe discuss some of the ideas you want to implement. So 2.0 is fully backward compatible by definition, and I want to say this out loud because people will say, oh, 2.0, does this mean I have to rewrite my code? Despite everything I said in the slides, I think that's easy to misunderstand. We didn't do a rewrite. Like, it's the same code base. It's the same code. It's just we're introducing a new substantial feature in compilation mode, and that's fully optional, and you wrap your model explicitly to get that mode. So your code base works as is. I mean, we were going to call it 1.14, and then we're like, oh, it would be nice to call it 2.0. So it's fully backward compatible. So before you go on Twitter and be like, is 2.0 fully backward compatible, or should I rewrite my code? I'm telling you up front. Try it today in the nightly binaries and give us feedback. And we have a bunch of deep dives starting from the next talk on how each of these technologies actually works under the hood. And don't miss our Ask the Engineers series that is happening, starting this month online. And also, we have some office hours. If you want to try it out today in the afternoon and you have questions, you can bring your laptop on at the back. We're going to have the office hours later today. With that being said, I will start handing it off to Peng Wu, who will deep dive into Torch Dynamo.
I was waiting for all this talk for him to utter the word PyTorch 2.0. And finally, he said it. Welcome to PyTorch Conference. This is my first one. I'm Peng Wu. I support the PyTorch compiler team. So as a compiler person, PT 2.0, to a large extent, is really a compiler story. And you might wonder, why does it take so long for us to actually fully embrace compiler technology into the core of PyTorch? And the reason is because what makes PyTorch beloved by researchers is flexibility, dynamism, expressiveness is exactly what makes it very hard to compile. So it took us 5 years of developing various solutions, compiler solutions, to get to where we are. And I want to call the inflection point of our journey searching for the right compiler solution Torch Dynamo, which is what I'm going to talk about. So it starts with asking this question: what is one thing that we could change first in the compiler stack that will fundamentally change the efficiency of PyTorch? It's not a new compiler optimization. It's not even a new compiler backend. Actually, the the key first move lies in the top part of the compiler, which is the graph capture. So we all know that graph mode execution can be a lot more efficient than executing ops one at a time, especially if you are a machine learning accelerator designer or if you are a production engineer. Unfortunately, for eager first machine learning framework like PyTorch, it's actually non-trivial to get graphs reliably. So that's why we care about graph capture, because it's simple. If you don't have reliable graph capture, you don't have a reliable compiler coverage. So let me introduce TorchDynamo, our first out-of-box graph capture. Here's one example of a toy PyTorch program. And here is this one-liner change torch.compile. And in this example, we actually allow you to specify a custom backend. And in this particular example, my compiler basically takes the graph that's captured by Dynamo and do something about it, which basically print it out and return a Python callable. So if you execute this program, you'll be surprised to see actually 3 graphs being printed out, because in this example, we actually put a twist of a data-dependent control flow. So this graph break actually is a feature, is a fundamental design feature of TorchDynamo that makes it out of box and sound. So let me double click on what makes TorchDynamo sound and out of box. Number one is partial graph capture. So this is our ability to skip anything unwanted and then fall back to eager. And with partial graph capture, we save the programmers to have to shoehorn their models into what the backend compiler want. Instead, we're just simply transiting in and out of between eager and the graph mode. And then there is the guarded graph generation. Basically, we want to make sure whatever we're capturing at capture time is still valid when we're replaying this graph. And finally, if we did find a mismatch on the guard, we have the ability to just in time recapture them. So basically, partial guarded graph capture with just-in-time recapturing is what set Dynamo apart from all our previous graph capture technologies. And by the way, there's this thing called AOT autograph that captures the backward part of the graph, and that makes it working for training. So I want to show you some numbers, which Soumith already highlighted in his keynote, that would back the claims we made so far. You have seen this 7K plus model, so this demonstrates that it indeed works out of box. And right now we have more than 20 experimental backends for inference that's integrated with TorchDynamo, and we have more than one backend that's integrated with TorchDynamo for training. And the number is smaller on training side, not because of Dynamo, but because there are just less number of training backends available. And we're working actively with vendors to migrate into this new stack. And finally, you've seen this 30% number. What does it say? Actually, it's not only talking about the performance, it also demonstrates that partial graph actually works. So by capturing graphs and allowing graph breaks, we not only did not diminish the capability of the backend optimizing compiler, we actually amplify it by bringing more models or more regions of the models into the compiler world. So Dynamo is great, but if you are an experienced PyTorch compiler user, you would ask this question. So which technology do I use? As of today, we actually recommend using TorchDynamo for any scenarios that can be deployed with eager. So that includes most of the training scenario and some of the inference scenarios. And for all the other scenarios, which we call the export path scenario, our existing solution still works. But in the future, actually not so far future, we actually want to have an organic consolidation of front-end technology around TorchDynamo. It has always been our vision to have a unifying front-end and have a vibrant, thriving back-end ecosystem. And the speed of our consolidation actually depends on 2 things. Number one, how fast do we deliver the PyTorch 2.0 export story? And number 2 is how fast the vendors can migrate into this new stack. So we look forward to that new experience of a consolidated front end. Yeah, so that's Dynamo, and I want to bring you back to the question we asked in the beginning of the talk. What is that one thing, right? So as a compiler, optimizing compiler person for 2 decades, I never imagined myself talk about a compiler front end. But the front end part of the compiler, graph capture, really matters, because once we're able to bring most of the PyTorch models seamlessly into the graph world, the era of compiler-accelerated PyTorch really arrives. So if you're excited about this vision, there are more nuanced aspects of the compiler story that you are going to hear today and in the following months. And if you're an ML practitioner, I would encourage you to try out PT2 on your workload. And if you're a vendor, I encourage you to talk to us to explore migrating into this new stack. And finally, we have some talk series that would dive deeper into the technology in the PyTorch 2.0 stack. So with that, I'm going to pass the torch to Jason Ansel.
Hello, everyone. My name's Jason Ansel, and I'm going to talk about Torch Inductor, which is a new compiler backend for PyTorch 2.0. When designing Torch Inductor, we started off with 3 key principles. So the first principle is that Torch Inductor is PyTorch native. And what this means is that Inductor uses very similar abstractions to PyTorch Eager, which allows it to faithfully capture all the behavior of PyTorch. The next key principle is Python first. So with PyTorch 2, we are embracing Python. And part of that involves writing Inductor entirely in Python, which makes it much easier to hack on and extend. And then finally, we wanted Inductor to be really general. And so we focused on breadth rather than depth early on, which means tackling the tricky operators and tricky optimizations early to ensure that our design was general and could scale. Inductor uses 3 key technologies as well. The first technology is a define by run loop level IR. And what that means is that the core compiler IR that's done at the loop level is actually a Python callable. And to do things like code generation and analysis, we actually execute the IR and do that, which is a sort of novel trick in the compiler space, but something that's been used for PyTorch programs for a while. Next, we really wanted Inductor to support dynamic shapes and strides from day 1. And so Inductor uses SymPy, which is a symbolic math library, to reason about shapes and generate code that's not specialized to specific input sizes. And finally, we didn't want to reinvent the wheel. We wanted to reuse state-of-the-art languages. And so we took inspiration from what our users were doing. And increasingly, we were seeing people write high-performance kernels in this new language, Triton, by Philip Tillett at OpenAI. And so what we have is we have a compiler in Torch Inductor which generates Triton code, which is easy to understand. You can look at the output and inspect what it does, or even change it. And on CPUs, we generate C++ code. So what is Triton? Triton is, you could think of it as a better CUDA. So it's a higher level language than CUDA, but also lower level than a lot of pre-existing DSLs. And it makes it really easy to write high performance code, even for tricky things like matrix multiplies that are competitive with things like cuDNN and cuBLAS. Next, I'm going to talk about a define by run loop level IR. And so here's what the IR for a permute and an add would look like. And so we have this inner function here, which takes a list of SymPy expressions. That list of SymPy expressions represents a coordinate symbolically that we want to generate. And then the body of this function will call ops.load twice and ops.add once. And the way you use this IR is, for example, if you wanted to write an analysis pass, you could replace this global variable ops with something which records the loads. Then you could run this function, and you could do your analysis to figure out what loads this function makes. And if you wanted to do code generation, you could replace this ops function with something that printed out Triton code, execute this function, and do code gen. This makes it really easy to write lowerings, because if you're building composite ops that sort of take two inputs together, you can actually use the features of the Python language to build your lowering. And then partway through the compilation process, we actually use FX to trace this defined by run IR, which gives us a IR that's more manipulable. So here's an overview of the compiler stack. We start off with the graph that Torch Dynamo has captured, and we use Autoencoder and PrimTorch to decompose the operator set into a much more minimal operator set, around 250 operators. And Autoencoder captures the forwards and the backwards graph, which we compile independently. Next, there's graph lowerings. Graph lowerings takes this primitive operator set, which is around 250 operators, and lowers it to inductor's loop level IR. And the inductor's loop level IR contains only around 50 operators. So we've removed a lot of the complexity and simplified the graph substantially. We're now operating on basically single elements of tensors rather than full tensors as in the input. Next, there's the scheduling phase. Scheduling is where we decide what gets fused with what, and do other optimizations such as memory planning and tiling. And then finally, we have code generation. And so there's two pieces to code generation. We have the backend code generation, which either generates Triton code or C++. And then we have what we call wrapper code gen. And wrapper code gen is the code that stitches together the calls to many different kernels. And it basically replaces the interpreter part of the compiler stack. So here's some results on GPU. I know Soumith shared these earlier, but Inductor generates up to 1.86 geomean speedup on large realistic benchmark suites. And we're super excited about these results and hope to continue to improve them in the future. We also have results on CPU, and these CPU results are a collaboration with the Intel PyTorch team. We see up to 1.26x geomean speedup on CPU inference. And this serves the purpose of having Inductor support CPUs, but it also supports the purpose of making sure the Inductor is general. We didn't want to build a compiler that only supported GPUs. We wanted something that could scale to support a wide variety of hardware backends. And having C++ as well as Triton forces that generality. So thanks so much. The code base for Inductor is in the PyTorch repo. I've linked it here. And there's more information in the blog post as well. Thanks so much.
All right, I'm Michael, and today I will be talking about PyTorch 2.x series export path. So this is more of a directional thing that we plan to launch in the coming major versions of PyTorch. So what is PyTorch 2.0 export? It's a workflow for whole graph capture and optimization that's using the best technologies that Peng and Jason and Soumith talked about that we are using to bring compilers to PyTorch in order to provide an explicit whole graph capture workflow. So why do we care about export? I mean, we talked a lot in the previous talks about sort of rich out-of-the-box graph capture, but we know that our most demanding production users typically want granular control over performance and runtime behavior. So for example, users with hard latency or resource utilization budgets tend to want ahead-of-time guarantees that certain optimizations will be performed, and they don't want dynamic compilations necessary in the loop. As another example, we have a lot of users that operate in fairly constrained runtime environments. Python might not even be available. So for example, if you're running on an embedded system or on a phone or in a C++ only inference environment, Python might just not be available. So for these users, we plan to provide an export workflow, which utilizes the core technologies of PyTorch 2.0 to produce a single graph ready for a downstream system. And that's the third major use case for export, which is that we want to interoperate with a vibrant ecosystem of backends, and that means we need to meet them where they are, which is generally providing a whole graph that represents the compute for a single model. So there are three components that we want to deliver as part of this vision. So first is the whole graph export API that we've been talking about, which leverages the latest graph capture technology in Torch Dynamo to soundly and easily produce a single graph out of your PyTorch model. The second is that we really want to focus on simplifying integration with PyTorch by standardizing our graph representation on a smaller number of operators with well-defined semantics. So this is the primitive operator set that you've heard people talk about today. And lastly, we want to provide tools for working with and transforming graphs so that folks integrating with PyTorch don't have to reinvent the wheel every time when they want to do basic compiler transformations. So first, for some background, I'm going to describe a little bit about what we do in PyTorch 2.0's default mode, which for the purpose of this talk, I'll call the just-in-time or JITted mode. Now, this API is already a little out of date. We're moving kind of fast in PyTorch land. So Torch Dynamo optimize is really Torch compile now. But when you call an optimize function, Torch Dynamo performs a sort of bytecode analysis of the program and creates an optimized representation, which intersperses partial graphs with Python code. And it then attaches guards to this optimized representation so that if you call the same function with materially different inputs, say now your tensors are on a different device, Torch Dynamo will transparently recompile the graph. So you always get correct results. So there's a lot going on under the hood here, but this is how we can provide the sort of magical default experience of PyTorch 2.0, where you can add just a single line of code to your program and get significant performance improvements with no manual intervention, no tweaks to your code, et cetera. And we're confident that the majority of PyTorch users will really love this workflow. You get performance without compromising the fundamental user experience of PyTorch. The export stack allows you to capture your entire model as a single graph. So whereas previously you had sort of this interspersed partial graph and Python code, here we just export a single graph with the sort of assumptions made by that graph. Hey, my tensors are on GPU, or my tensors have a particular set of shapes or vary along dynamic batch length, et cetera. And any assumptions the model is making will also be returned for inspection by the user. So unlike Torch compile, this workflow is explicit rather than implicit. Sometimes Dynamo doesn't know how to represent something in the final graph. Say you have like an async generator in your model or something. And in these cases, you may be required to change your model code. However, in practice, we find that the majority of models that we're seeing on our benchmark suites can be exported cleanly to a full graph. So that's the export API. But what are we actually exporting? One of the historical hard problems that backends have faced when integrating with PyTorch is that PyTorch has over 2,000 operators, and historically we've lacked very good sort of guarantees about their semantics, right? So here's a figure from Horace, which I believe we already have, like maybe we've spawned like 400 more operators in this time. But this is sort of a breakdown of all the operators within PyTorch, and there's a great amount of complexity. And so if you want to support sort of every operator in PyTorch, it's historically been an almost insurmountable task. So our response to this is we want to greatly simplify our operator set, which is called A10 if you don't know. And we want to make stronger guarantees about their semantics. So one example is we want to greatly reduce the number of ops by eliminating variance. So add out, add underscore versus add. And we want to express some of the compound ops in terms of decomposed, smaller constituent ops. So we can produce a subset of ops that's a lot easier for a backend to handle. And you go from 2,000 plus to around 750. This subset also has fundamentally simpler semantics. So A10 and PyTorch are typically quite expressive, so you can do sort of in-place mutation of tensors, you can do striding, et cetera. But in this simplified subset, all of our ops are purely functional, tensors are always contiguous, et cetera. And this allows us to solve some of the problems that we see backends repeatedly running into when modeling PyTorch. For example, how to deal with tensor mutation, or aliasing, or striding. The export system will ensure that these are not present in the exported graphs, but retain the sort of soundness properties of the graphs themselves. So overall, we think that this will greatly simplify the task of writing a backend for PyTorch. And we also want to provide sort of guaranteed metadata information. For example, what is the shape and device and D-type propagation of any given operator, so that each individual backend doesn't have to construct their own sort of lookup table for this stuff. We can provide it sort of canonically correct within the Torch library itself. And for sophisticated backends that want even more control, and Jason talked a little bit about this, we can further decompose operations to a so-called primitive operator set. That's just 150 to 250 ops with very, very simple semantics. So in this case, a lot of the implicit behavior of PyTorch operators, like promoting different tensor types, broadcasting shapes, can be made explicit. And our goal here is to achieve functional conformance as a PyTorch backend, you really only need to implement the set of primitive ops. And this makes it a lot easier to bring up a new backend on PyTorch. Now, obviously, if you're decomposing your entire model to these really small set of ops and you just sort of ran them naively one at a time, that would be pretty slow because there would be a lot of per operator overhead. So this is mostly intended for sophisticated compilers that can reclaim the performance via operator fusion. But it is a sliding scale, right? You can choose whether to decompose an operator from the sort of A10 level, the closer to eager level, into the primitive ops set, so that you can start by implementing first the primitive set of ops, and that guarantees sort of, you can run any PyTorch model. And then slowly you can sort of implement more of the higher level eager ops to get back performance that way. We also want to provide utilities and common functionality to make it really easy for people to work on the graphs that they're getting out of this system. So right now, getting your code out of PyTorch into a backend requires a significant amount of custom work. Every backend acquires the graph and works with it in a slightly different way, and we see a lot of people reinventing the wheel when it comes to common compiler passes, like dead code elimination, common sub-expression elimination. They write their own pattern matchers, et cetera. So we want to make it as efficient as possible to map this exported A10 IR onto any backend. And so we want to provide a set of tools and functionality and infrastructure to allow people to do that. So just to recap, for PyTorch 2.0 export, we want to provide a whole graph explicit export API that lets you get a sort of freestanding graph out of any PyTorch model. We want to standardize our IR and operator set so that it greatly simplifies the task to bring in a new backend. And we also want to consolidate our compiler infrastructure to avoid every backend reinventing the wheel. And by doing this, we want to foster a really vibrant ecosystem of separate backends. And for us, significant functionalities in Tree. Now the APIs that you saw in this slide are not final, but they are available in the nightly. And we plan to stabilize this functionality and make it generally available in a follow-on release from 2.0. Thank you, everyone. And now Horace, I believe, is going to talk about our support for dynamic shapes within the whole PT2 stack.
Hey, so my name is Horace, and I'm on the PyTorch compiler team, and I'm here to talk about dynamic shape support in PyTorch 2.0. So what is the problem we're trying to support here with dynamic shapes? So what we're trying to do is we have a neural network, and we want to pass it inputs with different shapes. In addition, we want this to be fast. So one natural question might be, why am I up here talking about this if this already works? Like, if you take a PyTorch program and you pass in tensors with different shapes, this already works fine, and I'm sure many of you have already utilized this feature. Unfortunately, with compilation, as previous speakers have mentioned, things become quite a bit trickier. And to understand why, let's take a look at the execution flow between eager mode and PyTorch 2.0. So in eager mode, what we do is when you get in a tensor, is we go through the Python code, then we go through the PyTorch C++ code, and then we go through the kernels. And then when you get another input, you go through the Python code again, and then the PyTorch C++ code again, and then the kernels again. On the other hand, with compilation, this execution flow becomes quite different. So upon the first input coming in, we capture all of this logic, and we create a compiled graph out of it. Then the next input that we get, we need to look up this graph, and if it's in the cache, then we can just jump directly to the compiled graph without needing to go through all of these steps again. And so notably, this reuse of the graph and the static representation is what enables us to do these optimizations and gain the performance. However, it also introduces a new challenge, which is that all of these components, the Python code, the C++ code, and the kernels, can all depend upon the shapes. And so in eager mode, this isn't a problem because you're re-going through this entire thing each time. But in compilation, this is a problem. So our compiled graph needs to be able to support different shapes. And in the case that it encounters a shape that it does not support appropriately, we need to be able to know about this, and we need to know that we need to recompile, and this graph is no longer valid. So there are two main ways, or two main things that we need to do in order to support symbolic shapes, or that our programs can depend upon the shape values. And one of them is if you just directly use the shape values in your program in some manner. And so this is totally fine in static shape world, because when you look at a shape, it's just an integer, and it's totally fine because the shapes are all static, and you can just rely on this being a constant. However, in dynamic shapes, these are no longer constants, and so we need to be able to treat these as symbolic values. And so this is actually quite tricky. So as you can imagine, because we have a lot of C++ code, and in C++ code we have integers everywhere, and now these are no longer just integers. They need to be symbolic values, and we need to do this across our entire system. And so this required a lot of work. But as a result of all this work, with symbolic tensors, we have this cool, exciting new system where if you print out the shape of a symbolic tensor, we can now have a symbolic representation of the shape. So we can take a look at what being able to propagate these symbolic shapes through our entire system gives us. So this is a IR for Resident 18. And so if you take a look at the metadata there, we can see that it's a float 16 tensor with 4 dimensions. And so the first dimension is S0, this a varying batch dimension. The second dimension is 64. As for Resident 18, the channels need to be static. And then the last 2 dimensions are pretty interesting in that the shape of them are the input shapes downscaled by 4. And so you can see that the last one is kind of non-trivial representation of shapes. And so this is all enabled by representing our shapes in SymPy, which is a commonly standardly used symbol manipulation library. So the other issue that we need to, the other way that you can rely on shapes other than directly is basically indirectly through control flow. And so there are 2 kind of main observations that motivate our design. So the first one is that control flow actually is a very useful source of information about the shapes in our program. So for example, if you do an operation between 2 tensors, oftentimes the shapes need to be identical. And so this provides us information that allows us to simplify our shape expressions. The second the second observation that we had is that it's actually fairly rare to actually branch extensively upon control flow in your system, especially many times through the course of your execution. And so this motivates our system, which we call specializing and guarding. And so what we do in this sample program is that when we encounter this control flow that shape 0 is more than 5, we peek at the underlying shape. We see that we go down the first branch, which is that the shape is more than 5. And then we guard on this, the branch that we went down symbolically. So you can see in the bottom, we have just a graph that just has a multiply in it without any control flow, and as well as kind of a precondition on what cases need to be required for this graph to be correct. And so note that because we've propagated shapes through our program, these guards are all evaluatable without needing to rerun our graph. And so when we see a new tensor whose shape is less than or equal to 5, we know that this graph is no longer correct and that we need to retrace and recompile. So although specializing in guarding is a very useful technique, there are many other tools in the toolbox, particularly for the export path that Michael mentioned earlier. So for example, if you really want all of this in a single graph and you don't want to specialize it, we'll provide control flow ops where you can manually ensure that you have both of these components in a single graph. So those are the main components of our symbolic shape system. And one of the things that has, I think, historically made dynamic shapes so difficult for a compiler to get working is that you really need this to work across all layers of your stack, right? So if your compiler supports dynamic shapes, but then your compiler your front end does not support dynamic shapes, you end up with a system that doesn't support dynamic shapes. And so when we were looking at supporting dynamic shapes with PyTorch 2.0, we knew we couldn't really do it in a half-baked manner. And so implementing the system required a lot of investment across many layers of our stack in order to ensure that symbolic shapes worked all the way through. But as a result of all this work, we now have a system that, one, allows Torch and Darter to generate efficient code for different shapes without needing to recompile. Two, it's built for both the JIT and the export style use cases and is integrated into the PyTorch 2.0 export path. And three, this is all enabled by deep integration into the core components of PyTorch. So, talking about how cool our system is one thing, but it's good to actually look at some numbers to demonstrate what we can do. And so one disclaimer I'll add is dynamic shapes are still under active development, and so these results were obtained on a feature development branch and not a master. But we expect that all of these will be in master by the release. So if you take a look, a very common use case for dynamic shapes is for language models with varying sequence length, especially for autoregressive generation. And so in this case, if you take a look at the orange line, which is PyTorch eager, you can see that it grows smoothly with the sequence length. It doesn't need to recompile. And so this is kind of the experience that you guys get today. And so one way to deal with varying shapes, if you only support a static shape compiler, a common technique is to pad to the nearest power of 2, and then pass that through your program. And so you can see what the performance looks like there with the purple line, where you can see that you have these jumps where you need to pad up to the nearest power of 2. And so although this improves performance in many cases, you can see that we're still leaving a lot of performance on the table due to the extra overhead introduced by these computations. On the other hand, with PyTorch 2.0, with dynamic shapes, the pink line, you can see that we not only generally outperform both static shapes plus padding, as well as eager mode by a pretty significant margin. We're also able to kind of have this smooth performance curve as we increase the sequence length, which is kind of what you get from eager mode as well. Another nice thing about supporting dynamic shapes is for reducing compilation time. So although we do this pad to the nearest power of 2 to minimize our compiles, we still need to compile about 5 or 6 times for static shapes in this example. On the other hand, dynamic shapes only needs to compile once, resulting in significantly reduced compilation time when needing to support these kinds of dynamic shapes. So although I've spent most of our time today talking about compilation with dynamic shapes, the system that we've built is not really only for compilation. Really what I view what we've built as is a system for symbolically reasoning about shapes in PyTorch. And so this enables potentially new future things that we can do. So for example, one thing that you might build with this system is you might want to symbolically shape check your function. So you might want to add some annotations to your function, and then we can symbolically reason about your shapes and tell you that, oh, hey, actually certain inputs might result in a shape error in your program. And another thing you might do is you might want to count the flops in your neural network symbolically. So you might want to get a symbolic representation of how the flops in your transformer network scale with the sequence length or the batch size. So thank you for listening to my talk. And there I'd also like to thank many other contributors to the symbolic shape system who kind of brought it to where it is today. So yeah, thank you for your time.
Hi, everyone. How are you all doing today? I'm Anjali. I'm a TLM on the PyTorch distributed team. Today, I'm going to be talking about some of the APIs we're building for scaling workloads. Can we go back a slide, please? I think they're a bit out of order, so I'm just going to have to wing this. OK, the mission of PyTorch distributed team is the following. We want to build easy, efficient, fast, and reliable large-scale training APIs for PyTorch users. Our mission is rooted in 3 core values. We want them to be usable, we want them to be modular, and finally, performance. We want APIs to be intuitive to users. We want them to be able to seamlessly scale from a single GPU to multiple GPUs. We want them to be modular, such that you can build 2D and 3D parallelism solutions. We also want them to work well with other PyTorch features. And finally, we want this enabled stack to give the best performance at scale. We can think of PyTorch distributed APIs in the following format. We have high-level end-to-end APIs that provide data parallelism like FSDP and DDP. APIs that provide pipeline parallelism like PIPI and tensor parallelism APIs. These core APIs and ML workflows in general are powered by the core, these end-to-end APIs are powered by core APIs like distributed tensor, distributed checkpointing, activation checkpointing, and collective APIs like C10D. Moving from Eager to PyTorch 2, we've enhanced our existing APIs, added new ones, and also added Dynamo support for DDP. Let's take a look at DDP and FSDP, which is how we've implemented data parallelism. Most folks might be familiar with DDP, where we replicate parameters on different devices. We enable gradient synchronization using already so that params are in sync. FSDP also implements data parallelism. But here, you shard parameters on different devices, and you use all gather before you have the forward pass of the enable module. Post the prototype and beta release of FSDP, we've been working on enabling new features and working on enhancing existing ones. For example, we worked on better interoperability with activation checkpointing. Now it depends on the safe tensor hooks, which means that we were able to solve a lot of edge cases. Next, we've also enhanced mixed precision offering so that it works better with bfloat16, which means you can run a larger model but have better performance guarantees. And finally, for tackling issues in the forward prefetching arena, we've enabled a rate limiter. An example on the right, we can see a DDP module being wrapped and an FSDP module also wrapping a module. So these are both module wrappers, essentially. Like mentioned in the keynote by Soumith, we've also enabled Dynamo support for DDP. Using a single line of code, torch.compile, we can now optimize this DDP example with Dynamo. Dynamo optimizes DDP by breaking the graph at the collective boundary. This means it's the size of the subgraph, and basically the number of parameters or size of the parameters in subgraph is equal to the gradient reduction bucket size. This is needed for computation and communication overlap. Without this, you'd be compiling into a single kernel, smaller number of graphs, and you would essentially be calling collectives after the backward pass has been completed. To enable pipeline parallelism, we've implemented a prototype API called PIPI. PIPI API enables your model to be converted into a graph, sharded using user-annotated split points, and enables micro-batching and specialized scheduling of forward and backward passes that's needed for pipeline parallelism. We've been working on enabling or improving PIPI such that now we provide deferred initialization so that you can just initialize the specific stage on the GPU. So you have larger models that can now use PIPI. And we've also been working on enabling better automated split APIs. So users can specify the number of stages they want or the size of the stage, and we can automatically shard your model. PIPI is a cross-host pipeline parallelism solution, and it also supports complex architectures like skip connections and shared params. So looking at an example on the right, we have a pipe object that we instantiate from a split module. And essentially, it's the pipeline driver that orchestrates, that we've instantiated that orchestrates the forward and backward passes, and also how we do the micro-batching and et cetera. We've also implemented tensor parallelism using core D-tensor constructs. Tensor parallelism is useful when you have computation that is inherently parallel, that you can then shard across devices. It's also useful when you want to defer maybe synchronization. Tensor parallelism API that we have, which is a parallelized module called on a model, and we specify a parallel plan, which specifies how you want to shard the weights in your model. Let's take an example on the right. We have an NN linear module, and we call parallelized module on it with a column-wise parallel plan. This means you're sharding the weights of your module in the dimension 1. The inputs and outputs to this layer is actually massaged based on the parallel plan, so they can be sharded or replicated as specified. Let's take a look at example 2 below. Here you actually have an entire transformer model that you can call parallelized module with. And here we specify a pairwise parallel plan. So you run column-wise sharding followed by a row-wise sharding. So parallelized module is actually built on top of D-tensor. And D-tensor is how we specify how annotate how tensors should be sharded or replicated. We also provide support for 2D parallelism using parallelized module. So the example on the right, it's the same example as before where we're calling parallelized module on a transformer model, but then we wrap it with FSDP after. So this is an example of 2D parallelism. Tensor parallelism API, like parallelized module, is actually replacing the parameters in place with D-tensors that have been annotated to specify if a tensor is replicated or sharded. Here are a couple of resources to take back with you, links to PyTorch distributed tutorials and FSDP. We also have examples for tensor parallelism and PIPI, followed by a post describing how we enable Dynamo for DDP. Thank you. Handing off to Dennis, who's going to talk about TorchX.
Hi, my name is Dennis Vanderstay. I'm a software engineer at Meta and tech lead for TorchX, a PyTorch domain library for large-scale recommender systems. Yep, wrong button. So agenda today. So first we're going to talk quickly about what is actually TorchX. We'll do a brief code walkthrough, and finally we'll go through some performance benchmarks. So what is TorchX? I think simply put, it's whatever is missing from PyTorch to author and scale state-of-the-art recommender models. As you remember, PyTorch works well with deep neural networks, often dealing with dense inputs. However, it's less optimized for wide models with sparse inputs. That's where TorchX comes in. It's domain-specific. We have custom modules built for Rexus and optimized for distributed runtime environments. It's scalable. It leverages your model parallelism to automatically adjust to the author's demands from 1 GPU up to n GPUs. And most importantly, it's performant. TorchX performance optimizations are born from research and built for production. We are constantly scanning the latest research from academia and industry to find the new features that we think will help. At the same time, we're constantly refactoring our existing features to ensure that they continue to perform at state-of-the-art performance levels. So how do we do it? At its core today, we rely heavily on module-based model parallelism. What does that actually mean? Basically, TorchX will take your PyTorch model and prepare it for distributed training. The most common technique we typically use is to actually replace modules with a sharded equivalent. So in the example on the right of the chart, what you'll see is here we have an embedding bag collection, which is our customized module, and we'll swap it out in the sharded environment. Basically what we're doing is we're keeping the embedding lookup, and then we're adding collectives before and after that operation automatically, so the user doesn't have to worry about those things. Basically, that first communication lookup is going to communicate the data, input data to the shard, and then the output of the embedding will be placed back onto the local device. Also, due to our novel use of awaitables, we're able to actually have multiple sharding techniques per module to optimize based on your sparse input data. And for the rest of your model, what we do is we typically wrap that in distributed data parallel, so we're ready for your distributed training environment. Beyond that, we offer a lot more features. We don't really have time today to go through each of them. If any of them catches your eye, I encourage you to go online, look at our tutorials and documentation. Plus, we'll see some slight results of these later in this presentation. But basically, to rattle them off, it's batched embeddings, fused optimizers, jagged tensors, hierarchical sharding, input batch pipelining, collective quantization, embedding quantization, automated planning, and DDR HBM caching. I hope you got all that, but I'd suggest just going to the website. Okay, so let's do a quick code walkthrough and to show you just how easy it is to apply TorchX to your models. So basically, I'll load the slide here. What we're doing is, at its core, what you need to do is we need to do some light modeling changes. We need to swap out your NN embedding bag collection, NN embedding implementation in standard PyTorch with our NN embedding bag collection, which is a specialized module which we provide. Basically, here you can see one that's configured. It has 2 embedding tables. We've also implemented in the library, for easy experimentation, a version of DRM, where you can directly just pass your embedding bag collection in, along with other inputs to try it out. Now, this output, with this amount of code, basically is fully functional. It's only going to execute on a single device, and as you can see from the execution diagram, basically what's going to happen is you're going to have the tables execute, do the lookups in serial, and then you'll have the rest of your model run. Now, obviously, we want to distribute this. So what do? Basically, first you have to initialize the distributed environment. So we borrow from PyTorch's distributed PyTorch distributed, and basically the first few lines of the code are boilerplate code, which you do to set up your runtime environment, which basically means for each device that you're working with, you typically operate it on one process. Now, once you've done that in each process, all you have to do is call DMP, which is our Distributed Model Parallel API. In this example, we're taking your model, and we're saying we want to run it on a CUDA device of various ranks. Finally, the output that you get is ready to run. It's basically ready for distributed environment. So what does it mean? Going back to our execution graph in the bottom left corner, as you can see, we have device 0 and device 1. Now we have that collective up front, moving your input data around. We have table 1 and 0 doing the embedding lookups in parallel, and then the rest of your model will execute distributed data parallel. Now there's some other tricks we do on top of this, but again, I encourage you to look at documentation to learn about that. Okay, performance benchmarks. So we want to take some light performance benchmarks here, and we're going to look at 2 things. One, what's like on a single GPU, and in the case we have multi-GPU. So in the first case, we're looking at the single GPU. So what's actually happening? So the first blue bar is what it would look like if you just used the standard embedding bag collection. This is before sharding it. And basically this, when we implement this, is a lightweight wrapper around PyTorch's built-in NN embedding bag. Now, as soon as you go and shard this, what we're basically going to do, again, is swap it out with our customized module. In there is highly optimized FBGEM OSS kernels, which allow basically 2 things, table-batched embeddings and optimizer fusion. The net result from a training loop is typically a 32x improvement. Now, when you're operating a single GPU environment, typically you don't have the luxury of having all your embeddings sitting in your HBM GPU memory. So what can you do? We support things like UVM caching, like I mentioned earlier. In this case, what you're going to do is have a majority of your embeddings sit on the CPU memory, while a small amount is cached on the device, typically around 20%. And here you'll see you will regress in performance slightly by 2x factor, but you're still operating 16 times faster than the baseline. And then on the extreme side, if you want to have all of your embeddings sit on your CPU and save the HBM memory for your dense parts of your network, basically you're only going to have a 30% performance regression. But we really aren't interested in just one GPU, we're interested in multiple GPUs. So in this example, what we're looking at is as we scale between 1, 4, and 8 GPUs in the last 2 bars. Now, inevitably what you notice, holding the batch size constant, you will get some performance improvement, but it'll be sublinear, particularly as you go between 4 and 8 GPUs. The way that we address that is basically what's happening, right? Part of the problem is fundamentally, at some point, eventually you have so much GPU compute and your CPU can't keep up. So one way to remedy that situation is actually increase your batch size, which is a common technique. So in the final bar, you increase the batch size by 4x, and therefore you get a much better performance, getting much closer to linear behavior. I think the main point of it is, as you scale your models, you're never going to get perfectly linear behavior. But we're constantly looking for improvements and techniques to continue to keep that curve as linear as possible, and I'll apply those automatically so the user doesn't have to worry about it. So that's all I had for this brief talk. And first of all, I'd encourage everyone to go to our website and look at pytorch.org/TorchX to look at our tutorials and to learn more. And everyone on our team, I just want to say thank you, and we look forward to seeing you on GitHub.
Wow. Over 40% performance improvements out of the box with PyTorch 2.0. It's like an early Christmas present here for everyone. So we'll take a quick 10-minute break, and we'll be back for more talks. Thank you. welcome back. These next round of speakers are here to tell you about new features of PyTorch. And please welcome Tristan Rice to tell you about multipy. Thank you.
Hello. Hi, everyone. I'm Tristan. I'm going to be talking about Torch Deploy. Torch Deploy is a system for running eager mode PyTorch models in production. We just launched into beta, so we hope you try it out after this. Let us know what you think of it. If you have any feedback, feel free to submit GitHub issues, that kind of thing. So I'm first going to talk about what Torch Deploy is, and then get into a little bit about why you might want to use it, and then finally get into just a little bit about how it actually works under the hood. So to start, kind of what is Torch Deploy? So Torch Deploy is a system for running multiple Python interpreters inside a single process. So this is designed to make it so you can basically run your eager Python models in sort of production environments. So you don't have to do things like scripting and that kind of thing. So it uses completely independent Python interpreters. So there's no global interpreter lock. So you avoid a lot of the issues that come from normal Python multiprocessing. So Torch Deploy is a C++ library intended for use for production inference services. It's targeting right now for production for Linux x86, 64-bit. But we also have support for ARM 64-bit as well. So here on the right side of here, this is sort of the hello world for Torch Deploy. You can see here at the beginning, there's the interpreter manager. This manages all of the sub-interpreters. You can specify any arbitrary number of interpreters. In this case, it's 2. You then can acquire an interpreter. In this case, we're just grabbing 1. But in an actual production system, you'd probably be doing this for multiple threads and independently managing the interpreters. You can then basically just construct your model in Python how you would. So in this case right here is just importing a very simple model. It's just a convolutional layer with some parameters there. But in an actual system, you can just import from some Python files or a Torch package or construct it inline like this. This returns a wrapped Python object from C++. So you can then basically use it how you might any other Python or C++ object. So in this case, we then basically just run it. So you just pass in a Torch tensor, execute it, that returns a Python wrapped object, and then you can convert it back to a tensor. So you can do any pre or post processing in C++, and then just pass it straight through there. The biggest benefit for Torch Deploy here is you don't need to make any modifications to your model. It runs exactly as it was written, so you can take the training model and turn it into the production side. So it's much faster to take it sort of from a research to production environment. And it also doesn't require any tracing or scripting. So for much more complex models, you can just kind of keep it in the eager mode Python. And if you have performance, you can always go in later and use some other techniques to optimize on that. Torch Deploy also has a shared backend, so all of the interpreters and the parent process are all sharing the same libtorch backend. So you don't need any extra copies of your model. The memory is shared between all of the processes, or well, all of the interpreters. And you can pass back and forth with 0 copies because it's all just a pointer to the underlying data. Plus, there's no process boundaries here, so you don't need to deal with Python multiprocessing or multiple processes. And you can kind of manage and monitor your inference job just in a single process. So you can use a lot of standard server monitoring tools and that kind of thing. So here's a kind of an overview of what this all looks like when you're actually running this in your system. There's a couple of different colored sections here. The white section is going to be just your code, basically. So your C++ binary, and that's where the interpreter manager lives. In purple is libtorch. So this is actually where everything executes. So this is where the tensors, kernels, and operators all live. And this supports all of the backends that PyTorch supports. In yellow and red, you actually have the sub-interpreters here. So this actually includes an entire copy of the Python interpreter, so libpython, and this is also where your model code will be running. The key bit for Torch deploy is Torch is actually split into two different pieces here. So libtorch has all of the C++ backend and all of the real heavy lifting, and then there is basically the sort of front end to this, which is the libtorch Python library, which is all of the Python specific bits. So within each interpreter, we can just load a single copy, or we can load a copy of the libtorch Python for each of the interpreters, as well as any Python C extensions, but then you have the shared backend. So this lets you actually have these independent Python interpreters. One of the big new features of the Torch deploy beta is you can now actually load from just a standard Python path, standard Python environment, like this is virtual env or conda. And to do this, we had to do sort of a bunch of work to make it so we can load arbitrary C extensions that you can just kind of pip install at runtime. So this view on the right here is kind of a simplified version of what sort of the memory space is going to look like this. So you have your main program, which is just loaded, and then you would be dynamically loading libtorch, which is shared between everything. And with deploy, to do this all, we basically play some tricks with how symbols work. So with libtorch, since we want that to be available everywhere, we can load that using basically a global namespace, so the symbols are loaded in everywhere. And then for the individual sub-interpreters, we can use a local namespace. So those symbols are only available to that one particular interpreter. To actually support arbitrary C extensions, you need to be able to actually still link that against the Python interpreter. So all the, the Python C extension can talk to just that specific Python interpreter and not all of them. So we actually had to implement a custom linker that can basically do all of this symbol resolution in a much more fine-grained control. So you can actually have these completely separate independent interpreters, so there's no global variables, and you can avoid the Python global interpreter lock. So yeah, we're now in beta. If you want to find out more about this, there's documentation on the website, as well as on GitHub. But yeah, we hope you check it out and send us some feedback. Thank you.
Hi, I'm Ankita, and I'm a software engineer at Meta. And today I'll give an overview of the Torch multimodal library that we released recently. So let's start with a quick refresher on multimodality. Very simply put, any task that needs to reason over or handle different types of input or output, be it text, video, images, or audio, can be categorized as a multimodal task. A popular one from research is visual question answering. So given an image and a question, the task is to predict the correct answer. Now it's critical to incorporate the understanding of the data from different modalities to be able to get to the right answer. So in this case, the image signals are critical for understanding if the color of the sky is red or blue. There are other popular tasks like being able to retrieve relevant images or videos given an input text, or more recently, being able to generate images conditioned on an input text. And of course, multimodality is not just limited to research, it's heavily used in practical applications as well. So being able to understand the content from video or posts is a critical part of recommending relevant items to a user on social media, and that's inherently a multimodal problem. So is the task of understanding if the content is harmful or offensive to the user. And we also have applications like self-driving cars, where you need to be able to combine the sensor data with the visual data to get a holistic understanding of the state of the vehicle. So with the aim of making the lives of ML researchers and practitioners working in the field of multimodal AI easier, we are introducing Torch Multimodal. This is essentially a PyTorch-based library to accelerate and enable innovation in multimodal AI. So let's take a look at the core principles that we focused on when we started building out this library. So firstly, modularity, where we offer modular building blocks that can be imported and used out of the box. So for example, multimodal models often have unimodal encoders and fusion modules that users can choose to use out of the box independently in their code so that they can mix and match with other components as well. Next is interoperability. So we want to accelerate exploration and reduce duplications. So we provide components that are interoperable and composable with components from other parts of the ecosystem. For instance, you should be able to swap out a standard text encoder, which is part of a multimodal model, with a component from another library or maybe even your custom encoder. And finally, extensibility. It's very critical for the user to be able to write their custom components by extending the standard ones from our library. So for example, you might want to import just the core model so that you can add your own task-specific layers and fine-tune it on a custom task instead of the one that the model was pre-trained on. So today, the key offerings from our libraries include the common low-level building blocks. These are essentially Lego pieces that are useful if you want to build a model from scratch. Then we have the end-to-end models, which are state-of-the-art. So you could import them and instantiate them for reproducing results from academia or for experimenting with your own use case. And we also have a repository of example scripts that can act as a starting point if you're a researcher looking to write your own training pipeline. And these also demonstrate very common techniques like multitask learning, zero-shot evaluation, and integration with other PyTorch distributed APIs. So to cover a few example offerings that we have, for building blocks, we have vector quantized variational autoencoder, which helps in learning the discrete latent representation for your data and forms the visual tokenization layer for a lot of the generative models today. There is also the cross-modal contrastive loss, which can be plugged into any use case and is also used by several examples in our library. Which also brings me to CLIP, which is an end-to-end model, which is image-text model that was pre-trained using the contrastive loss. And we also have MDETR, which is essentially a text extension of the popular object detection algorithm DETR. For example scripts, we added omnivore pre-training. Omnivore was work done in Facebook AI research, where a single visual encoder multitasks to learn image, video, and 3D representations. And finally, we also have another foundation multimodal model flavor, which I will talk about soon. All right, now let's dive deeper into how you can train CLIP, which uses aligned image and text data for cross-modal learning. So the components that you need from Torch multimodal are the specific transform, the model, and the loss. So the transform handles all of the pre-processing, so your text tokenization and image resizing, et cetera. And you can use any image text data set and set the transform on that. Then you need to instantiate the model. So here we are using the CLIP VIT L14 default configurations, but you could also choose to instantiate your model with your own parameters by using the raw model class. And finally, you hook up the contrastive loss, which also has a learnable temperature parameter as part of it. And then you just sort of put all of the components together into your training loop like any other model. Next, we go over how you could use a pre-trained model from our library for your task. So here we are using Flavor, which is a vision language foundation model. It was essentially pre-trained by multitasking on both unimodal and multimodal data with various supervised and unsupervised text, vision, and multimodal objectives like image text matching, contrastive learning, and mass language modeling. And here we have a demo video.
I'm going to walk through how we can use the pre-trained Flavor model for a unimodal task, which is image classification. We treat image classification as a case of zero-shot eval for the model. Firstly, we need the transforms for pre-processing and converting raw data into tensors. We use the flavor image transform out of the box, and for text, we use the BERT text tokenizer, which was used by the flavor text encoder. Next thing we need is the model. Here we use the core flavor model and set pre-trained as true, which loads the pre-trained weights. With these three elements instantiated, let's write a small function that takes in the model, image, and the set of all possible labels and predicts the label with highest probability. Since we are doing zero-shot eval, no training is involved, so we set the model to eval mode and do everything in no-grad settings. The image tensor comes from image transform, and the labels get tokenized and tensorized through the text transform. The encode image and encode text APIs on the model do the forward pass through the respective encoders and return the CLS token embeddings after being passed through the projection layers. We get the similarity scores of the image with each possible label by taking the dot product. And finally, we do a softmax to get a probability distribution over the labels. So here I have a picture of a dog that I want to classify. Since Flavor has a text encoder which can work with any natural language input, the label set can be anything. So here we see the model can predict the correct label from dog, cat, and house. But we can also change the label set to be something completely different, and the model is still able to predict the correct phrase, which is picture of a pet in this case. All right. Now let's see how we can use Flavor for a multimodal task, which is visual question answering. This time we fine-tune the model on the text VQA dataset, which we load first from Hugging Face. So the input is an image and a question, and the model has to predict the correct answer. In this case, the question is about the airline in the picture. We treat VQA as a classification task where the answer is predicted from fixed set of answer vocab that we build here. For transforms, we use the same text and image transform that we used in the zero-shot case, but we also add logic to convert the answers to tensors by looking up from the answer vocab. We set these transforms on the dataset. Then we get to the model. In this case, we use the Flavor variant for classification, which is essentially the core model that we used in the zero-shot case, but with an MLP classifier head added to it. Again, we set pre-trained to true because we want to fine-tune the weights. We also need to give the output dimension for the MLP or the number of classes as an input. For the model forward, we pass the text, image, and labels. This does the forward pass on respective unimodal encoders before fusing the unimodal embeddings by passing through the multimodal encoder. The CLS token embedding from the multimodal encoder is passed through the MLP classifier to give the final logits. The model also computes the cross-entropy loss from the logits and labels. So all you have to do now is to hook up this model to a simple training loop to fine-tune. So here I just covered some examples of how to use a model from Torch Multimodal for different use cases. You can also hook up Flavor to other tasks like text classification or use other models from our library for fine-tuning on VQA. Please visit our GitHub repo for such detailed examples. Thank you.
Okay. So we're just getting started. We've just done the beta release for our library, and we also have a bunch of exciting things on our upcoming roadmap. So firstly, we aim to solidify the support for the existing modalities like vision and text by adding more diverse models for them and making our API stable. At the same time, we want to increase the set of supported modalities so that we can cater to different parts of the multimodal community. So we are looking at adding things like audio and sensor data support. Secondly, with semi and self-supervised learning becoming very popular with research work like MAEs, we think SSL is going to be very important. So adding SSL primitives which work in multimodal settings, which can just be plug and play, is also something we are looking forward to. And of course, with the recent breakthroughs in the space of multimodal AI, we hope to add both building blocks as well as end-to-end components for tasks like multimodal summarization or text-to-image creation. So please check out our GitHub repo as well as some of the blogs and tutorials that we published recently to learn more about our library. And that's all I have. Thank you.
Hello everyone, my name is Vincent and I'm a developer for TorchRL, the reinforcement learning and control library for PyTorch. So when we started this effort of developing TorchRL, we had a look at the existing ecosystem of RL libraries that were using PyTorch. And what we realized is that some of them were heavily focused on things like production or some subfield of RL like model-based and things like that. We also acknowledge the fact that some libraries were absolutely great and used by a very wide community, but they were developed by people that had left the field and were left unmaintained. So we saw that as an opportunity for us to come up with something new with a consistent effort in developing an RL library that were using PyTorch with the that was up to date on the latest features of the library, and also a library where users would be able basically to escalate the issues that they were encountering in RL to PyTorch core and solve those issues in the core library. So the breadth that we wanted to cover was basically everything that was from newcomers to skilled RL researchers, but also everything that was from running baselines to developing new algorithms with the library, which is not an easy task. The first thing that I was told when I started working on this is that people wanted a library and not a framework. So there are many ways to interpret that sentence, but one thing that immediately came to mind was that people wanted to have a library that was very modular, with standalone components that you could basically pick without using the whole stack of primitives that the library was providing, but also components that you could easily swap in the algorithms you were developing. Also a library where the syntax would be totally unsurprising to RL practitioners, because sometimes what you can see is that people have renamed something into something else to suit the purpose of their library. And also we wanted to have an extended functionality, so to privilege breadth over depth, and a library entirely written in Python or almost entirely written in Python such that it was easy to hack for practitioners. What we didn't want is to have a library that was just a collection of algorithms, or just a library that was an extension of Gym, like many libraries I think are, in the sense that they provide you something on top of Gym to basically train our algorithms. Because we wanted to satisfy also users that were not using Gym, that were using other simulators, or no simulators at all. We try to have a core dependency on PyTorch and PyTorch only, and we support many other libraries such as Gym or GM Control or Habitat or Jumanji or Brax or whatever. We really try to integrate all of these into a unified API such that users can easily swap from one simulator to the other. We try to focus on two main pillars. The first one is efficiency, and that goes along the line of everything we've talked about so far with PyTorch core, but also very specific modules that are dedicated to RL, such as an efficient replay buffer that can work in distributed settings, vectorized environment transforms, or advantage computations and things like that. We also wanted, as I've said before, to focus on modularity. So to have generic module classes with very few level of abstractions, environments, modules, models, and basically all those little components that you can play around and put together into a unified algorithm. To cover spaces that were from model-based RL to model-free RL, on policy, off policy, offline, online, basically try to cover as much of the RL space as you can from the beginning. So modularity, in our opinion, comes in two flavors. The first is that you would like to be able to swap components with each other, and the second one is that you would like basically to be able to adopt one single component without adopting the whole library. the first thing to note is that reinforcement learning is not about the media, such as in vision you have images, in text you have text, etc. But RL is about the algorithm. It's basically about how you're going to have a policy that plays with the environment to collect data, what are you going to do with this data when you pass it through your loss function, etc. So it's really about the interaction of all those pieces together rather than the media that you're trying to work on. And it's very difficult to come up with a unified API because, for instance, if you think about a policy, so a policy in RL is something that usually reads an observation and outputs an action. But sometimes your policy is a little bit more complex. It's going to read an observation and, for instance, a recurrent neural network state and output an action and the next state. And also, sometimes your policy is going to return something else than an action. For instance, an action and the probability of that action. So first, you have to consider that your policy is something that can be really different from algorithm to algorithm. But also, your policy has to be sort of multimodal in the sense that you need to execute it in training or evaluation mode, exploitation versus exploration, and all these kind of things. So basically, you have a policy that can behave in very different ways, and also that should be able to digest very different kinds of information. So this is a rather loaded slide, but basically the core idea of the solution we found to those problems was something that we call TensorDict. And TensorDict is basically sort of a data carrier for TorchRL. So all the components, almost all of the components in TorchRL read and write TensorDict, and that's basically the only thing that you need to buy once you start using the library. And it makes our life much easier because now you can have, for instance, an environment that is not reading a specific number of features like an action and an RNN state or whatever to output a different number of outputs. You're sure that your environment is always going to read a TensorDict and output a new TensorDict. Same thing with the policy. The policy is just going to write a TensorDict and output a TensorDict. The replay buffer is going to read and write this TensorDict. So basically a TensorDict, what is it? It's just a dictionary with extra tensor features that allow it to basically execute shape operations such as reshape, view, permute, and things like that. You can stack TensorDicts very easily together. You can unbind them, split them, do many things that you would do basically with a tensor, but you can execute them on a dictionary that contains only tensors. So first, TensorDict was part of TorchRL, and our early users were pointing to the fact that it was something that they would rather see as an independent library because they were hoping to use that in many other projects like self-supervised learning and things like that. So we open sourced TensorDict as a separate library under PyTorch Labs, and you can check it out. It's out there, and yeah. Okay. Now, the second component of modularity that I was talking about is the fact that you would like to have those modules and be able to use just one module without using the whole stack of components of TorchRL. And the way we go about that is that we try to basically foresee, before users ask for it, to have those modules that are easily used across, let's say, experience of the users. So for instance, here I have a loss that is a DQN loss. And this DQN loss, you can use it with a TensorDict if you want to use all the features that it provides, but also a basic user that has very little experience in RL could just use it with regular tensors. And this module will take care of creating all the TensorDicts, etc., under the hood for you to execute the inner operations. Same thing goes with replay buffers that are highly optimized for TensorDicts, but basic users that don't want to benefit from all those features, but just want the basic usage of the replay buffer can use it with tensors or even other Python objects. I will quickly skim over the features that TorchRL is already providing. So we have an environment API that covers GIM, DeepMind Control, Habitat, Brax, and other libraries. And on top of those environments, you can use transforms, and those transforms can be used on batch data, which makes them much faster, but also be used on device. We have vectorized environments, and that can be executed on multiple processes and also on distributed settings. We provide modules that have like common architectures that are used in RL and things like that. For data collection, we have data collectors that work in a synchronous or asynchronous manner on a single machine or multiple nodes. We have a good rebuffer API that can store data on physical storage and allows you to basically store terabytes of data when you're doing your experiments. We have some objectives like SAC, DDPG, PPO, and many others that are ready to use out of the box. We have a trainer API that provides also a checkpointing mechanism such that you can basically be full tolerant or have like restart your training once you have stopped it. We integrate various loggers such as 1DB, TensorBoard, and basic CSV logging, things like that. We have various utilities. And finally, one thing I would like to point is that we have a good set of examples and tutorials in the library, and we have quite a decent documentation about how the library should be used. So feel free to check it out. I have the two links here for TorchRL and TensorDict. So yeah, thank you.
Hi, everyone. My name is Raziel. And so far, you've heard about all the cool technology that we've been building and a lot of references to Python and server. But next, I will give you an update on PyTorch support for on-device machine learning, aka mobile. First, I'll give a quick recap on why on-device ML matters. Then I'll talk about how we see the space growing and evolving, the changing needs. Then I will cover, is this well supported so far, and how we're thinking about evolving PyTorch to support this space better. Okay, on-device ML is important because it provides some capabilities that server does not have, right? Perhaps an obvious one is offline. So that means that applications and products do not rely on a connection. So there is more resilience to those type of connectivity issues. Furthermore, this can give a level of efficiency versus having a direct connection to a server. So that translates in being able to have long-running AI interactions. For example, this is how assistant wake words typically work. This efficiency also translates into reduced latency, so it enables products that really need a lot of interactivity. Also, by having the machine learning running on device, you can take advantage of the data that is available on these devices to do this type of multimodal tasks. And last but not least is a privacy-enhancing technology because it allows the data to remain on device. So if you think about it, on-device machine learning allows new type of products that will not be possible if you had reliance on server-side execution. In PyTorch, we've been supporting on-device machine learning for some time now. We released PyTorch Mobile 3 years ago. Since then, we've been doing constant performance upgrades. And lastly, we push a significant binary size reduction and on the runtime. We use it very successfully at Meta. It's used across many applications like Messenger, Facebook, Instagram, Spark AR, for example. This is about like 50 models across these applications that daily perform about 70 billion inferences. However, the future for on-device ML is rapidly changing. I think one of a reflection of the success of this space is how fast and how much growth we've seen. And just to give a sense of the scale, an estimate of the value of AI in general is already measured in the trillions. And on the other hand, the investment on edge computing is very large already and growing. And we are not talking just about mobile phones and apps. We're talking a wide variety of products on a wide variety of devices and applications. This, however, means a growing set of challenges. We obviously have more software platforms. It's not just about Android and iOS. As you saw on the previous slide, there is a lot more devices. This translates in hardware heterogeneity. that the framework needs to support optimization and targeting for example, like doing mixed compute execution, where you want a model or program to be able to partially execute across different compute units, for example, running partially on a DSP, partially on an NPU. There is more metrics to optimize. It's not just about performance. For example, power consumption is a very important one for edge computing. And we've seen also an increased model variety and complexity. And also very important and interesting is the number and variety of experts involved has grown. And this process of bringing research to production has become much more interactive. How is the future well supported? Well, if you see the solutions out there, a lot of them have been focused on creating narrow solutions. And this forces users into abstractions and semantics that were not those that they used when they created the program in the first place, when they authored the model. And then now they have to grasp with another set of solutions. This has some unfortunate consequences. It increases friction because developers now need to think about what is the programming model, the programming paradigm that I need to follow in order to author a program, a model that can successfully be deployed across different devices. And it also fragments the ecosystem. For users, because they have to learn a different framework, a lot of the concepts may be similar, but they're fundamentally different. And for framework developers, there is a lot more surface to cover. In PyTorch, we've always been very adamant about keeping semantic consistency across the stack, but we need to scale it up to this growing set of devices. Our hypothesis is that we need to power an ecosystem where both narrow solutions, but also general ones, can be built on a common platform within PyTorch. So with that in mind, we're building a new software stack for on-device machine learning that is anchored in 4 principles. The first one is we want to maintain PyTorch authoring semantics. Basically, we want to extract a representation that is non-Pythonic, that is easier to lower and optimize. But we want to make this process as easy and clear so the programming model is easy and intuitive so users know what will be possible to be captured and what won't. You saw a previous talk about export, so this is the other key thing. We want to preserve consistency across all the PyTorch stack, and we are doing it by reusing all the components that you heard today. The second principle is we want to embrace user extensibility. So this means that we want to allow users to customize a program, and we want to do it via well-defined entry points. And not only that, but these entry points need to have a clear and verifiable contract, because we want to make sure that the semantics of the program are maintained even as optimizations happen through the stack in order to target a particular device. Now, we obviously want to support out-of-the-box components right away. One of them, very important, is a portable, small, efficient runtime that can be deployed across a wide variety of devices, including microcontrollers. And obviously, kernel libraries to execute these programs, with some optimized for common hardware. And the same goes for supporting compiler-based backends. That is typically the way to delegate execution to accelerators. The important part is that we want to build these on the same entry points that anybody can use to develop their own solutions. And also enabled by these previous 3 principles, we will offer APIs and tools to improve developer productivity. So a developer SDK that allows you to do profiling, debugging. But not only that, we're also thinking about how do we do this and provide this information and these tools that is actionable. And one way to do this is we want to be able to bring this information as close as possible to the author program. So if you see a profile information debugging, you want to see it not in another abstraction, but in terms of the code that you author in the first place. And we will see this new ecosystem with documentation, tutorials, examples. Now, this is not built overnight. We're working hard to get this ready, so you can expect a better release of this new software stack late summer next year. So please stay tuned. Thank you.
What an incredible morning we've had. So I want one more round of applause maybe for all of our speakers that came here today. So we're heading into the lunch break. There's food waiting in the back. Reminder also to follow the conversation today with the hashtag PyTorch Conference. You can also find the QR codes posted around for the rest of the agenda and the speaker bios. So there'll be posters and breakout session starting at 1 p.m. There'll also be office hours in the back there near these little tables around the posters where PyTorch technical leads will be there to answer any of the questions you have if you want to try out 2.0. So enjoy lunch. Thank you.
So hi everyone, I'm Clément Chadebec, and today I'm going to present you my Python library, Pythae, that unifies generative autoencoders implementations in PyTorch. So well, first, what is a generative autoencoder? Well, you may know autoencoders. They're a class of deep learning models that try to map complex input data into a much lower dimensional space called the latent space. And so the main idea is to learn a latent representation, so a lower dimensional representation of those input data. Well, generative autoencoders are basically a subclass of autoencoders that are made generative using a sampling distribution. And that sampling distribution can be used either during training, as for the variational autoencoders, or after training, as for the regularized autoencoders. But well, why did we create Pythae? So well, first, as you may know, existing implementations of the original papers may be difficult to adapt to other use cases, be in different frameworks or no longer maintained. And so Pythae has a brick-like structure that allows users to use different models with different sampling techniques, neural network architectures, and training schemes on their own data pretty easily. Second, Pythae provides you with a reproducible research environment. So most of the models that are implemented in Pythae were actually able to reproduce the original paper results. Finally, the code was thought to be as flexible as possible and as accessible as possible. And so we'll find on the GitHub an online documentation, and the library is also illustrated through different tutorials. So this is the structure of the code. So basically, this is a really brick-like structure. So on the left, you have the models that you can choose, and you can define your encoder and decoder architecture. In the middle, you've got the trainers. So the trainers are also thought to be as flexible as possible because you can define your optimizers, schedulers, and callbacks. And on the right, you've got the samplers that you can choose to generate data from a trained generative autoencoder. And you may find also other features such as experiment monitoring tools, such as 1DB, CommentML, and MLflow that has been integrated to Pythae. And you can also share your trained model through the Hugging Face hub. So now let's have a look to the API of the code. So let's say that I want to train a variation autoencoder with Pythae on my own data. So the first thing that I need to do is to define my architecture. So it can be done pretty easily using the base encoder and base decoder class. So I import them and I create two other classes, my encoder and my decoder, where basically I specify my neural network architecture. Then I instantiate those classes and I can launch a training. To launch a training, I need different things. So the first thing that I need is to define a training configuration. This is basically where I specify the number of epoch, the learning rate, and the batch size that I want to use. Then I define a model configuration, here a VA configuration, and I can instantiate my VA. So to instantiate it, I pass the model configuration as argument, but I also pass the encoder and decoder that I've just built before. Then I can instantiate a training pipeline with the training configuration and the model, and I can launch the training pipeline on my own data. In the end, once the model is trained, I can reload it using the AutoModel class pretty easily. And then I can use whatever sampler I like to generate new data from that trained model. So in that example, this is a Gaussian mixture sampler. So basically, all you have to do is to define your sampling configuration, and you can instantiate a generation pipeline, and you can launch a pipeline by specifying the number of samples that you want to generate. So here you've got the list of the models that are actually implemented in Pythae. So there are 25 models that are currently implemented in the library, and most of which were able to reproduce the original results provided in the papers. Finally, those are different resources that you may need to get your hands on the code. So basically, the code is available in GitHub at that link. You will also find an online documentation. The library is available in PyPy and can be installed with that command line. And I want to stress that that library is also open to contributors. So if you want to contribute to a new model, a new sampler, or simply fix a bug, I would be very happy to help you in that direction. So thank you very much for your attention. I would be very happy to answer any of your questions if you have any.
Hi, my name is Jimmy Whitaker. I'm Chief Scientist of AI at Pachyderm, and today we're going to talk about automating PyTorch by using TorchX to make data-centric machine learning workflows. We're first going to talk about why iteration is important for successfully applying machine learning. Then we're going to go on to introduce some tools that have made iteration in production much more reliable in the PyTorch community. And finally, we'll talk about how these components can be used together. So let's get started. First, let's talk about iteration. When it comes to applying machine learning in practice, iteration is the key to success. We see this all the time when we're developing software. We focus on the development of our application to get to an initial release, but once we've reached this milestone, it's just the beginning. We've likely learned a lot in the process of building our application, so we then focus on how to improve it or expand it by adding new features, applying bug fixes, improving performance, and so on. The same is true in machine learning. Once we train a model and put it into production, this is only the beginning. As soon as our model begins to touch real-world data, there will be new requirements to improve the model. The first release is just the first of many. Setting ourselves up for iteration is how we apply machine learning in the real world. But to iterate quickly on machine learning models, we need to be able to track changes, prioritize stability and reproducibility, and support collaboration all at the same time. Furthermore, we have a new life cycle that we need to consider, the data life cycle. In machine learning, data is the new source code, and this means that we need to be versioning, testing, and treating it in a way that's similar to how we develop code for software. Together, the code and data lifecycles are both crucial for iteration on machine learning applications, and this is what we aim to solve with our integration. For the code lifecycle side, TorchX proves itself to be quite useful for productionizing PyTorch applications, while Pachyderm is hugely valuable for iterative development within the data lifecycle and connecting with TorchX. So let's take a deeper look at each of these tools. Let's first talk about TorchX. TorchX is an SDK for quickly building and deploying machine learning applications with various technologies. It allows users to create containerized definitions for PyTorch applications, making them reproducible and scalable. This library has a variety of benefits. It provides a framework for how to design your applications and execute it in a variety of environments, such as Docker or Kubernetes and even others, enabling you to iterate quickly and reduce the amount of effort required to productionize your PyTorch applications. Data, however, typically remains one of the untracked variables in machine learning development. Paths to object storage can be unreliable, and versioning of large data sets can be really complex, leading to gaps in reproducibility and agility. And this is where platforms like Pachyderm come in. Pachyderm is a system built specifically to version data and trigger pipelines whenever data changes. In a way, Pachyderm looks like a CI/CD system for data. Whenever the data changes, it kicks off runs for connected pipelines. Built on Kubernetes and object storage, Pachyderm can be used to scalably version any type of data set, no matter the data type, and trigger pipelines whenever a change is detected. Additionally, with everything else in the system being version controlled, such as your pipelines and your data, you can benefit from having a full lineage and history of everything that's happened. For example, showing what changes to an input data set or training code produced in a particular model can be really, really useful when you're iterating quickly to produce machine learning models and upgrade them. When we combine PyTorch and TorchX, we end up with an incredibly powerful platform that allows us to build out automated data-driven workflows that have end-to-end lineage and reproducibility. We can do this by simply creating Pachyderm pipelines that have TorchX entry points. Pachyderm, which is built on Kubernetes, uses containers for its pipelines. And this means that we can run any application that can be put into a container, such as native Python, PyTorch, or even Java and Scala. And this also means that we can have a Pachyderm pipeline schedule TorchX applications to run whenever a Pachyderm pipeline is triggered. Practically speaking, this means that we can set up training pipelines in Pachyderm to automatically trigger a TorchX distributed training job whenever there are significant changes to our data set that's versioned in Pachyderm. Any models or other artifacts produced during the training job can then be put back into data repositories in Pachyderm, versioning them and maintaining a full reproducible history of everything that's happened in the system. Together, TorchX and Pachyderm combine to provide a foundational platform for combining the code and data lifecycles. Version data repositories in Pachyderm can track all of the changes to our data. These changes can in turn trigger pipelines that then automate the reproducible workflows that are scheduled with TorchX. Furthermore, it's all built on Kubernetes and object storage, ensuring that it can scale up to any task. Building data versioning and reproducibility into the core of our machine learning workflow is foundational to applying machine learning in practice. Without it, we cannot hope to improve collaboration, reliability, or agility. And TorchX and Pachyderm pair nicely to provide the foundational elements of applied machine learning. Make sure to check out our examples and documentation for more information on how these two work together. Thanks.
Hi everyone, I'm Minjin and I'm an AI frameworks engineer at Intel. In this session, I will talk about scaling inference on CPUs with TorchServe. There are 5 main topics for today's agenda. First, I will give an overview on TorchServe. Second, on CPU performance tuning principles for getting a strong out-of-box CPU performance. Third, on Intel extension for PyTorch. Fourth, on TorchServe with Intel extension for PyTorch. And finally, we'll conclude with a summary. Let's get started. What is TorchServe? TorchServe is a performant, flexible, and easy-to-use tool for model serving and scaling PyTorch models in production for inference. Model serving is the process of integrating trained deep learning models into a larger system in production. TorchServe allows users to easily deploy their trained deep learning models. TorchServe provides support for both PyTorch eager mode models as well as Torch scripted models. TorchServe provides a number of default model handlers for handling the model initialization, pre-process, inference, and post-processing steps for various domains, including image classification, image segmentation, object detection, and text classification. Users can also write their own custom handlers for handling their own custom models. Now, let's discuss on general CPU performance tuning principles to boost out-of-box TorchServe performance. There are two main principles that I will discuss. First, avoiding logical cores for deep learning workloads generally improve performance. The majority of time in deep learning inference or training is spent on millions of repeated operations of GEM, general matrix multiply, and most GEM operators benefit from using non-hyperthreading. Therefore, we generally recommend avoiding logical cores by setting thread affinity to physical cores. Secondly, multi-socket systems have non-uniform memory access NUMA. If a process is not NUMA aware, slow remote memory is frequently accessed when threads migrate cross-socket. We address this problem by setting thread affinity to a specific socket. Knowing these principles in mind, proper CPU runtime configuration can significantly boost out-of-box performance. Before we discuss, let's first note how users can obtain their CPU information. CPU information can be retrieved with lscpu command on Linux. The following is an example of lscpu execution. There are two sockets, and each socket has 28 physical cores. Since hyperthreading is enabled, each core can run 2 threads. In other words, each socket has another 28 logical cores. Therefore, there are 112 CPU cores on service. The first principle is to avoid logical cores. GEM run a fuse multiply add or dot product execution unit shared by hyperthreading cores. With hyperthreading enabled, OpenMP threads will contend for the same GEM execution units. When 2 logical threads run GEM at the same time, they will be sharing the same core resources, causing front-end bound, such that the overhead from this front-end bound is greater than the gain from running both logical threads at the same time. Instead, if we use 1 thread per physical core, we avoid this type of contention. Notice on the left, we avoid logical cores by setting the thread affinity to physical cores 0 through 55. Finally, we recommend binding a process to a specific socket to avoid slow remote memory access. Each socket has its own local memory, and sockets are connected to each other, which allows each socket to access the local memory of another socket called remote memory. However, it's better to utilize local memory and to avoid remote memory access, which can be around 2x slower. Notice on the left, we pin threads to physical cores on the first socket, 0 through 27, to maintain the locality of memory access. Let's apply these principles to deploying ResNet 50 with TorchServe. On top is out-of-box TorchServe single worker inference without core pinning. When the number of threads is not manually set, PyTorch by default sets the number of threads to the number of physical cores, 56 in this case. We notice one main worker thread is launched, then it launches 56 threads on all cores including logical cores. Furthermore, as we did not pin threads to cores of a specific socket, the operating system periodically schedules threads on cores located on different sockets. Comparing local versus remote memory access over time, we can verify remote memory accesses, which results in suboptimal performance. On bottom is the same setting but with core pinning. We observe that one main worker thread is launched, then it launches threads on all physical cores on the first NUMA node, 0 through 27, and we can verify that now almost all memory accesses are local accesses. Now we have a look at multi-worker inference. On top is out-of-box TorchServe multi-worker inference with 4 workers without core pinning. We notice each of the 4 main worker threads launches 56 threads, launching a total of 56 times 4 threads, which is twice the total number of cores. Therefore, cores are guaranteed to be heavily overlapped with high logical core utilization, multiple workers using multiple cores at the same time. On bottom is the same setting but with core pinning. To avoid core overlap amongst the workers, we can equally distribute the physical cores to workers and bind them to each worker. In this case, bind worker 0 to cores 0 through 13, worker 1 to cores 14 to 27, and so on. Doing so makes each worker use its assigned resources as highly efficiently as possible and minimize resource conflict amongst the workers. We've discussed general principles to CPU configurations. Now I will give an overview on Intel extension for PyTorch. Intel extension for PyTorch is a Python package to extend PyTorch with up-to-date feature optimizations for extra performance boosts on Intel hardware. There are three major optimization techniques of Intel extension for PyTorch. They include operators, graph, and runtime performance optimizations. At the operator level include vectorization and parallelization to maximize the CPU efficiency, low-precision data types including bflow16 and int8, data layout optimization for better cache locality. At the graph level include graph optimization. While PyTorch by default runs in eager mode, Torch scripted models can convert the topology into graph to apply constant folding and operator fusion into the graph for reduced compute and better cache locality. At runtime, Intel extension for PyTorch provides runtime extension to accelerate even further, including fine-grained thread affinity control, launcher for automatic setting of the optimal CPU configuration. Eventually, all targeted features and optimizations are targeted to upstream stock PyTorch. Compared to stock PyTorch, Intel extension for PyTorch optimizations are more aggressive at a broader scope. Intel extension for PyTorch provides simple front-end Python APIs for users to easily optimize their model to get performance optimizations. For FE32 and bflow16, users simply need to import Intel extension for PyTorch package in and apply the IPEX.optimize against their model object to apply optimizations to their model. As well as for int8, Intel extension for PyTorch int8 quantization API has the same look and feel as that of PyTorch. Now we will introduce TorchServe with Intel extension for PyTorch. Intel extension for PyTorch has already been integrated into TorchServe to give out-of-box performance boosts with an ease-of-use API. Simply add a few lines and config.properties, which is a file that TorchServe uses to store configurations. Set IPEX enable to true to enable Intel extension for PyTorch. Set CPU launcher enable to true to enable launcher. Launcher automates setting the most optimal CPU configuration. User can also specify launcher arguments to CPU launcher args. In this example, we specify node ID 0 to use the physical cores of the first NUMA node, applying the CPU tuning principles that we've discussed. Evaluated the performance boost of TorchServe with Intel extension for PyTorch on ResNet 50 and BERT. We observe 1.21x throughput speedup for BERT and 2.43x throughput speedup for ResNet 50 with FE32 inference, and 2.2x throughput speedup for BERT and 7.71x throughput speedup for ResNet 50 with int8 inference. Now that we've discussed Intel extension for PyTorch with TorchServe, we'll conclude with a summary. In this session, we have walked through some general CPU performance tuning principles to boost out-of-box CPU performance. We have also introduced Intel extension for PyTorch and its integration into TorchServe with an ease-of-use API, showcasing up to 7.71x throughput speedup for ResNet 50 and 2.2x throughput speedup for BERT. And finally, please check our GitHub to TorchServe and Intel extension for PyTorch and related blogs that dive deep into today's topic.
Hi, I am Tal from Microsoft Elf ILDC, and this is Federated Multilingual Models for Medical Transcript Analysis. This work is used in a product that we are developing called Text Analytics for Elf. Text Analytics for Elf is a platform for understanding clinical texts. Among its features is named entity recognition. We recognize over 30 types of entities that are all relevant to the medical domain, such as treatment name, diagnosis, medication name, etc. On top of this, we also identify various relations, such as examination and examination results. We can attach time to the entity that the time refers to, etc. We also identify different type of assertions, such as negation. So, for example, if the diagnosis is negated, then instead of presenting to the client that the entity appeared, we also tag it as negative for better understanding of the clinical intention of the text. And finally, we also do entity linking. We link all the entities found to UMLS, so the clients can enjoy any structure information from those ontologies. So how do we do it? So behind the scenes, there's a large language model implemented in PyTorch, and it reads a lot of clinical text in different languages. But as everyone knows, clinical texts are private and protected and cannot be accessed by anyone. So what we do is a federated learning pipeline. First, each client provision is on a subscription with its own compute and its own data, and only the client compute can access his own data. And then we distribute a language model to all the clients where they train on their own data, update the central model, and once the central model is updated and aggregates all the different weights from all the clients, it can run evaluation and redistribute the model for another round of training. And this repeats till the model is converged. If you want to access some resources that we used for this work, you can first access the Azure ML pipeline for federated learning, where you can create federated learning pipelines on your own. You just have to implement the training step and the evaluation, and you can implement your own federated learning pipeline. We also used Flute, which is a platform for federated learning simulation. If you want to run simulation of your experiment and check its validity, you can do this over Flute, and then you can save all the overhead of slow communication between different subscription, etc., and just run a simulation over a single cluster. And finally, you can access Text Analytics for ELF for more information about our product. Thank you.
Hi, I'm Robin Lobel, creator of Torch Studio. Torch Studio is a graphical user interface for PyTorch, allowing all PyTorch interactions such as loading, formatting datasets, debugging, training models in a user-friendly way, removing most of the coding burden and getting instant visual feedback. It can work both as a standalone software or as an extension to your favorite IDE. If you don't already have one, Torch Studio will set up a Python and PyTorch environment for you. You're then ready to load your first dataset. As a basic example, we're going to load the MNIST dataset, composed of handwritten digits and their interpretation. It's as simple as selecting the Torch Vision datasets category, then the MNIST dataset, and clicking Load. Torch Studio will automatically download the dataset and show it to you. As inputs, we have pictures of handwritten digits, and as targets, we have the corresponding interpretation of those digits. For now, let's leave the default formatting as is, and let's run an optional analysis of the dataset by clicking Analyze. It will scan the whole dataset and break down its composition. As we can see, the dataset is well balanced. All 10 digits are almost equally represented, and the order in which they appear in the dataset is pretty random, so there's no need to reformat. Now that we've loaded the dataset, let's create a new model by clicking the plus sign at the top. This will create a new tab. Each tab represents a model. Torch Studio provides a model which can learn to classify pictures from this dataset. It's available in the Torch Studio Models category, and it's called NIST Classifier. This model comes from the PyTorch tutorials, and if needed, we could see and edit its source code by clicking Code at the top. But for now, let's just build it as is by clicking Build. This will display its graph representation, showing what nodes it contains, how they are connected to each other, and how tensor size changes from one node to the next. We feed it with monochromatic pictures at the top, with a resolution of 28 by 28 pixels, and at the end we get 10 possible values. For now, the model knows nothing about classification. That's why for any digit picture will show it, it can only say there is an equal chance it's any number. It's time to train it. Let's leave the default hyperparameters as is and click Train. If you didn't set up a remote training server, it will use local hardware to train it. In this case, the metal acceleration of my Mac. As training progresses, we can monitor loss and accuracy metrics on the right side of the screen. The most important one is the accuracy. As long as it keeps improving, it means the model is properly learning. And this is reflected in the predictions of the model. As we show it different digit pictures, including pictures from the validation datasets that it never saw before, it now properly predicts the correct interpretation. When the training completes, which is when it can no longer improve the accuracy further, we can export our trained model in different formats, as model weights, or as torch script or RNX file containing both the model and its weights. These models can then be reused as is in production, such as Python scripts, desktop applications, or web services. Now let's move on to a more advanced example, involving a custom project within an IDE, a remote training server, and exploring the hyperparameter space. To install IDE extensions and set up remote servers, click Settings in the Torch Studio menu. To add a remote server, click Add, give it a name, enter its address, username, and password or key file. It works with any server, on-site servers, cloud instances such as AWS, Azure, Google Cloud, and any operating system. If the server doesn't already have a Python or PyTorch environment, Torch Studio can remotely install and set it up for you. We'll then install the extension for the IDE, in this case Visual Studio Code. All we have to do is click Install VS Code extension. We can now close Torch Studio. Let's launch our IDE and load our Python project. This project contains a custom dataset and a custom model. Let's add a Torch Studio training to it by right-clicking on the project and clicking New Torch Studio Training. Then click on that new file to open Torch Studio. Let's drag our custom dataset from VS Code to Torch Studio and click Load. This is a dataset made of spectrograms. The goal is to teach a model how to remove reverb in an audio recording. To achieve this, we've prepared different audio recordings on which we've applied reverb, which will be our inputs. And the targets are the original audio samples without reverb. To speed up training during this demo, let's use only half of the dataset. Now that the dataset is loaded and formatted, let's create a tab for the model. Then drag and drop our model from VS Code to Torch Studio and build it. We can see its shape as a unit. Let's train it with the default hyperparameters by selecting a training device on our remote server and clicking Train. As the training for this model starts, let's duplicate this tab by clicking on the plus sign. This time we'll change the depth of this unit by changing its depth parameter and rebuild it. As you can see, its graph representation changed, reflecting the deeper layers and connections. Let's train this one too. As the training is already in progress on this remote device, it will wait for the previous training to finish before launching this one. Finally, let's make a third copy of this model, and this time let's change the loss function from mean square error to mean absolute error, and queue that training too. Now that we've explored the hyperparameter space for that model a bit, It's time to compare what parameters actually improve the training performances. Let's move to the dashboard at the top right corner. The dashboard shows you all the metrics and all the parameters differences from all your models at once, so that you can easily identify what makes a positive difference and what model performs the best. In this case, this combination seems to work best, producing the highest validation metric. So we'll switch to this tab and export the weights. The weights will be immediately available in our IDE project, and then all I need to do is create the model with the corresponding depth and load its training weight. It's then ready for inference in my Python project. I hope you enjoyed this presentation. If you'd like to know more about Torch Studio features, please visit torchstudio.ai for videos, tutorials, and more.
My name is Li Ning. I'm a senior software engineer in AWS. In this session, I will introduce TorchServe CPP backend. Today, I will cover these topics. First, introduce our team, answer why we build the CPP backend, what's the change in architecture, and then deep dive the CPP backend internal, give a demo and a benchmark result. TorchServe is an open source project jointly developed by AWS and Meta. These are members for CPP backend project. Why CPP backend? There's a high production demand for lower model loading latency, reducing GPU memory usage, improving GPU utilization concurrency, and even request embed TorchServe in edge device. However, it is difficult to support these requirements in Python backend due to Python language limitation. So we decided to build a CPP backend to better serve TorchServe community. Now let's see what's the change in TorchServe architecture introduced by the CPP backend. Left side picture is TorchServe original architecture. It is a Java frontend and a Python backend worker process. On the right side picture, we can see backend extended to support C++ worker process. Java frontend is not only able to connect with a Python worker process, but also able to connect with a CPP worker process. Let's deep dive CPP backend internal. As same as Python backend, CPP backend is divided into multiple layers. Top layer is socket to communicate with Java frontend. Second layer is service management, which is responsible for request response, encoding, decoding, and dispatching the requirements. Third layer is common backend API to support different machine learning plugins. By default, TorchServe provides TorchScript backend. The bottom layer is machine learning platform handler API for customer model loading, pre-processing, and inference. The bottom two layers are highly related to TorchServe users, as same as Python backend. I will explain them one by one. The common backend API layer defines 3 virtual functions for different machine learning platform to plug in. Function initialize is for machine learning platform initialization. Function load model internal is used to implement model loading in different machine learning platform. Function predict is used to implement prediction in different machine learning platform. TorchScript backend is the default CPP backend. As same as Python backend handler, CPP backend has default base handler implementation, but users can override it. Function initialize is is used for model initialization. Function load model is used for model loading. Function pre-post process is used for model pre- and post-processing. Function inference is used to call model to run prediction. CPP backend maintains the same behavior as Python backend to allow users to build a model MAR file by using model archival command. For example, users is able to use TorchScript base handler to build a model MAR file. User is also able to build a customer handler dynamic library and then wrap it in model MAR file by using model archival command. Finally, users are able to load model and run prediction by using same REST API or gRPC API as Python backend. Let's take a look at a demo. This is the CPP backend user menu page. To save time, I already installed the code. This is the CPP backend common API links. This is the TorchScript base handler API links. Let's see two use cases to build a model MAR file. First, I'm using TorchScript base handler to build a model MAR file and move the model MAR file into the model store. Second, I'm going to using customer handler dynamic library and wrap it into model MAR file. Now I'm moving the model MAR file into model store. Let's start the TorchServe. We can see the two models are loaded. And then we run the model inference. This is a model text classification by using script tokenizer benchmark result. The model size is about 1.9 gigabytes. The first picture shows model loading latency is reduced about 25%. The P90 and the P99 inference latency also reduced. When the batch size is 1, the P99 latency is reduced about 10%. With the batch size increasing, the gap between CPP and the Python backend is reduced. These are the GitHub links for TorchServe and the CPP backend. Please try and give us feedback. Thank you.
If you could please take your seats for our breakout sessions. They are about to begin. Once again, please take your seats for our breakout sessions.
Started? Take it away. Okay. Hi, y'all. I'm Nikita. I'm a developer advocate at Google and joined today by my teammate, Eric.
My name is Eric, Google Cloud AI engineer. We're excited to be here today.
Awesome. May I change the slide? Oh, shoot, the slides aren't showing. Can you guys? Oh, you can't see the slides. All right, sorry about that. Okay, so today we are going to give you an overview of how to do distributed training with PyTorch on Google Cloud using Vertex AI. There are a lot of different ways to do distributed training, so our goal today is to just kind of like give you an overview for a bunch of different ways that this might be possible. But before we do all of that, I always think it's useful to just kind of give us a little bit of context and step back and remind ourselves why we might use distributed training in the first place, why are we going to all this effort. So as we all know, when model training takes a few hours or a few days, it's pretty easy to iterate and experiment and try out new ideas. But when model training is taking like weeks or months, it really slows you down, becomes a lot harder to iterate and experiment. So using the right distributed training configuration can dramatically reduce training time, and shorter training time, of course, makes for faster iteration to reach your modeling goals. And who doesn't want that? However, unfortunately, distributed training does come with its own set of challenges. So first, you've got to make some kind of change to your PyTorch code, right? Maybe you're using like DDP. Are you doing some kind of model parallelism setup? Whatever you decide to do, there's some change that needs to happen at the PyTorch code level. But then, all of a sudden, you're like worrying about managing infrastructure and submitting jobs and clusters and dealing with fault tolerance, and then you have to optimize usage of your accelerators and deal with limited bandwidth between your nodes. So there's all this extra complexity that gets tacked on once we enter the realm of distributed training. So what we want to show you today is, at a high level, how you can leverage managed services on Google Cloud that will hopefully reduce the friction of running and operationalizing distributed training of your PyTorch models. And the focus is less on how to change your PyTorch code, but more on how to use these Google Cloud tools to run this code at scale. And the main tool we will use today is Vertex AI. This is Google Cloud's managed machine learning platform. There are a lot of different products to cover the whole kind of ML workflow, but our focus will really be on the training service today. And then at the end, Eric will talk a little bit about pipelines as well as our prediction service. So running a custom training job on Vertex AI is done with the use of containers. You'll package up your training code along with any dependencies that you need, and then you can specify your desired hardware configuration, and this includes adding GPUs or TPUs, both of which are available to you when you use PyTorch on Google Cloud. And then you'll submit a remote job to run on the training service, and you won't be worrying about provisioning or managing servers, nothing like that. However, there is an interactive debugging service if you want to SSH in, poke around while your training jobs are running. And then there are a couple of other tools that I won't get to talk about today, but I did want to mention. When you run custom training with Vertex AI, you can use the automated hyperparameter tuning service. You can integrate with managed TensorBoard, which will allow you to set up a TensorBoard instance to track your experiments. And then there is an experiment tracking service as well, all to help you discover the optimal model faster. Now, since this service works via containers, Vertex AI provides a set of pre-built training containers for PyTorch. These contain kind of common dependencies that you might be using in your training code. They're updated regularly. And if one of these containers meets your needs, so it has all the dependencies that you need, you can package up your code as a Python source distribution and then let Vertex manage the container for you. But if you want some like custom dependencies, you just want more control, then you can use a custom container, and that's what we will show you today. And we'll start by looking at GPU training on Vertex AI. So your Docker file for your custom image might look something like this. I'm actually using the pre-built training container here as my base image. We copy over our training code. It's probably defining our model, executing a training loop, that kind of thing. If you want to install any additional libraries, you can add that in here. And then we set up our entry point to invoke our trainer, and that'll run our training code. So once you have built your image, the main way you'll interact with the Vertex AI service is via the Python SDK. So you're going to create this thing called a custom container training job, kind of a mouthful, but it is exactly what it sounds like. It's a training job for a custom container. And you'll need to pass in the URI to where your container image is, either in Google Cloud Container Registry or Google Cloud Artifact Registry, which are two places to manage your containers. And then you can call run. And when you call the run method, you will specify the machine type for this job. You can specify any accelerators you want. And this is basically what it would look like to do single machine, single GPU training on Vertex. If we want to enter into the realm of distributed training, we can just bump up the accelerator count. Now it's set to 4, and this is single machine and multi-GPU training. Now, of course, this is assuming that you have like updated your training code to be able to work with distributed training. This would work with torch.multiprocessing, torch run, PyTorch Lightning, et cetera, as long as you set that up in your training code. And then when we submitted a job, we can track the progress in the Cloud Console. So here you can see all of your jobs. You can even go into one of the particular jobs, check out the logs, if anything goes wrong, see what container image you used, what the configuration was, et cetera. So this is kind of like step one when we start to think about what it means to operationalize machine learning and machine learning training. We're not just like running directly in a notebook on someone's VM, but we've actually packaged up our code in such a way that we can run these reproducible, repeatable experiments, and hopefully, at some point, move those experiments into a pipeline that we can rerun on a regular cadence for continuous training. So we've talked a little bit about distributed training on a single machine with multiple GPUs, but what about if we want to train across multiple machines? Things get a little more complex here, of course, and this is where using a managed service can be really helpful. So the main concept that you'll need to understand from the Vertex AI side is called a worker pool. Vertex provides up to 4 worker pools that cover the common machine tasks that you might encounter when doing distributed training. So you can think of a worker as just a single machine, a single node, and a worker pool as a collection of machines that are all performing similar tasks. So in worker pool 0, we would define our primary worker. This is also known as the chief or the scheduler. And when I say define this worker pool, I just mean specifying the machine type, specifying what container image you want it to run, and then whether or not you want accelerators. If you want additional workers, you would specify those in worker pool 1. And then if you're using some kind of parameter server architecture, you would specify that in worker pool 2. This is also where you would add any reducers, and I will cover that in just a minute. And worker pool 3 is where you would add any optional evaluators. So if you want a machine that's just running evaluation on your training job, you can set that up here in worker pool 3. So your combination of different workers is really going to depend on how you've decided to distribute training in your PyTorch code. But you're totally flexible on the Vertex side in terms of how you want to configure this cluster. So if we wanted to do, for example, multi-machine, multi-GPU training, again, we create our custom container training job. We pass in our image. And then my poorly formatted code here, sorry about that, we're specifying a replica count of 3. So that would be 1 primary worker, 2 additional workers. So you can think of this as like a DDP setup. Each worker has 2 accelerators on it, and this is how you would configure this on the Vertex side. And if you're a torch run user, because I think a lot of people are, the way you do this is you can pass in the command that you want to be invoked when your container is started, and this will override any entry point instructions that you have in your Docker file. In this case, our command is torch run, and then our rendezvous backend arguments, followed by the Python file we want to run. That's task.py. We pass in this command to our custom container training job, and then again, we call job.run. And this is how you would run a multi-machine, multi-GPU training job using torch run on Vertex AI. So there's one other optimization I want to mention before we look at TPUs. And this is something you can take advantage of if you are doing a distributed training setup where you've got some kind of synchronous data parallel algorithm. So before I do that, I'm going to attempt to give like the world's briefest refresher on data parallelism in less than a minute. I'll see if I can. So let's say we have 2 GPU workers, and we want to distribute training across both of them. The way you do this in a data parallel setting is you take your input data, you split it in half, you send 1 to one worker, the other half to the other worker. In this case, each worker is going to compute the same ops, but on different slices of the data. So they'll both compute the forward pass, compute the loss, then calculate gradients based on the loss function. And now we have 2 sets of gradients. So in synchronous data parallelism world, we want to reduce those multiple sets of gradients into 1 set of gradients, and we will do that via an operation called an all-reduce. And the way you do this reduction, you want to pass the data as efficiently as possible, use as little bandwidth as possible. So there are a lot of different algorithms that do this reduction efficiently. You might be familiar with ring all reduce or tree-based algorithms. But on Vertex AI, we have a feature called reduction server, which is specifically there to optimize the bandwidth and latency of multi-node distributed training on NVIDIA GPUs for synchronous data parallel algorithms. The way this works is that reduction server introduces a new worker role called a reducer. And reducer's only job is to take blocks of gradients from the GPU workers, reduce them, and then redistribute those gradients back to all of our workers. And because of this limited functionality, they can run on relatively inexpensive compute nodes. And this means that, additionally, the latency of reduction server doesn't depend on the number of workers. So again, you can use reduction server if you are working with a distributed training framework that's using NVIDIA's Nickel library to do the all-reduce operation. None of that made any sense. Don't worry about it. Eric's going to share the more fun stuff, which is his benchmarking results that he ran with reduction server.
Yeah, it sounds great. To benchmark reduction server's performance, we set up an experiment for a PyTorch training job in a multi-node and multi-process environment. When comparing the training result between with and without reduction server, we see that reduction server was able to significantly increase the training throughput and reduce the training time. The result here is really, really amazing. We're very happy about the benchmark result, but we also understand that the real impact that reduction server is going to bring really depends on the characteristic of your training workload.
Awesome. So like I said, you can take advantage of reduction server if you are using a distributed training framework that uses NVIDIA Nickel to do your all-reduce operation. You don't need to make any additional changes to your PyTorch code. What you need to do is make sure you have the transport plugin installed in your container image. This is already included in our Vertex pre-built containers for PyTorch. So if you aren't using one of those, you can just add the installation step in your Docker file. And then when you submit your training job, you'll need to specify some reduction server reducers. And that's what I've got going on over here. You can see that there are 4 reduction server reducers that I've added. I specified the machine type and also the container image to run on them. And this is what multi-machine, multi-GPU with reduction server would look like. So GPUs are not the only accelerator available to you on Google Cloud. You can also use TPUs with PyTorch, and TPU support on Vertex is currently in preview. TPUs are custom ASICs built by Google for deep learning at scale. You can write your program for a single chip, scale to hundreds of chips for sustained perf per dollar, and they do support a few different frameworks, of course, including PyTorch. So if you want to use PyTorch with TPUs, you will need to use the PyTorch XLA library. This uses the XLA compiler to basically connect PyTorch to cloud TPUs. And then you'll also need to initialize the TPU setup in your custom container. We have some samples on how that works. If you want a simpler path, you can actually use PyTorch Lightning, which will use XLA under the hood. You just need to set the number of TPU cores in your trainer. And this actually makes it really nice to move between TPU and GPU training. And you can use this on Vertex. So again, we'll run a custom container training job. We'll package up our job. And when we specify the hardware, this time we just want to specify a TPU. I've set the accelerator count here to 8. But if we were to bump that up to 32, that would actually be a full TPU pod that you could use on Vertex AI. Now, we've looked at a bunch of different ways to configure and submit training jobs on Vertex, but I think the story always feels a little incomplete to stop here, because training is just sort of like step 1, right? What happens when we want to take these experiments, do something more with them, thinking about like continuous training, that sort of thing. So Eric's going to wrap up today by talking a little bit about how we can operationalize our training jobs and use Vertex pipelines in the process.
Thanks, Ankita. Yeah, exactly. We know that launching models into the real world is more than just building it. To bring your models to life, ad hoc and manuals are not going to work. You need to have an automatic machine learning process. The process here is not only to help you to deploy the model to production, with automation and continuous training, it also helps you to scale your machine learning use cases and ensure your models are always in line with your business goal. This is really about operationalized machine learning at scale. The million-dollar question here is how. This is where Vertex AI pipeline come into place. What is Vertex AI pipeline? It's a fully managed service on Google Cloud. So with the pipeline, you can manage a machine learning process in an automatic, scalable, and cost-effective way. On your right-hand side, this is the pipeline for the PyTorch training job Ankita just introduced, starting from training all the way to deployment. This is a complete end-to-end machine learning workflow. Let's take a look at some of the key components of the pipeline. The first key step of the pipeline is to build a custom training container image. We use pre-built PyTorch image as a base, package the training application Ankita just introduced, and then build the training image. The output of this step sent to the next step to run the training job with Vertex AI training and reduction server to build a PyTorch model. Another key step here is to build. Is it?
We lost our slides.
Yeah, can we go back? Yeah, it's right here. So another key step here is to build a custom serving container image. We use TorchX image here as a base and install all the required dependencies to run the TorchX to serve model prediction. The beauty of the pipeline here, each of the steps running its own container. So you can develop the step independently and track the input and output from each step in a reproducible way. And the pipeline handles all the underlying infrastructure for you, so you can run your same pipeline in the dev environment as in your production environment, making your deployment process much, much simpler. So with that, let me hand it back to Ankita to wrap this up.
Cool. And if you want to learn a little bit more about pipelines, we do have a poster using TorchX with Vertex AI pipelines, if you're curious. So today we looked at a variety of different ways that you can run distributed training of your PyTorch models on Google Cloud using Vertex AI, whether you're doing single node, multi-node training, using GPUs, using TPUs. Hopefully, you've learned a little about how you can leverage these services to scale your PyTorch workflows. So we've got some resources here if you want to learn more about how to use PyTorch with Vertex AI. But we are constantly building new demos, new tutorials, new things. So if there's something specific you want to see, please come find us, come tell us, find us in the happy hour later. We'd love to hear what you'd like to see. Like I said, we love building new sample code. So thank you guys so much.
Thank you for your time.
Our next breakout session will be Research to Production at Amazon Scale with PyTorch, and that will begin at 1:30 in this room. Our other breakout at 1:30 in the far room will be Scaling PyTorch FSDP for Training Foundation Models on IBM Cloud. Hello, everyone. We have found a gray laptop case. If it's been misplaced, please go to the registration desk to reclaim your lost gray laptop case.
Everyone, my name is Kyuk, and this is my co-presenter Pooja, and we're both from the Amazon Search Science and AI team, and we're here to talk to you about research to production at Amazon scale, specifically about how we use PyTorch on the cloud, and what were some of the challenges and lessons learned in doing so. All right, so a bit of a team intro. We're called Search Science and AI, and we are mostly an applied ML team within the larger search organization at Amazon. And what we do is, well, one of our goals is to build state-of-the-art universal semantic representation of Amazon entities. And I know this is a mouthful, so I'm going to spend the next 2 slides dissecting what this means so that we can all understand what we mean by this statement. All right, so here are some of the examples of what we mean by Amazon entities. These are essentially things that make Amazon Amazon. And what we'd like to do is we would like to really capture the semantics of these entities and represent them in some form factor like a model or a mathematical vector. So remember how we said that we wanted these semantic representations to be universal, right? We just don't want any semantics. We actually want them to be universal. And we can define universality across 5 different dimensions or categories. And this is why the project itself is called M5 across 5 different dimensions. The first one is entity. So we just saw that a lot of the entities at Amazon are, there's not just one, but we have many. And we want to capture representations for all of them. The second one is modality. So customers interact or experience Amazon through various modalities like text, if you're reading a review or a product description, or audio-visual, if you're looking at images of a product or a video of a review. And also speech, if you're conversing with Alexa. So we want to be able to capture the signals from all of these modalities so that we can actually have very accurate semantic representations. And then the next 2, lingual and locale, have to do with the fact that Amazon is a global marketplace. So a lot of the times, these entities are actually going to span across multiple languages and multiple locales or marketplaces. So we want to be able to capture this multilingualness and multilocaleness of these semantic representations. And then finally, we want these representations to be multitask so that they can suffice the various types of use cases that we have in the core retail business. All right, before I get started on the technical details of M5 and how we use PyTorch on the cloud, I wanted to spend a few minutes really giving a shout out to some of the PyTorch ecosystem libraries that we use today that have really made it easy for us to do research to production on the cloud. And the 3 that I'd like to call out today are Torch Data, Torch Snapshot, and TorchX. And the reason for that is because all of these 3 libraries support AWS services out of the box. So if you have an AWS account and you would like to use PyTorch on it, if you use Torch Data, Torch Snapshot, and TorchX, it will work out of the box on AWS services. So as you can imagine, we're Amazon and we're very heavily on AWS. The second reason is that these 3 libraries kind of just work out of the box without you having to sit down and configure or customize them very heavily to really fit your use cases. So they have a very short time to first successful run. And that's really helped us be very productive with our experiments and really be able to focus on the core modeling aspect of things without having to worry about writing wrappers or shims to make these libraries work for us. And we were also pleasantly surprised that the performance with the default configurations were actually pretty decent. So far, we didn't really have to tweak a lot of those configurations to get the performance that we wanted. All right, as for the PyTorch core modules that we frankly don't use today in production, but that we're really excited about and we've actually started experimenting with, so we hope to actually start using them in prod pretty soon, are Torch Dynamo, Torch Distributed FSDP, and FunkTorch. And I won't go into the details of what these libraries do. You can refer to previous talks or blog posts and documentations. But I'll just say that these 3 libraries as a whole, they will increase the performance, the efficiency, the expressibility, and the scalability of our PyTorch programs. So we're pretty excited about really using them to increase our productivity and speed of iteration. All right, so back to M5 and how the journey of an M5 model looks like from research all the way to production. We split this out into 3 different phases. The first is experiment, the second one is productization, and the third one is vending. So this split shouldn't really be a surprise to anybody. It's pretty obvious that one would split the research to production in these 3 phases. But we'll take a look at these phases more in detail to give you a glimpse of how it looks like to use PyTorch on AWS. All right, so the first stage is the experimentation phase. This is the phase where most ML engineers are going to be authoring their training scripts. They're going to be trying out different model architectures as well as data sets and different training parameters. And the speed of iteration and reproducibility is of the utmost importance in this phase. So we track all of the experiments that we have and their run metadata. And we also make sure that we archive the code workspace that goes into these experiments. And this is very important for us because it helps us refer back to previous experiments to make the next set of experiments very high quality, and also for productization. So for productization, because we're tracking all of this metadata and also the workspace or the code, we're able to actually have all of the references and information that's needed to move a successful experiment into production with a very high quality. A lot of the runs at this phase are going to be very training heavy. So most of them are going to be your trainers. And your trainers need data. And we've actually experimented with a couple of data storage solutions on AWS. And we ended up settling with S3. And the reason for this was because S3 scaled the best when it came to the variety of data sets that we have, the cardinality of data sets that we had, and the sizes of data sets that we had, which ranged from anywhere between terabytes all the way to double-digit petabytes. S3 by itself wasn't going to be enough, so we had to do 2 additional customizations on top of S3. So the first thing we did was to develop a tool called M5 Data Kit. And you can think of this as like Git, but for data sets. So what this does is it essentially does a lot of bookkeeping about where your data is, what are some of the metadata that went into it. It has things like support for versioning and branching, citations of data, where your data sources are from, and it also tracks the overall lineage of how the data sets have been transformed over time. The second thing we had to do was to realize that the Boto 3 Python client for S3 was not really giving us the throughput that we wanted. We use expensive GPUs to train, and Boto 3 Python client used in a naive way was really not saturating the GPUs as we would have liked them to be. And so what we did was to PyBind the S3 C++ client for the read and writes, and that ended up giving us the throughput that we wanted to really saturate those really expensive GPUs. Coincidentally, the same methodology is also available to you guys on Torch Data. So if you have data on S3, you can try this out. It's called S3IO with Torch Data, and try to see if that actually improves your throughput. Cool. The jobs have to run somewhere, so we have to choose a compute cluster and a scheduler. And we ended up choosing AWS Batch for our choice of compute cluster. And this was because Batch is actually built ground up to service HPC customers. So one interesting trivia about Batch was that one of the goals of AWS Batch was to move traditional HPC customers that are running on-prem onto the cloud. So we wanted to help people make that transition from on-prem clusters into AWS. So a lot of the features and API design that went into Batch is very canonical to HPC use cases, which is very relevant to AI use cases as well. The other property of Batch that is going to be very relevant for the audience here is that Batch itself is a free service. So there is no additional service surcharge for using Batch. What you really pay for is just the AWS services, the other AWS services that you use through Batch, like EC2 or S3. And with this, I'm going to hand it over to Pooja to talk about the rest of the phases.
Thanks, Q. So, hi everyone. My name is Pooja Maknikar. I am SDM at Amazon, leading M5 productization experience. I'll be talking about the second stage in model lifecycle, that's productizing ML models. So as you can imagine, M5 model size ranges from tens of millions to 100 billion parameters. It's not easy for everyone within Amazon to use these models or experiment with these models because they don't have access to hardware, to best hardware or enough proficiency to invest in high compute performance system. So to overcome this challenge, we distill down large models into smaller ones for better portability and practicality. This helps us when large M5 models to other teams who doesn't have enough hardware available. Next challenge we faced was our downstream customers do not depend on Python runtime. They use Java or C++ services to build latency sensitive online inference services. To To enable these customers, we serialized models using TorchScript and vended out these models to remove dependency on M5 code base as well as on Python runtime. So this was done, but the main challenge here is bringing up research code to production standards. And heavy lifting in productization stage is we invested time and efforts in improving code base used for data processing as well as model source code to meet our production bar by modularizing code base, writing unit tests, integration tests, as well as adding automated quality checks in our CI/CD pipeline. Last but not the least, we also added model card for each of the model in productization stage to give information to customers on how the model was trained, which data set was used, how the model performs on different benchmarking tasks. This helped us achieve ease of use and performance and increase the adoption of M5 across Amazon. Let's have a look at the stats of M5 adoption. So in just last 3 quarters, we have seen 210 plus teams using M5 models. They have onboarded, plus there is a 20% average month-over-month growth in customer adoption, and 100 plus teams are using pre-computed embeddings. I'll cover more details on this later, but the crux of this stat is us building scalable vending solution helped us achieve the customer adoption goals in 2022. So the next stage in ML model lifecycle is vending. In vending stage, we heavily optimized on improving reliability and user centricity of our M5 models. Our downstream customers deploy these models in production system, so it's important to have reliable source of vending these models. We built central repository called Bazaar Model Hub on top of AWS SageMaker to vend out vetted, versioned, and documented models across M5. Using SageMaker model registry enabled us to not invest in needing to reinvent the wheel of defining data storage or maintaining the versioning. We just used off-the-shelf SageMaker model registry for building Bazaar. The next thing we invested heavily in is benchmarking each model which we went out via Bazaar. All our downstream customers have variety of task use cases to use these models. So we kept evolving our benchmarking suite to improve our model quality and task coverage. We included these model cards, we included this information in M5 model cards so that all the benchmarking results are available to customers before they choose which model to use for their use case. The next thing we invested was we provided usage script to each customer for every model vended via Bazaar. This enabled customers to help them understand how to query the model hub, how to load the model, how to run the inference using model. For the vending stage, we categorized use cases into broadly 2. One, customers can fine-tune M5 models on their custom downstream tasks, or they can just they can generate the embeddings using Amazon product catalog. We analyzed that most of the customers were downloading models and setting up pipeline to generate embeddings. We identified this common use case and started generating embeddings for Amazon product catalog, and this helped our customers to increase their experimentation velocity. Next, I'll dive deep further on our M5 model hub referred as Bazaar. The right side of this slide shows high-level overview of how Bazaar was built. The top workflow shows how M5 trains M5 models using PyTorch eager mode. First step is Python pre-processing module. The output of Python pre-processing module gets fed to main model, which is in eager mode. So just before productizing these models, we use TorchScript to serialize the Python pre-processing code and serialize deep learning model, and then register it into Model Hub. The main difference here between other model hubs is we also went out serialized preprocessor. Here, this helped us enabling customers to maintain the consistency in code between training as well as inference. TorchScript has several advantages, including top few, including it does not depend on Python runtime. It enabled our customers to deploy M5 models as is in their inference systems, as well as it removed the dependency on M5 code as well as third-party training related dependencies. However, it does come with the cost. We need to invest time and efforts to serialize the pre-processing code and main model and maintain our code's scriptability. It did work out for us because we serialize model only once, and there are tens or hundreds of customers using this model as is without having to re-implement the pre-processing code or having to bring in all the dependencies coming with model. Okay. Next, I'll be talking about the typical customer engagement workflow at M5. As you can see on the right side of diagram, customer engagement funnel can be divided into 4 stages. First is onboarding, followed by experimentation, followed by deploying to production, and then expanding it to worldwide. We do have baseline on dwell time, average dwell time at each stage of this engagement funnel from various customers. We optimize our products and tools to reduce this dwell time as well as to increase the convergence from one stage to the next one. We track model ROI and platform feedback on an ongoing basis through tight partnerships with customers. We use this engagement data to improve our product quality and user experience. So as a takeaway, the bottom line is we improved research to production velocity for teams across Amazon using these 3 principles. First, warm start. We created Model Hub, which is collection of pre-trained ML models to start from. So customers don't have to invest time or hardware in training the model from scratch. We have dedicated team of engineers to continuously improve the model quality and generalizability of the models. Second was resource efficient. As you might have known that there was a GPU resource crunch at the start of this year, M5 being the central team to pre-train the large models, which are resource intensive as well as time intensive and expertise intensive. By providing these distilled version of models via Model Hub to customers, customers can use these models without having to have any prerequisites of hardware. Last is best practices. We are the early adopters of technology, so we learn through our mistakes, and we share our knowledge to customers via models vended, as well as tooling and libraries and documentation shared with teams across Amazon. So this concludes our presentation. Thank you so much.
Thank you.
Hello, everyone. Good afternoon. My name is Parinita Rahi. I am from the Microsoft AI Frameworks team within the Azure AI Platform organization.
Hi, everyone. My name is Razwan Tanase. I'm an engineering manager in the Azure Machine Learning team under AI Platform.
And today, we are here together to talk about the Azure container for PyTorch. So this is a better together story with how PyTorch works great with Azure. So the Azure container for PyTorch is meant to solve 3 key problems. One is for researchers and scientists. How do they, don't worry about the setup times and, which package is compatible with which other version that is required for their large training workloads. So, we test and we pre-install and validate packages that are required for typical deep learning workloads for your training workflows. And then it's also meant to optimize training time. So it comes pre-installed with Microsoft's open source technologies that has accelerators that help speed up your model training time. And then it is integrated within the Azure stack, so you can use it easily within Azure ML SDK, within the CLI, or the Azure ML Studio.
Okay, so now let's see what this Azure Container for PyTorch is really about. In essence, it's an optimized training framework which is useful to ease the setup and development of PyTorch model training. Besides that, it comes with the latest versions of Ubuntu, Python, PyTorch, along with device drivers that are optimized to perform on Azure hardware. Besides that, it comes with a bunch of accelerator technologies that are meant to speed up the model training, such as Onyx, Onyx runtime for training, deep speed, Onyx runtime for a mixture of experts, and OpenMPI. All of these are validated and tested against multiple first-party customers that are within Microsoft, and we guarantee that these will be working perfectly for third-party customers as well. Besides all the training packages that are meant to speed up, this Azure Container for PyTorch is also useful for the experimentation phase of deep learning, which means that it comes pre-bundled with a bunch of profilers, like PyTorch Profiler, PySpy. It has integration with TensorBoard, so data scientists can monitor the model training phase and whatnot. And besides that, it is also backed by Azure customer support. I can go over some of the details for the container. So the Onyx runtime is used for both speeding up the inference and the managed training. At the same time, DeepSpeed is one open source deep learning library that is meant to speed up training, and it's shown that is useful for training billion parameter models or even trillion parameter model in near linear scale. The Azure Container for PyTorch is available in two flavors. First of all, the most lightweight option is a curated environment in Azure Machine Learning Workspace. And second of all, it's available as a VM image as part of an Azure Data Science VM, or DSVM as we call it in short. Curated environments represent a managed asset that is versionable and allows customers to have transparency, trackability during their ML lifecycle process. DSVMs are useful for, DSVMs are one way for customers to get an entire OS image which bundles data science specific tools. Besides the model training, also tools for visualization and many more.
Yeah, so to add to that, I think the curated environments help you enable reproducible, auditable, and portable machine learning workflows, so you can repeat, view your tasks, your training jobs, and repeat them with changing certain parameters, et cetera, very easily. So it helps scale out for organizations who want to reuse their training workflows over and over again, and has versioning support and other similar properties. So this is an example where when we use the Azure Container for PyTorch and include with it the deep speed acceleration technology and the Onyx runtime training capabilities, the gains that we see in terms of the samples per second or the training time. So here, this was run against the Hugging Face models like Roberta Large, GPT-2, Bloom models, and Distilbert. And the green lines are when it's run just with PyTorch. The orange is when it's run with PyTorch plus Onyx runtime or ORT. And the blue is when it's run with PyTorch, ORT, and deep speed. And you can see the huge jump in terms of the training time improvements. We see 39 to 103% faster training times when these powerful acceleration technologies are combined and run with PyTorch on Azure. So here are some customer examples of folks who have tried ACPT and the capabilities included within. The first one is Bing. So Bing runs its ads language representation model that is served over 130 markets. And these are transformer-based models using billions of parameters, and they use it both for continuous pre-training and fine-tuning. And with overcoming resource limitation and speeding up training productivity are key objectives. And so when they use ACPT with deep speed and ORT combined, they see anywhere from 1.3x to 2.4x speed up in their training times. The other one is a third-party customer we have, which is a small startup which works on AI algorithms that help generate original clothing designs and help fashion companies meet customer demand and get to market faster. And so with smaller-sized organizations, its resource is a big challenge. Time spent in setup and all of that, the easier we make it for those customers, the better it is. And so in their distributed data parallel implementation, they were able to use ACPT effectively to gain their objectives. There is a blog available for this on the Azure website. I can link it out later. And another internal Microsoft team that used ACPT is the Microsoft AI Cognitive Service team. They build state-of-the-art computer vision technologies for next generation framework for visual recognition. And they're able to use ACPT to run scale jobs over hundreds of GPUs, and were able to do it efficiently. And that, again, helps most of these research teams focus on the research work without having to worry about, how do I integrate all of these various libraries and components and keep up with the new versions that are coming up and the new versions of PyTorch that are coming up.
Okay, so now let's look how the entire PyTorch stack on Azure works. So at the bottom of the stack, we have the hardware layer, which contains most up-to-date, most powerful GPUs that are available in the market, like NVIDIA A100s or NVIDIA V100s, which are interconnected with speedy InfiniBand interconnects. On top of that, we have the next layer, the software layer, which our recommended way is the ACPT container, which bundles a bunch of training optimizers like Onyx Runtime, DeepSpeed, SYCL, and it has the pre-validated versions of all of these components that are guaranteed to get the most optimal performance for customers. All of these can be used with multiple entry points, such as the Azure ML SDK or the command line interface, or simply from the Azure ML UI. Customers can come and choose and integrate at any layer that they want from the stack. So they can either use our pre-built curated environments, or they can build their own custom solutions, which might be tailored for their needs. We have many customers that are using this internally, like Parnita just mentioned, the Bing, Microsoft Office, and at the same time, cognitive services. The benefit for the end customers is that they would get to use the same technologies that have been battle tested by first-party customers against planet-scale workloads.
So next up, we have a demo on how easy it is to use ACPT within Azure ML. For this demo, we'll show you a Distilbert fine-tuning model from Hugging Face. Let me see. How do I, it's not playing. Okay. So in this demo, we'll cover 4 aspects. One is how do you create a curated environment and a custom environment within Azure ML. And we'll show it specifically within the studio, but you can do it through CLI and SDK as well. And then we will show you how you can train a custom environment using the custom environment that we built with ACPT. How can you train the Hugging Face Distilbert model? And then if you were to compose it with DeepSpeed and ORT, what are the training time gains that you would see? And then finally concluded with how to deploy this on Azure ML and inference using Onyx Runtime. So in this example, we are using the Hugging Face model, which is trained with the Stanford question and answering or the SQuAD dataset. And this one takes a question and it takes a piece of text called context. And then it produces an answer, which is a string of text taken from the context. It tokenizes and encodes the question and the context and feeds the input into the transformer model, and then generates the answer by producing the most likely start and end tokens in the context, which are then mapped back into words. So in this example here, we have, some of the demo resources. I'll provide a link to it for the YouTube video. There are 2 source codes we'll be using in this demo, and both of them are available in our GitHub repos. And additionally, to run this demo on Azure ML, you would need Azure subscription and an Azure ML workspace and the access to Azure ML UI Studio. So this example is of the Distilbert fine-tune model. There are 2 code files. One is the ds-config JSON file, which is in use to enable the deep speed configuration. And the second code is a fine-tune.py file. And in here, basically, it takes 2 arguments. One is to enable ORT, and another is to enable deep speed. And then the source code for the Hugging Face transformer model that's used is part of that resource. So if you're interested, you can take a look at that from the Hugging Face site. So we load the squad data set. Again, the data set is available in the Hugging Face dataset library. And in the first, we load the model, we load the transformer, and then we convert it. If the ORT argument is specified, we convert it into the ORT module. And then similarly, if the deep speed argument is specified in the JSON, then it enables the deep speed state zero enablement. And then the model training happens. So this is the source code used. Now Razwan will tell you how to create the curated and custom environments.
So right now we're going to see the curated environments and custom environments experience on the UI. If customers would be able to use directly the curated environments, they would have 4 different options depending on various versions of PyTorch, CUDA, and that are part of the packages. For this particular demo, we need some extra packages from Hugging Face, the transformers and the data sets. So in this case, we're going to create a custom environment starting from the curated environment on which we're going to do this package installation. So Parinita is going to show over here. We create a custom environment. We give it a name, which is going to be ACPT demo.
Yeah, so the previous snapshot was what the curated environment would look by itself, and you could easily use that for your training workloads. But as Razwan said here, we need transformers and a few other dependencies, so we are going ahead and enhancing the custom environment.
So we're starting from the curated environment that contains the PyTorch 1.12. Then we're going to add pip installation for several packages, transformers, accelerate, and datasets. And once everything is edited, and we're going to proceed towards creating it.
You can also add tags in case you want your environments to be searchable. We're skipping that step here. And then review and submit.
And now we're going to have a custom environment that is going to be ready for training. So it builds successfully.
So once we have a custom environment created, we can also use that within our training job. So it asks us to select a compute type. You can choose automatic compute or a compute cluster. And then for this model, given GPUs are useful, we'll use that. And then we could choose, for another example, the ACPT curated environment, but we'll go ahead and use the
custom environment that we just created.
And once we have the custom environment, we'll give it a name.
And the next step is to upload the files that Parinita just showed earlier, the fine-tuning and the deep speed configuration, pretty much the entire folder where she had the source code. And we're going to have 2 experiments over here for comparison. So one is going to be running that fine-tuning script without any arguments. That's going to be the vanilla fine-tuning, so no acceleration from neither deep speed nor Onyx runtime for training.
Yeah. So 2 flavors, and so here we'll write the command. So you just need to specify Python and then fine-tune.py, which was the fine-tuning script I showed earlier. And if you're running it with deep speed or ORT, you just need to pass those as additional arguments. And if you're running without it, you just submit this as is.
Over here in the create training experience, you would be able to see below that, besides the core training aspects, customers would have the ability to enable interactivity of the job. So they are able to connect with the Visual Studio Code. They can connect to a TensorBoard endpoint. They can actually remote into the container that's running. It's pretty much helping the entire experimentation phase.
So we added the distribution type. We added the process count per node after we had applied. And then we review our training job specifications, and then we submit create. So there are two outputs. The first output is the one which was just with the fine-tune.py and no deep speed and ORT arguments specified. You'll see the total training time is around 8,440 seconds, which is 2 hours, 24 minutes. And another run of the same job was with the deep speed and ORT arguments specified, and the total training time there is reduced significantly to 5,044 seconds, which is 1 hour, 27 minutes. So that's a total 1 hour gain in terms of your training job. So imagine if you have to run this over and over again, how much compute resources you would save. So next, we're going to show you how to deploy this trained model on Azure ML and inference it with ONNX runtime. So the resources, again, attached with the slides. You could do it through the CLI by installing all of these dependencies. We'll show you how you can quickly, the code for converting to ONNX format is also available here. And then, if you were to run the model with ONNX runtime, that's also shown. All scripts are available in the resource. So here we'll locally convert the pre-trained ONNX model, the pre-trained Distilbert model into ONNX format. And that requires you to run it in eval mode and pass certain inputs and call the torch.export ONNX module. And once we have the local file, then we can also test it locally on our Jupyter notebook just to see that the trained model works well. And so here, you provide a question called what is Dolly Parton's middle name with some context, and we get the right answer, which is Rebecca. So we know that the model works fine. So now let's see how to deploy this model on an endpoint on Azure ML.
So we're going to create a real-time endpoint over here, and we're going to use the ONNX model that Aparna just generated locally, and she had tested. So the first thing is we're going to provide the name for the endpoint. We're going to choose the compute type that we're going to use, and later on in the stage, we're going to actually upload that model. One of the things that we were saying earlier about the entire PyTorch stack is that it's pretty modular, and then customers can come and choose at each point in their ML lifecycle how they want to integrate. In this particular case, we're leveraging the inferencing part as well, not just training as we focused earlier.
To continue with the inferencing, it asks us to register a model. And so we'll browse it locally from the ONNX file that we had created and upload the model so that the model is registered. And once a model is registered within Azure ML, you can use it across various inferencing jobs and deployments.
And one of the other benefits of registering the model is that you would be able to get full lineage of that model. So you're going to be able to see the data set that was used for training. You're going to be able to see the environment, the cluster where it was trained. That helps with reproducibility and traceability for your ML lifecycle.
So we now have a registered model. So the next step is to go ahead with the deployment. We'll go and give it a deployment name. And so as part of, and it asks for a scoring file. So a scoring file essentially has two functions. One is an init function, which is called once, wherein we'll load the tokenizer and we'll call the ONNX runtime inference session. And then a run file, which runs multiple times for each node. And in here, we will basically perform the inferencing task from using ONNX runtime.
Yeah, the run function is executed for every request that goes into the real-time endpoint, and the init one is just when the container gets started.
So we upload the score file here, and then we can select both the ACPT curated environment or the custom environment. Both have ONNX runtime package loaded in it, so inferencing can be performed with either. And then we select the virtual machines that are available within our workspace and provide an instance count and give the amount of traffic we want it to receive and review. And that's it. We have an endpoint ready.
And once the endpoint is created, then you pretty much get an URL that you could hit from a Postman or any of your favorite HTTP clients.
We showed you how to create the file, like convert it into ONNX, how to register the model. Now to invoke the endpoint, you can use the online endpoint invoke command and pass your workspace and configurations and resource group, etc. And that way you can use the model. The other way is also to call using the post URL from Postman. That is it. I think we have a few additional resources available externally. One is the Ignite announcement blog for the Azure container for PyTorch that you can use and leverage for additional details about the container. And then we have some of the other resources I showed you within the demo that you can access. And last but not the least, there is a short survey. There are 6 sweaters to be given, so if you take the survey, there is a chance that you might win a sweater or 2. So please do submit the survey, and thank you for taking your time.
Thank you.
Welcome back, everyone. I hope you had exciting conversations today. I sure did. So this afternoon, we'll have our partner talks. And to get us started with this, we're going to have Joe Isaacson and Geeta Chauhan discussing the state of PyTorch.
Hey everyone, welcome back. Excited to be here today. My name is Joe, and I'm an engineering manager at Meta on the PyTorch team. And I'm joined virtually by Geeta Chauhan, who will be joining us for the second half of the talk. So excited to co-present the state of PyTorch, which has become a little bit of an annual tradition to give a lightning overview of some of our major feature launches, talk a little bit about some metrics and growth, and help celebrate all of you who have helped to make PyTorch the success that it is today. So kind of in that order, talk about some feature launches, do a little deep dive into research community using PyTorch, back out to the community at large, and then finally hand it over to Geeta for industry. So first up, we're excited to have had 3 major releases this year, 1.11, 12, and 13, constituting somewhere around 10,000 commits from hundreds of developers. So thank you all for that. You've heard about many of these major feature releases throughout the day today in talks and in the poster sessions, but just to re-highlight, we have Torch Data, Torch Arrow, new libraries for common modular data loading primitives, for constructing flexible and performant data pipelines, and for pre-processing of our batch data. We've upstreamed FuncTorch, a library that adds composable function transforms into PyTorch for familiar APIs like VMAP and GRAD, JVP and VJP, enabling things like per sample gradients. We're excited of our launch of FSDP, fully sharded data parallel, enable training of large AI models by sharding model parameters, gradients, and optimizer states across multiple machines. One of our most highly requested and commented on issues on all of GitHub, Apple M1 support. So we're excited to launch acceleration on Mac to now take advantage of Apple native Silicon GPUs for significantly faster model training. We had a poster session on Better Transformer. So this is kind of out-of-the-box performance wins on CPU and GPU for fast path implementations of transformer encoder layer and for multi-head attention. NVFuser is our new deep learning compiler for PyTorch, supporting a wider range of operations, faster speeds, and TorchScript has been updated to use it by default. And finally, we're incredibly excited about our new domain library launches for TorchRec and Torch Multimodal. On the rec side, having a common sparsity and parallelism primitives for high-speed recommendation systems, and on the multimodal side, having this composable building blocks for training state-of-the-art MTML models. So backing up a little bit, we're excited that we can now observe over 350,000 GitHub repos that use PyTorch available. And that's about a 45% growth year over year. I don't think it would be fair to be adjacent to the NeurIPS conference without taking a little time to dive into researcher usage. So we see over 9,000 GitHub repos that can be associated with AI research papers from this year via Papers with Code. And that constitutes somewhere around 63% of all AI research implementations choosing PyTorch, and a 4% growth. With the Cambrian explosion of AI, it would be impossible to get into every single domain that is currently using PyTorch, but just to highlight a few we're excited about. On the generative modeling side, we have researchers at FAIR who have built Make a Video to be able to take as input a text prompt and generate these kind of whimsical, one-of-a-kind videos. PyTorch is being used in next-generation therapeutics with researchers at Asimov using PyTorch to generate optimal programs for living cells to produce next-generation therapeutics. And on the graph neural network side, Kumo AI is using PyTorch alongside the popular PyTorch geometric to build, train, and scale large-scale graph neural networks. So talking a bit about the community, as I mentioned earlier, we have over 11,000 commits over the past 12-month period, with more than 3,000 unique contributors, which is crazy, and a 20% increase year over year. So I just want to thank all of you for kind of coming here and contributing to PyTorch. There's a little bit of a technical issue, so we aren't able to have a scroll with everyone's username who's contributed over the last year. So this is a random sample size of individuals, but whether you've contributed documentation or bug fixes, low-level performance optimizations, high-level API design, we appreciate all of your contributions. And finally, there's contributors from major organizations as well who have helped with everything from fast kernel development to supporting different devices, integrations into cloud providers to make it easier for AI researchers and developers around the world to be able to use PyTorch. So thank you all for coming in. And lastly, I just want to highlight one of my favorite aspects of all of PyTorch, which is community engagement. It's incredible to me that we have over 2 million views of our PyTorch discussion forum. There's been over 20,000 replies to community questions and concerns and bugs. So thank you for being active on there and getting out there and helping the community. And over 3,000 contributors to that. So with that, let me hand it over to Geeta to talk about industry usage.
Thanks, Joe. I lead the Applied AI group at Meta. We collaborate with leading companies across the industry for PyTorch adoption and integrations. I will share some of the key highlights from our work in 2022. From the latest LinkedIn talent report, we are seeing more than 44,000 professionals have tagged PyTorch as a skill set on their LinkedIn profile. And there are 2,500 plus related jobs for PyTorch on LinkedIn now. Overall, this is a 50% year-over-year increase in PyTorch professionals just this year. With the cloud providers, our focus this year has been on large foundation models. With AWS, we enabled the launch of the Trainium ML chips for training large language models and seeing near linear scaling across the Trainium clusters. Further, in a three-way partnership with Google, AWS contributed the XLA backend to the PyTorch distributed to ease migration of training workloads onto the Trainium chips. With Microsoft Azure, we launched the PyTorch Azure Containers and the DeepSpeed MII library, a new open source library that speeds up model inference and at a lower cost point with built-in support for more than 24,000 models. With Google Cloud, we launched the PyTorch XLA profiler for the cloud TPUs to help with troubleshooting and profiling large training runs. We also added support for the fully sharded data parallel to PyTorch XLA and launched the OpenXLA project for community-based ML compiler and infrastructure projects, which includes the XLA compiler and the stable HLR. We saw many exciting startups emerge in the AI space. I would like to highlight a few. Stability.ai, best known for the open sourcing of stable diffusion models, is building open AI tools for developing cutting-edge AI models for generative art, music, language, videos, 3D, and biology. Predibase offers an alternative to AutoML and uses a declarative approach to building AI models. Their Ludwig library, a Linux Foundation project, has migrated to PyTorch from TensorFlow, and we collaborated with them to add support for scriptable tokenizers to TorchX. Fashable is a startup focusing on AI-generated fashion for clothing design for the fashion industry, for faster time to market and reducing waste. We helped their team to speed up their GAN-based model training in collaboration with Microsoft Azure. We are seeing a rise in the software vendors building libraries and solutions on top of PyTorch. Hugging Face, a standing partner known for the transformer libraries. This year, they added support for Accelerate to speed up distributed training and inference, and diffusers for the diffusion models. We have collaborated with them to integrate better transformers and fully sharded data parallel. Elasticsearch, the search engine platform, has added embedded PyTorch support for NLP models by integrating libtorch into the Elasticsearch stack, making it easy for developers to perform tasks like named entity recognition, sentiment analysis, and more from right inside the Elasticsearch itself without having to make an external call. MosaicML is another emerging startup with focus on efficient model training. Their PyTorch-based library Composer enables training neural networks faster and at a lower cost point. They recently launched their own cloud offering, and we are collaborating with them on integrations for FSTP and Torch data. We are seeing a rise in the production use cases of PyTorch across the industry. I would like to highlight a few. On the Tesla AI Day, Tesla shared details of how they're using PyTorch, not just in the self-driving car, but also as part of their Dojo superclusters and their new AI accelerator, with Dojo extensions for PyTorch and their new compiler engine. With Disney, we collaborated on their new multimodal-based activity recognition solution for the media production field, where they combined insights from audio, video, and subtitles to get better results. Amazon Search is using large-scale models across multiple modalities to power their discovery engine for Amazon. Their M5 team runs thousands of experiments and training jobs each month and is quickly able to roll them into production. They make use of PyTorch Distributed, PS3 plugin, PyTorch Profiler, and are migrating to FSTP. We are excited to see these great uptakes of PyTorch across the industry. You will hear from many of our partners on the talks today, along with the poster sessions. For more case studies, please check out the PyTorch community stories and Medium channel. I will now hand it back to Joe. Thanks.
All right, thanks, Geeta. And thank you all for coming out today and for being part of the PyTorch community. Hope to see you all on GitHub.
Hello, everyone. My name is Jeff Daly. I am a principal member of technical staff at AMD. I have the privilege of speaking to you today about getting started with PyTorch on AMD GPUs. So I have the pleasure of working with a fantastic team, and I really need to highlight them here. So every one of them contributes to making PyTorch either more performant or robust. You'll find many of their usernames on pull requests and issues, but really, you can't count source line contributions alone. And that's because a lot of them work behind the scenes, too, working on features, performance tuning, CI maintenance. The bottom line is this team represents a significant investment from AMD to the success of PyTorch on AMD GPUs. So today, I'll be covering the hardware and software products from AMD that enable running PyTorch on AMD GPUs, and I'll finish with some exciting performance results. So I'm going to start by introducing the AMD ROCm software stack, but I really need to talk about our GPUs first. So AMD builds high-performance computing solutions for a broad range of use cases, from PC gamers to data center platforms. So while traditional GPUs have been built to be general purpose in nature, designed to drive both graphics-oriented as well as compute-oriented workloads, AMD recently introduced a different approach to fuel even higher efficiencies. So now there are two architectures. AMD RDNA is optimized for gaming to maximize frames per second, and AMD CDNA is optimized for computing to push the limits of floating point operations per second. But more importantly, both of these architectures can run PyTorch, and that's enabled by the AMD ROCm software stack. So ROCm provides a complete set of libraries that you would come to expect. Starting from the bottom up, we have driver support across several Linux distributions. Sitting on top of that is our HIP language, compiler, and runtime, as well as a debugger and profiler. math libraries such as BLAST, solvers, MIOpen, which is for convolutions, RNNs, and normalizations. All of these lower layers is what we build on top of to enable frameworks such as PyTorch. And thanks to ROCm, you can run PyTorch today on the RDNA-based AMD Radeon Pro V620 or the CDNA-based AMD Instinct MI250 GPUs, just to name two. It's the same ROCm, and a critical piece of ROCm is HIP, so let's take a closer look. HIP is a C++ runtime API and kernel language that allows developers to create portable applications for AMD and NVIDIA GPUs from a single source code. You can compile HIP C++ code for either platform, which means if you develop new projects directly in HIP, it'll work on both. But we do recognize that there are many existing projects, and so we provide porting tools. These tools make it easy to port CUDA code to HIP. It's a source-to-source translation tool called Hipify. There are a few implementations of Hipify today. One of them is Hipify Clang, which allows you to translate C++ code. But we also have Torch Hipify, which is a custom Hipify built right into PyTorch. It's in the Torch utils directory. It's baked right in, and it's pure Python. So you can start with any of these HIP codes and now compile it for either platform, such as PyTorch as one of these codes. So the similarities are pretty apparent, but there are differences too, and we need to highlight those. So we do expect developers would need to conditionalize, compile their code in some cases to protect against hardware differences or software differences, or even specifically performance differences when we tune for specific platforms. And so, for example, what CUDA calls a warp, we call a wavefront, and on NVIDIA devices, the warp size is 32, but on our hardware, CDNA-based GPUs, it is 64. And that's just one example of a difference that we'd have to conditionally compile to protect or to optimize for. But you really don't have to worry about PyTorch because we've taken care of all of that for you. We've already done the porting effort. Okay, and to help illustrate Hipify, let's take an example and look at it. All right, so the original CUDA code is on the left, highlighting specific CUDA API calls, and the HIP version of it is on the right, and you can see the similarities right off the bat. Okay, including the triple chevron notation for launching kernels, it's the same. Our Hipify tool will take care of this for you, allowing you to get started quickly on our GPUs. Okay, so now that you've seen an example of the kind of HIP porting effort, now let's look at how to build and install ROCm PyTorch. We are absolutely proud to say that ROCm PyTorch is PyTorch. All of our code is part of mainline. So you can go to pytorch.org, the Getting Started page. You'll find us there right next to the other stable compute platforms. We have what you would expect, stable wheels, nightly wheels, Docker images as well, and soon we're going to have Conda packages too. But if you have to build it from source, it's really easy. There's only one extra step, and that's to run the Hipify tool first. And like I mentioned earlier, Hipify Torch is already part of PyTorch source code, so it's all there for you, ready to go. All right, so we've covered how we ported PyTorch to ROCm. Now let's cover an important topic of porting your workloads to ROCm PyTorch. So on the left, we see a simple PyTorch model. And as we did before with the Hipify example, here is the version of the code for ROCm. And I'll go ahead and highlight the differences for you. There are no differences. The code is identical. Okay? That's by design. You should not need to port your PyTorch workloads to ROCm running on AMD GPUs. This includes the torch.CUDA module that would manage HIP streams, device management, architecture lists, memory usage, et cetera. And that's because the similarities are there. Even sending your tensors to your device, it's still CUDA. So 2 device equals CUDA, that works for us as well. It's kind of unfortunately named that way, but that's how it is. We have full feature parity with CUDA PyTorch, including the caching allocator, streams, devices, convolutions, BLAST, and nickel. Okay? All of this is regularly tested by our internal QA teams, but it also, every single PyTorch commit runs against our ROCm CI. You'll find it on the HUD if you went and looked. Okay? Furthermore, CUDA extension classes like Torch Vision that use CUDA extension, they'll run Hipify for you automatically. And there are some caveats. Some of the compiler flags need to be changed, but really it's pretty straightforward. If you want to see an example of how it's done, I recommend that you look at Torch Vision as an example. The bottom line is we wanted the minimal barrier for entry. Okay? We want you to be able to run your favorite workloads, your Hugging Face models right out of the box, no changes. So this is all intentional and by design. All right, I've showed you how it works. Now let's see how fast it runs. We've used Microsoft's Superbench version 0.6 to collect these performance results. Superbench is a validation and profiling tool for AI infrastructure, which supports, among other things, workload benchmarking and profiling. So we've used it as a test harness to run some Hugging Face workloads, as well as some Torch Vision workloads. So these results feature our AMD Instinct MI250 128 gigabyte Open Accelerator Module, or OAM. And it consists of 2 graphics compute dies per OAM, compared to NVIDIA's A100 80 gigabyte SXM. Here we're presenting total training throughput, which is the harmonic mean throughput of each GCD summed across all GCDs. And this is FP16 training. You can see we're up to 1.4 times faster for transformer-based models and up to 1.6x faster for vision-based models. And the results really speak for themselves. However, we do invite you to try it yourself. Okay, you can take a test drive today using the AMD Accelerator Cloud. It offers you an environment to remotely access and evaluate AMD Instinct accelerators or AMD ROCm software. Whether it's porting legacy code, benchmarking an application, testing multi-GPU or multi-node scaling, the AMD Accelerator Cloud gives you quick and easy access to the latest GPUs and software. Software such as OpenAI Triton, which we've been working on for a while now in support of PyTorch 2.0. So some of the information I presented today can be found on docs.amd.com. That's our documentation page. There's far more information there that I could cover in the time allotted. Information about HIP, porting guides, the rest of our libraries, and much more. And you already know how to find our stable wheels, but if you want our Docker images, there's a link for you there as well, and also a link for the Accelerator Cloud. Thank you very much.
Hello, I'm Keita Watanabe, and if you take a look at the slide, there's my name actually. So, okay, seems like the title, we have 2 titles, but please ignore a practice guide on AWS Inferential, because in this session, I'm not going to talk about Inferential, which is already covered in the poster session. Unfortunately, this session originally supposed to be done by our colleague Urosh, but because of some unfortunate accident, he's not available, so I'll be talking about today's session on behalf of himself. So before going to actual topic, let me briefly introduce my team. So my team, AWS Frameworks team, is supporting our self-managed machine learning workload, which is a machine learning workload which doesn't use any managed solution, such as SageMaker, for example. And as a software stack, we are mostly using Kubernetes, EKS, Slurm, Power Cluster, AWS Patch. And the primary workload is LLMs, but not limited to that. Machine learning in general will be our scope. And so today, I'm going to talk about our latest option for distributed or a large-scale machine learning model training. But before jumping into that, let me briefly talk about LLM trends and so forth. So first up is large language models trends. So as all of you have already know and also have seen in the session or new reps, the number of parameters of machine learning models ever increasing over time, especially recent years, which presents new challenges such as in communication through nickel or glue, and also we need to tackle memory limitations, and also need to exploring heterogeneous architectures, which kind of raise the needs to support different data types. So with that being said, for such challenges, we recently released AWS Trainium, which is a cost-efficient LLM option available. So AWS Trainium is the second generation AWS developed in-house chip for machine learning training, which is 1.5 more performant for popular NLP models compared with P4D instance, and also up to 4 times network bandwidth compared with the same instance. And as a result, cost-wise, we have up to 50% reduction to train LM models. So far, we have 3 type of instances which supports Trainium. The smallest one is TRN1.2x large, which has 1 Trainium chips. And the largest one is TRN1 32.x large, which equips 16 Trainium chips. And in this reInvent, which was actually happening at the same time as we have NeurIPS, we have launched TRN1.1n.32x large, which is essentially TRN1.32x large, but have a double instance networking capacity. So this Trainium has native support for a wide range of data types, such as FP32, TF32, BF16, FP16, uint, and configurable FP8. So as a result, compared with, again, with P4D instance, we have achieved a huge improvement in pflops performance. For example, compared with in the comparison of float 16, the performance of Trainium is 1.4 times better than that of P4D. Similarly, for floating point 32, we have 2.5 more performant capability in Trainium and 5 times more performant in float 32. This is partly enabled by our new feature called stochastic rounding. So in neutral rounding, say if you have 1.2, it will always be rounded to 1. But on the other hand, when you do stochastic rounding, it will be rounded based on its number. So in this particular case, 2 times out of 10, you got to have 2, and or for the rest, we have 1. Based on that, we can achieve a better performance, better training performance with faster training time. So let me lastly explain about PyTorch integrations. PyTorch integration of Trainium is enabled by the software stack shown in here. In the first layer, we have PyTorch, of course, which has lazy tensors for eager execution and compression. And the second layer is JIT cache, which hiding compression overhead and kind of easing development of machine learning models. And PyTorch XLA converts PyTorch operations into corresponding XLA operations. And XLA is the compiler-based linear algebra execution engine. And all of those stuff enables distributed trainings. And in Trainium, we support mixed precision FP16 and BF16. And DDP is also supported. And if you want to go even more, supporting multiple instance training, FSDP is also supported by Neuron SDK, which is SDK we use to train ML model on Trainium. So this is the minimal code we can use to train about large models. So in here, we are using Hugging Face transformers. And if you have experience training your model using Hugging Face and PyTorch, you might notice that there's not so much difference from what you do in usual model training using GPUs. All you need to do a few things. First one is import TorchX array, as shown on the top. And then, as usual, you got to instantiate your models, PyTorch models, and prepare training groups. In the training groups, we have probably unfamiliar lines called XM, mark steps, which tells XArray to compile the graph to optimize its performance. And during training, you just need to optimize the steps to do the backward computation and update your network. All of them can be done in this manner. So that's essentially the brief explanation of the models. But if you want to train a PyTorch model in a more naive way, you can do them as well. So in that situation, you got the needs to instantiate XM device and transfer your PyTorch models and the tensors which will be put into training steps into XM devices, just like what you do in your training with your GPU devices. Sorry, it doesn't go to the next slide. Excuse me? Yeah, no questions. Yeah, of course. So yeah, that's about it. Thanks so much.
Hey folks, nice to meet everyone, both in person and online. My name is Hagai. I lead engineering at Mosaic ML, and I'm going to spend the next 10 minutes or so introducing you to Mosaic ML Composer and how you can use it to supercharge your PyTorch training. Today, thanks to the amazing AI community and thanks to fantastic tools like PyTorch, AI is everywhere and it's powering our day-to-day lives in many ways, from personalized recommendations through voice assistants and up to novel applications such as autonomous vehicles and AI-powered drug discovery. Now, as AI supports a growing number of use cases, it needs to become more intelligent. And this growth in intelligence is achieved through a growth in both the model complexity as well as the scale of the training data. Now, the table shown here shows how model sizes have been trending for state-of-the-art language models over the past 4 years or so. And if you take a look at the trend line that just showed up here, and mind you, the y-axis is log scale, it's very clear that you're looking at exponential growth in model sizes. And the reality is that this growth is actually not showing signs of slowing down just yet. Now, Mosaic ML was founded a couple of years ago to address this very challenge of growing AI complexity. Our mission is making machine learning training efficient for everyone, and it's a very relevant challenge given the growth in complexity that we just discussed. This is Team Mosaic ML in our San Francisco Dogpatch office. It's an incredible team, and I'm honored to be part of that team. And a lot of what I'm going to talk to you about is actually the work of this fantastic team. Now, let's cut to the chase and introduce you to Mosaic ML Composer. So Composer is a Python library. It's built on top of PyTorch, and the purpose of Composer is training neural networks. It enables higher accuracy, faster training, and overall reduces the cost of training your model. The library was developed by machine learning developers and for machine learning developers, and so it's loaded and packed with useful features. Now, this session is only 10 minutes, pretty short, so I'm going to focus on 3 main aspects of Composer: the trainer API, then training optimizations, and lastly, streaming data loading. So starting with the trainer encapsulates PyTorch's training loop. And it also bakes in support for things like multi-GPU training, multi-node training. It also allows you to customize your training using callbacks or hooks that gets called at different stages of the training. And we can actually see what this means in practice. So this is a very simple example of using a composer trainer. Step one is you create the model class that implements the composer model interface. And you can start by just implementing 3 functions, init, forward, and loss. And basically, you're good to go. This example is simply wrapping around the standard ResNet 18 from Torch Vision. Next, you instantiate the composer trainer. And you pass in the model you just created. You pass in the standard PyTorch data loaders, PyTorch optimizer. You specify the number of epochs and the device to run on. And then you just call fit. And that's it. You let composer handle the training loop and all of that complexity. Now you can kick back, allow composer and your GPUs to do the heavy lifting. Metrics are logged during training, and you can check them in your console. Or composer integrates really well with tools like weights and biases or CometML, and you can check your metrics there. And once training is done, you can look up your torch metrics in the trainer state object, as you can see here. Sweet. Moving on to applying training optimizations. Now, Composer packs more than 20 built-in optimizations to speed up training. And what's awesome is that these optimizations, each is fairly complex algorithmically, but you can very easily apply them and even compose multiple optimizations together. Let's see how it looks like. You first instantiate the optimizations you wish to apply. All of Composer optimizations reside under composer.algorithms. And in this code example, we instantiate progressive resize, blur pool, and label smoothing. And just these 3, if you use them, you're actually going to see really good speedups with models such as ResNet. Now, there are dedicated docs within Composer for each one of these optimizations, pointing at the research papers and giving you a lot of insight into how the algorithms actually work. Now, just like before, you instantiate the trainer object, and now you also pass in the list of algorithms that you instantiated just in the previous step, and that's it. You call trainer.fit, and Composer handles all of the nitty-gritty details of applying the optimization during training. And last but not least, streaming data loading. So this capability enables you to stream your training data from the cloud, freeing you from the need to download and manage data on the local storage. Now, for those that ever trained large-scale language models, you know that is a painful and time-consuming process that basically streaming data loading saves for you. And what's really cool is that this feature is implemented as a drop-in replacement for PyTorch iterable dataset. Let's see what this looks like. So step one is converting the data set into a supported format that allows the streaming engine to index the data and stream it over. And you can use the MDS writer class to generate the streaming data set. Next, you upload the data set to your favorite cloud storage. In this example, just shows using AWS S3, but of course you can use whatever cloud storage you would like. The streaming engine will know how to read from most cloud vendors. Now, once you did this, you instantiate the standard PyTorch data loader, and you provide an instance of streaming.dataset, which by itself extends PyTorch iterable dataset. And last but not least, you instantiate the trainer, you provide a data loader instance, you call fit, and you kick back while training data is actually streamed from the cloud. Once you created that streaming data set in your cloud bucket, you can stream it for multiple training jobs without the need to always download the data locally and manage it there. Sweet. So with all of that, how fast can you actually go with Composer? I mentioned the optimizations earlier. This is a mosaic of the different optimizations that are supported. We call these optimizations sometimes speed-up methods, and they're available on Composer today, and more optimizations are regularly implemented. Now, many of these are highly complex algorithmically, and again, the nice thing about Composer is that it encapsulates all of that complexity, so you don't have to worry about it, and you can very easily apply it to make sure your model trains fast and efficiently. Let's look at some concrete results of what was achieved with these optimizations. Using Composer to train ResNet 50 with a set of Composer optimizations deliver a 4.4x speedup on training speed running on 8 A100 GPUs. And this result was actually submitted to MLPerf and was actually faster than NVIDIA's own highly optimized training, which was also submitted to MLPerf. Moving to NLP, applying composer optimization sped up BERT large training by 2.7x, again on 8 A100 GPUs. And again, this result was also submitted to MLPerf and was actually faster than all other BERT large submissions on 8 A100 GPUs. In fact, it was more than 2 times faster than the second best result. So these results are impressive, and just think about how quickly you can iterate on exploring new models, new ideas by using Composer. If you're curious to learn more, check out Composer on GitHub, take a look at our docs, join the Composer community, and let us know what you think. We really would love to hear from you and are really into helping people adopt Composer and benefit from it. Thanks for tuning in. I really enjoyed this session and hope you did as well. Thank you.
Hi, good afternoon. My name is Kulin, and I lead the PyTorch MPS backend development at Apple. Today, I will talk about GPU-accelerated PyTorch training using MPS backend on Mac platforms. So to start off with, I'll provide an overview of the software stack we have. Then I'll discuss some of the optimizations we have made in the backend and provide some pointers to debug issues. And finally, I will go over some results and things which we are working on. So let's get started. Earlier this year, we introduced Metal acceleration in PyTorch, working closely with the core team. So special shout out to Alvin, Nikita, Edward, and other core members. It was really helpful to help design and implement this. So let's talk a little bit about our MPS backend and software components it relies on. Metal is the GPU programming API on Apple platforms. Metal performance shaders is a collection of high-performance GPU primitives for various fields like image processing, linear algebra, ray tracing, and of course, machine learning. These Metal kernels are optimized to provide the best performance on all of our platforms. Now, sitting on top of it is our Metal performance shaders graph, which is a general-purpose compute graph for GPUs. It extends support to multidimensional tensors. Also, it has compiler technology to allow us to do various optimizations, such as operator fusion, constant folding, dead code elimination, and many more. PyTorch MPS backend implements both the operation kernels and the runtime framework, which calls into MPS graph, MPS, and our Metal frameworks. This enables PyTorch to use highly efficient kernels from MPS along with Metal's command queues, command buffers, and synchronization primitives. Operations in PyTorch will create unique graphs which will be cached, which reduces the CPU overhead. And these operations are then encoded onto stream, which I'll just discuss later. For more details, you can refer to our WWDC talk from earlier this year of acceleration on Metal, acceleration ML with Metal. Now let's take a closer look at some of the runtime components we have in MPS backend. To start off with, we have a simple device class which does discovery of available Metal devices and selects the best GPU device for you. Then we have this stream abstraction, which basically is how we implement using our Metal's command queue and the last active command buffer, which is used to encode all the work onto. And then we have our allocator, which uses Metal heaps and automatic hazard tracking and similar heuristics which are used by other GPU backends. We have added GPU acceleration for a variety of operations. Currently, our MPS backend supports over 246 operations, and many more are being actively worked on. we are really excited to engage with the PyTorch developer community. Since our release in prototype phase, we have had a lot of GitHub issues. 149 of these we have been fixed so far, and we are actively working on resolving the rest. It's a very fast-moving field, so we are trying to engage with them as fast as we can. For unsupported operations, there was a lot of interest in contributing to our backend. It only took a couple of days for PyTorch developer community to pick up all the filed issues, and there have been 30 operations which have been added so far. There have been 46 pull requests just have been created and successfully merged by developers at large. And we are really excited to have you guys contribute. So please send the issues, PRs. Now I'll discuss some of the optimizations we have made in the MPS backend and debugging tricks. As you very well know, PyTorch uses a tensor to be a view of an existing tensor, which shares the same underlying storage. And this allows you to do a lot of operations and represent computation. Now let's take a simple example of a slice operation on a random tensor. Now this creates a view operation in our MPS backend, which is implemented using a gather-scatter approach. The graph takes input sizes, strides offset of an S-threaded operation, and creates an index tensor. And this on which we actually perform a gather operation. The execution of the graph and the materialization of the data happens on the following operation, which uses the gather output. Similarly, the scatter graph takes care of our in-place view operations. For more details, you can refer to our wiki page in the resource section, which I'll go over. The gather-scatter graphs can be expensive for common view operations. To address this, we have remapped some of these operations to the existing MPS graph API. Now let's discuss the commit and continue, which we have added to our MPS backend. PyTorch relies on dispatching work to the GPU for each operation. Consider a network with a simple batch run op. The op consists of 2 reduction kernels for mean and variance, and then you have 11 bytes kernels. With no commit and continue, which is at the top of the timeline, you can say, what will happen is the entire op will be encoded on a single metal command buffer on the CPU. And this then will be dispatched to the GPU. Now, you can see this empty block on the GPU timeline. That's what the idle time in GPU refers to. With commit and continue, which you can see on the bottom, we are able to parallelize the CPU and GPU work. The way it does this is, as you can see that while the reduction kernel for mean op is running on the GPU, the CPU encoding work for variance and element-wise operations has been started. Furthermore, the backend has heuristics to ensure that a new command buffer is not created for each kernel dispatch, and that reduces the driver overhead. Now I'll provide some pointers which I found helpful for debugging while developing on the MPS backend. I know this is a new stack, so I just wanted to have some pointers there, and we'll continue to work on updating our wiki page with this. So op development, when you're writing an operation with our MPS graph API, it can be useful to dump the underlying graph for more details and introspection. And the code actually allows you to do that. If you run into crash or hang coming from our OS frameworks, such as Metal or MPS graph, please file a bug using Feedback Assistant. Moreover, console app on Mac is quite useful to get more information on backtraces, spin dumps, and logs. So please use that. On memory side, there are good command line tools such as leak, heap, and footprint. It allows you to do a detailed memory analysis. And we will provide more details on this on our wiki page. Now let's look at some of the performance results. The chart shows the speed up of using MPS backend as compared to CPU. Here, the baseline CPU is 1. The numbers were collected on M1 Ultra with the latest 1.13 release. We used the Torchbench on a variety of networks to collect this. We have seen good speed ups across different networks, up to 64 times faster on some, and on an average of 10x faster. Now, I want to spend some time on what we are currently focusing on and what are things which we want to focus on in the near future. MPS backend is currently in prototype phase. Working with PyTorch team, we are identifying the criteria to qualify for the beta phase, and that's our primary focus. We want to make it stable and be able to run as many operations as possible with good correctness and performance. Also, we are trying to expand our op coverage using some of the feedback we have gotten on a GitHub issue, which is listed here. Encouraged by the adoption of MPS backend for stable diffusion, we have noticed we would like to work with model developers to enable even more ML workflows on Mac platforms. Apart from this, we would like to hear from you and gather feedback. Here are some of the resources we have, which I have covered over the, in our talk right now. And thank you. Thanks for inviting me here and giving this opportunity to speak to you guys. We are really excited to be working on our MPS backend and looking forward to giving you the best experience on Apple platforms. Thank you.
Hi everyone, I'm Sylvain.
And I'm Lysander.
And today we're going to talk to you about how to run a very large language model on consumer hardware. And so deep learning models, especially language models, are becoming larger and larger. And for instance, Big Science Bloom and Pythae's OPT are 176 billion parameters. And it can be a bit painful to run them on a small setup. At Hugging Face, we're committed to make machine learning more accessible, which also means making those super large models as easy to run as possible. You might know the Transformers library. I think it was in 1 or 2 talks today, which allows you to quickly download and use more than 60,000 checkpoints for 160 architectures. And for instance, here is all the necessary code you need to run BERT. And here is all the necessary code you need to run Bloom. Except that you're going to need 350 gigabytes of RAM if you're using FP16, or 700 gigabytes of RAM if you're using full precision. And so that code might crash, for example, on my machine, which has a limited amount of RAM and only 488 gigabytes of GPU memory. So we might need a couple more adjustments. We chose this setup with 2 GPUs and a lot of CPU RAM for the demo on purpose, to demonstrate how you can run a model with a mix of model parallelism, CPU offload, and disk offload. It would work the same way with just 1 GPU, as the main requirement is to have enough disk memory to host several checkpoints. So here is how you need to adapt your code so that it can run on my machine. It can also run on the cluster that trained Bloom, on a couple of GPUs in the cloud, or my machine, just 1 GPU, as long as you have enough memory to host the whole checkpoint. And even if you don't have enough GPU or CPU memory to host the whole model.
And so the traditional workflow when loading a model in PyTorch is that you first start by initializing a model with random weights, and then you load the checkpoints in memory. Once you have this checkpoint loaded in memory, you take this and you put it inside the randomly initialized checkpoint. However, with Bloom, that weighs 350 gigabytes in FP16, well, this doesn't really work on a traditional system with 32 gigabytes of RAM. As soon as you randomly initialize the model, then you're running out of RAM. And then when you load the checkpoint's weight, well, then you're at 700 gigabytes, and then this just doesn't really work. In terms of comparison, loading ImageNet, like the training set of ImageNet preprocessed with images of 224 by 224, is about 700 gigabytes, so it's quite a bit. Like when compared to BERT, for example, it's about 400 megabytes, so you can definitely do this workflow. So here we're using a neat little trick introduced in PyTorch 1.9. Here is a regular tensor which contains several attributes, including the shape, the d-type, and the data being the core of it all. But in PyTorch 1.9, they introduced the meta tensor, which is about the same, except you don't load the data. So here it takes no space, and it's extremely fast to load. And so that's exactly what we're doing here. We're importing the initEmptyWaits method from Accelerate, using it as a context manager. And when we load the model within that context manager, what's really happening under the hood is that we're basically loading all the weights on the meta device. And so as you can see below, the current RAM used is 0, because we're not loading any data. There's still the issue of the checkpoints weight being too much, and I'll let Sylvain explain how we handle that.
And so that's why in transformers, we've implemented checkpoint sharding. Instead of having this whole 350 gigabyte file which contains all the weights, let's split it in smaller files, and each file contains just a few layers weights. But if you try to load all those weights inside your model, you're still going to hit the same problem. So you need to decide in advance where you're going to load everything. To use the GPU space as much as possible, then the CPU, and then leave on the disk what doesn't fit. And so that's where, so here is the whole model with all the layers, and that's where having this meta tensor is super useful. Because we already know the shape and the d-type. Even if we don't have any data, we can still do the multiplication shape by d-type and know how much memory it's going to take. And with that, we're able to decide, for instance, here that the embeddings on layer 1 are going to go on the first GPU, then layer 2 to 4 on the second GPU, then we go off to the CPU because we don't have any space, and we leave the rest on the disk. This is what the device map equal auto argument meant in the code that we showed you earlier. So you can set it to a proper device map. You can decide, I'm going to put the embeddings on that device, the layer 0 on that device, or you can let Accelerate decide for you. The advantage of letting Accelerate decide for you, it's going to adapt itself to your setup. So if you have lots of GPUs, it's going to use them all. If you have just one GPU but a lot of CPU RAM, it's going to maximize the memory of your GPU and then use the CPU. Or if you're like my machine with a little bit of GPU, a little bit of CPU, it's going to fill that and then leave the rest on the disk. And so then it's just a game of going over all the checkpoint charts and load all the weights right on the device that we decided that we're going on. This way, you don't get out of RAM while it's loading the model. And once you're done iterating, you have a model that looks a little bit like this, split between GPU 0, GPU 1, CPU, and all the disk.
And so once you have this model loaded over many different devices, the question that arises is, how do you handle the inputs and how do you propagate those through devices? And so here we first start by putting the inputs on the first device, so the first GPU, that contains the embeddings and the first layer. As you'll see, it has some space available. It has 20 out of 24 gigabytes taken, and we'll see in a bit why is that exactly. So we first propagate the inputs through the layers hosted on this first GPU, and get the hidden states that we then put on the second GPU to be passed through the subsequent layers. So we pass them through layer 2, 3, and 4, and then comes layer 5. Layer 5 is currently hosted on CPU, which is way less efficient than just doing the operation on GPU. So what we're doing then is going back to the first GPU, but putting the fifth layer directly on that GPU to perform the operations. Once we're done performing the operations there, we drop the fifth layer, load the sixth layer directly within this GPU as well. And so the same process happens for the disk. However, disks are like loading a layer from the disk to GPU takes more time, of course, than loading it from CPU to GPU. So we'd rather put everything on CPU, but we don't all have the luxury of a 700 gigabyte machine. So we load all the layers hosted on disk down to the decoder until we reach the last layer of the model. So how does this look in practice? How does this look in code, given all the context switching and all the device switching? So first, we're going to start by instantiating the model, as we have seen before with the device map equals auto, which spreads the layers on the different devices automatically. Then we add the offload stack dict equals true. This is a parameter just for safety to ensure that we're not blowing up the RAM. It takes a bit more time to instantiate the model, but this way we're sure we're not running out of RAM. Finally, we specify the torch d-type Torch Float 16, as we don't want 700 gigabytes to be taken for the model. 350 is much more than enough. And so what the full inference looks like is we first have the model initialization. We then load the tokenizer, the appropriate tokenizer, and we tokenize a question. Here it's question, can I run Bloom on a single GPU? Answer, and we want to predict the next token. So we encode that, and here we have the single line that is device specific. We pass this on the first GPU, so 2.0. Then we perform inference. There's no device specific code here. It's all handled within the model by the hooks that we have put inside according to the different devices. And then we retrieve the last token, do the argmax on it, and decode it. In total, it took 2 minutes and 24 seconds to load the model, which is 300 gigabytes, once again, on a very small machine. The inference took 1 minute and 50, which is non-negligible, but at least it runs. And the answer that the model printed is yes.
And so, as I said before, that same code runs on any kind of setups that you might have. So here is a bit of a comparison across multiple setups. So obviously, if you have enough GPU space towards the whole model, it's going to run faster. So on 8 A100s with 80 gigabit of RAM, you can have the whole 350 gigabytes of the model on GPUs, and it takes 230 milliseconds to run a full forward pass. And since you have a lot of GPU memory on this setup, you can even use a bigger batch size and go to batch size equal 32 before you go out of RAM. And this way, you have an inference that goes at 10 milliseconds per token. Then, if you don't have enough GPU space, obviously, it's going to take a bit longer because you have all these layers created on the CPU that you're going to need to put one by one as we go through the forward pass. And so as we go through smaller and smaller setups, we can see that the more layer of loading on CPUs or the disk, the longer the inference gets. And one thing that's very important if you're looking at smaller setups is the I/O speed between the disk and the CPU or GPU. And as you can see, my machine, which is smaller than 2 A100s on GCP, for instance, still goes way faster because it has an NVMe. And so going from the disk to the GPU goes actually super fast. And that's all we had for you. Thanks a lot for listening to us, and we hope we find our tools useful when playing with large language models.
Thank you.
Thank you.
Hi, my name is Zain Rizvi. I'm a tech lead on the PyTorch developer infrastructure team. Our goal is to build tools that make it as easy as possible for PyTorch contributors across the entire open source community to contribute to PyTorch. So, why contribute? Since you're listening to this talk, chances are you're either a user of PyTorch, you integrate PyTorch into your existing systems, or you build a product that your customers use with PyTorch. Oh, could you go back one slide, please? If you're a PyTorch user, you might be wishing that your tool is better in some way. Maybe you're running into pain points, or you're wishing that PyTorch scaled better to your workflows. You might have an idea to how to optimize transformers even better. You have the power to change your tool to make it better suit your needs. And by doing so, not only will you be scratching your own itch, you're going to be improving the state of the art for the AI industry. If your customers use PyTorch, you can evolve PyTorch to optimize it for your product. Companies like NVIDIA, AMD, Microsoft, Intel, they all regularly make contributions to the PyTorch code base to make it more performant on their platforms. And by doing so, they give their customers a much better experience. So, you have an idea. Let's get some feedback on it. Our early feedback process is designed to make it as easy as possible for you to quickly find out how well your idea lines up with PyTorch's vision. And if need be, to help you tweak your ideas a bit to make them something that the PyTorch community will be excited to adopt. Now, we want this process to be as easy as possible for you. And sometimes that means just jumping straight into a pull requests. This is the case for smaller changes like bug fixes or documentation improvements. For anything that's a simpler feature, perhaps, you can file an issue on GitHub. Those are good for, you just share the change that you want to make, mention the benefits that you're expecting to get, and share that you're willing to implement the idea yourself. We'll get back to you really fast on that. And for the more involved proposals, you can submit a request for comments. This is good for things that are like more detailed, and it'll allow the PyTorch members to give your ideas the more thoughtful and detailed feedback that they deserve. All right, you've had your idea. You read our contributing.md guide to figure out how to build and test PyTorch locally. You start developing. Awesome. And then you get stuck. We have a whole bunch of ways for you to get unblocked. We have a couple forums. There's discuss.pytorch.org, which is for PyTorch users, but you can use it to also figure out or better understand our APIs. And then we have DevDiscuss, which is a special forum for PyTorch contributors like yourselves. If you encounter bugs, you can file an issue on GitHub, and also do that if you find instructions are confusing or vague. If you have an idea for how to better improve your workflow, to make it easier to contribute, you can also file a GitHub issue for that, or you could bring it to our office hours. The Dev Experience office hours is an open-ended forum where you can talk about anything related to your developer experience. You can talk about roadblocks that you're running into, requests that you might have, and if you've ever been curious about how a particular piece of infrastructure works over here, you can even come and ask us about that. We're always excited to help explain it. Now, you've gotten yourself unblocked, you've built out the feature, and you're ready, you've tested it, and you're ready to get it merged. Now, the fastest way to make that happen is to submit a PR and assign it to the right reviewer. But how do you know who the right reviewer even is? If you'd gone through the approval process earlier, the feedback process, then you can assign it to the person who gave you some feedback. Or you can check out the list of maintainers and find one that owns the area that's responsible, that's affected by your changes. And if none of those options help out, it's okay, no big deal. Just leave the reviewer section on the PR blank, mark your PR as being ready for review, and within a couple business days, our PyTorch triad squad, our peer triad squad, will take a look at your PR and assign to the right person. It takes a little bit longer that way, but we'll make sure your PR gets attention. Now, once you've gotten more ramped up on the PyTorch code base, we've got a couple more perks that you can make your lives even easier with. We have a Slack workspace that you can join us on. It's useful to have even faster collaboration with the core PyTorch maintainers, the people who are more invested in the PyTorch community. You can even become a maintainer yourself. We're always looking out for strong contributors who have expertise in a given area, who can take ownership of it. Anyone, anywhere in the world is eligible to become a PyTorch maintainer. And finally, the Dev Experience office hours are open to everyone, from beginners to novices. Everyone is welcome. Now, let's talk about some of the tools that we've built. There's the HUD, which is a site which gives you a lot of information about the PyTorch repositories and the commits that have been made. And one of the big use cases that you might find it helpful for is those times when you have a test that's failing on your PR, and it doesn't quite seem like it's related to your changes. You can hop onto HUD, take a peek to see if this failure you're seeing, if it's a symptom of some more widespread outage. Or you might discover that you should take a closer look at your code. Then there's Docker CI, which is a GitHub bot, which provides a comment at the top of your PR, and it lets you just find out what the current status of the CI is. That's the lower screenshot over there. You can see how many tests are still pending, and if anything has already failed, you can get a link to quickly dive into there and debug it. Then there's MergeBot, another GitHub bot, which lets us apply custom rules during merges and reverts. It's useful for things like fine-grained permissions checks, or making sure that we run extra tests just before we merge your change into GitHub. Then there's also Flaky TestBot, which is exactly what it sounds like. It automatically detects and disables tests that are flaky. Now, this is a lot of stuff to remember. If you want one link to remember all of this information, let it be this one. You can remember that, right? Or you can search for PyTorch Contribution Guide. It's going to be the first link on the results. And this will give you everything that you need to get ramped up as a PyTorch contributor. Now, if you have any questions, feel free to reach out to the PyTorch team at any of the resources that were mentioned earlier, or you can reach out to me personally on Twitter at ZaneRZV, and I'll be happy to help you out. Thank you very much, and have a great day.
Well, thank you to Zane and to all of our partners. We wouldn't be where we are today without our community partners and our ecosystem partners building for PyTorch. And we encourage everyone to contribute. So we'll take a 10-minute break, and then we'll be back to talk about the future of PyTorch. Thank you.
Hello, everybody. If you could please make your way back to the main room, we will continue our session. Thank you.
Hey everybody, I'm Chris Mattman. I am the Chief Technology and Innovation Officer at the NASA Jet Propulsion Laboratory. I'm so happy to be with you all here today. I'm here to talk to you about some of the really cool applications that we're leveraging PyTorch for, and just in general, how we're using machine learning really to kind of explore deep space, to explore Mars, to look at things like supply chain, deep space telecommunications, infrastructure, and other things. So I am here on Mars, so that's sort of what's behind me. We've got a couple of really fancy, amazing rovers that are on Mars, including the Mars 2020 rover, which is also known as Perseverance. There's an associated helicopter with that called Ingenuity. What's really cool about these rovers is that they're looking for the origin of life on other planets, including Mars. They've got experiments on them like MOXIE that's trying to generate oxygen on the Martian atmosphere. They're looking at particulates and whether or not there's any organic life on Mars and so on. And Ingenuity itself is really amazing. It's got a tech demo. What it's looking at is, can it be a scout for future Mars rovers guiding us on our path towards science discovery? And it's went well beyond the tech demonstration elements. It's had 30 plus successful flights and a Wright brothers moment already on Mars. One of the challenges that we have with Mars in general is that it's really far away. Mars, depending on the configuration of the Earth and so forth, is between 8 to 20 minutes round trip light time from the Earth to Mars to send a message there and get a message back. And that's a very, very thin pipe. And as it turns out, because of that, the rover planners, the humans that help command and direct the rover where to go, and so forth, only are able to use a couple hundred images a day to basically decide where the rover should go the next day. Coupled along with this, the rovers on them, don't have all of the capacious computing and really excellent GPUs that we have here on planet to do all of that amazing PyTorch and machine learning computation. As it turns out, the rovers have on them, as well as most hardware in space, what we call a RAD 750, or the equivalent of an iPhone 1 processor. Why? Well, because of cosmic radiation. And so because of that, we're forced to use a lot older processors. In the future, we will have that GPU machine learning type of processor on board. And in that future, what could we do? Instead of sending 200 images back a day to decide what to do the next day, we could run a PyTorch model on board, on surface, something like a neural image caption generator like show and tell, and things like that, to look at an image and give us back a text caption. And what if instead of 200 images a day, I could send back 1 million captions to basically decide what to do the next day? Because text is a lot cheaper to send over that thin pipe than an image is. We've been building and building out these algorithms and testing them, and that's really where PyTorch is kind of coming in and really benefiting all of our work. We're building these models in PyTorch, basically things that combine object detection and CNNs with LSTMs, which are long short-term memory, and RNN, or recurrent neural network models, that combine the objects that you see with the language models, those bidirectional models that you need to map those objects to different parts of the language. Again, cardinality, how many, how far away, and things like that. And so finally, the last sort of call to action I just want to kind of make to all of you is this wouldn't be possible without open source. It wouldn't be possible without the efforts that your community are doing, both to build a framework that we can take, modify, update, build models, share them with our partners, and so on and so forth, but also the data sets themselves, existing data sets that are published into PyTorch and models that we can use, share, reuse, build on top of. It would not be possible without all the work that you and the community is doing. So I want to encourage you at the conference to know that you're directly contributing to these efforts. I want to thank you for everything that you're doing, and I want you to get excited, hopefully, about all of the connections that you're making and the potential for your contributions to space. So thank you so much.
Hi, everyone. Good afternoon. I hope you're having a great conference today. My name is Ibrahim Haddad, and I'm the Executive Director of the LFAI and Data Foundation, and as recently as September, the PyTorch Foundation as well. So I work for the Linux Foundation in support of the PyTorch Foundation, and I have here with me in this event a number of my Linux Foundation colleagues. Can you please raise your hand so folks can see you? So there's Tim, Kylie, Cadence, and Jacqueline. We work for the Linux Foundation in enabling and supporting the PyTorch project and the PyTorch community. So if you'd like to talk to us, please find us and let's chat. So one of the very interesting things for us at the Linux Foundation was tracking the open source AI and data ecosystem. And we started doing this via our landscape, which you see on the screen. It's interactive, available online. And when we started this exercise, in early 2018, we only had about 60, 65 projects on the landscape, capturing the key projects in the ecosystem. Fast forward 4 years, we have over 330 projects representing the work of over 40,000 developers that are consistently contributing to these projects and producing, as of today, over 500 million lines of code. And every week, we have 1 new million line of code being added to that ecosystem. So it's very thriving and very active ecosystem. However, there are some challenges, such as integration across projects, such as governance-related challenges, challenges in relation to integration with projects and cross-pollination across these different projects from the developer perspective. And this is how our investment at the Linux Foundation started with LF Deep Learning. In 2018, we announced the establishment of LF Deep Learning, which we rebranded to LF AI and Data later on to project an expanded scope. And today, I'm very happy to announce that we have 51 members. Our developer community is over 18,000 active developers contributing to our projects that consist of 45 projects and growing by 1 project every month. So again, 18,000 developers, and we doubled our developers working in the projects in about 2 years since December of 2020. And this leads us to PyTorch and the PyTorch Foundation, where we've been in discussion with Meta about the PyTorch project as being kind of a key project, moving it into a neutral organization under an open governance. And on September 13, Meta announced the decision to move the PyTorch project into the Linux Foundation under its own umbrella foundation called the PyTorch Foundation, right? And that was really a major milestone for the project, or is a major milestone of the project, thanks to major efforts from Meta as staff and leadership, and the support of several of the organizations that became founding members of the PyTorch Foundation that you can see on the screen. And that signals really 2 main things. The first one is really a massive commitment to open source and open governance from Meta and the founding members of PyTorch Foundation. And the second one is increased funding and increased investment in open source AI, not just from the founding members of the PyTorch Foundation, but also from the Linux Foundation, as the Linux Foundation is also contributing funds and resources in support of the PyTorch project and the PyTorch Foundation. And one interesting thing that I will touch upon now to address some of the questions that we frequently get, but it's also addressed following in the panel that you can see the chair here for, is the governance. So basically, there are 2 types of governance here that are separated. The first one is the business governance, which is the governance of the PyTorch Foundation, how the PyTorch Foundation works, how decisions happen. And the way I look at this is the PyTorch Foundation, or the business governance, is basically the funding governance. This is how we gather funding to spend on the project, right? This is how we will be sponsoring our events, our marketing efforts, our communication efforts. This is how we will pay for the infrastructure, for a lot of activities that happen in support of the project. And there is the technical governance of the project, which is how technical decisions are being made, decisions about the roadmap, about the features, et cetera. And this remains as is. It is managed by the project, and there's really no interference between the PyTorch Foundation and how the project runs. And I think this topic is going to be covered in the next talk in deep details. Now, with respect to what the Linux Foundation will be supporting the project with, I have on the screen, as you can see behind me, a number of areas, not just in terms of implementing an open governance for the project and moving it into the foundation and having the foundation manage its assets, but it's also in relation to a number of other activities. We will be providing marketing, PR, communication services. We have a dedicated staff that will enable and support the project in many areas, such as events. So starting next year, we will be setting up this event, managing it, in addition to a host of other smaller events that targets developers. We will be responsible for all legal aspects, including managing the trademark, export control filing, license compliance scans, et cetera, and really a host of services that are available to the community and to the project itself. And one of these services is, as you see on the screen, is the LFX platform. And I have a slide on this coming up. LFX platform is basically a suite of services. It's a Linux Foundation product. We actually developed this platform. And as of today, it provides 11 different tools available for open source projects to use. And we've already successfully onboarded the PyTorch project on this platform. We have LFX Insight, security services, CLA services, and many others that are already available in support of the PyTorch project. And what I would like to do is actually invite you to subscribe to get a Linux Foundation ID, which is kind of a Linux ID that allows you to access the LFX platform and will be kind of your entry to everything that the Linux Foundation offers. And once you log in, just search in for PyTorch, and you will have access to really amazing statistics about the project and a host of number of tools and utilities that you can use in learning about the project, and a lot of things that you can actually download and integrate as part of your presentations talking about the project. Our immediate priorities as a foundation are three, as you can see on the screen. The first one is smooth transition of the project assets. So the project has been founded by Meta, and it's been managed by Meta and some of its partners for the past 6-7 years. And one of the things we're doing as the project moves into a neutral organization is to transfer all these assets to be owned by the PyTorch Foundation itself. So a lot of that has been happening, a lot of it has been completed, and we still have a few items that are in flight, just given the long history of the project with its founding organization. The second priority is hiring the staff that will be dedicated in support of the PyTorch Foundation. So this is completed as of now. We've hired 2 full-time resources. So Candice Gulhiri, who's sitting here, she's dedicated to everything marketing, communication, and PR in support of the PyTorch project. And Lucy Hyde, she's actually not attending here, but she's attending remotely. She's a project manager in dedication for the support of the PyTorch project. She's also a PyTorch user, and she's been a data scientist, so she has deep understanding of the project to help support and enable it as well. And the last priority we have is really, and we're getting there, is getting the foundation into a stable operation. So the foundation was announced in September. We hired the staff. We're moving and transferring the assets from Meta into the PyTorch Foundation. And we're looking at the beginning of the year to start as fully functioning foundation with its own staff and its own internal processes and operation. In terms of long-term operation, and that's really looking into 2023 and beyond, we have a lot of things that we're working on. What you see on the screen is just kind of a high-level summary. And what I can share with you at this point is we're looking at 5 different areas where we're looking to support the project. The first one is, or the first bucket or area is focused on developers. You know, how can we enable developers with additional tooling, documentation? How can we increase the number of contributors into the project? How can we increase the contributions from existing developers, you know, et cetera? So developer focused. The second area is in relation to marketing, communication, and events, and that targets promoting the project and creating additional events in addition to the PyTorch events, and there's really a whole list of things within that category. The third area of priority is in relation to enterprise adoption, and that basically focuses on programs and initiatives to have more organizations adopt the project and more organizations contribute to the project. Fourth area is training and certification, and we've already launched and made available 2 training courses on PyTorch, and we have a number of courses that are being designed right now. So if you are a developer who's available and willing to contribute to the design and implementation and making available technical training courses about PyTorch, please talk with Tim. He's sitting back there. He's the director of training and certification at the Linux Foundation and working with a number of developers on building curriculum that will make available via the edX platform to further provide technical training on the PyTorch project. And the fifth area of focus is academia and research. As you know, there's really a deep history between PyTorch as a project and academia and universities, and we want to expand on this. We want to have PyTorch even used more within academia and academic R&D labs. And that includes mentorship program and internship programs and many other programs that we're building. This is just kind of a highlight, as I only have about 5 minutes to share with you all of this information. As you can tell, there's really a lot happening, and we are at the Linux Foundation super excited with the project. We've been trying to get PyTorch to move the foundation for such a long time, and finally happened. So it's a great complement to a lot of the AI programs and data-related programs that we have. As you can see, we have 5 or 6 people here focused on helping and transitioning the project and supporting it. And my email is on the screen, so please feel free to reach out to me by email. And I'm available until the end of the event today, as well as my other colleagues from the foundation. So feel free to grab us and talk to us, and let's see how we can collaborate together. With that, next is a discussion on the PyTorch project and the PyTorch Foundation, and I will leave you with that. Thank you very much.
Today, we have a panel of PyTorch maintainers to tell us a bit more about PyTorch 2.0 and how to contribute to PyTorch also. So I'll start with some introductions first. We have Nikita Shulga, who's a tech lead and maintainer of PyTorch, including coverage of the platform support, continuous integration, developer tooling, and best practices. He drove the GitHub first and internal release process at Meta, which unblocked external maintainers to contribute to code on GitHub. We also have Natalia Gilmeshane, a core team lead, expert on PyTorch, including long-term focus on NVIDIA GPUs, performance, profiling, and the new PrimTorch, inductor, and some other parts of 2.0. Then we have Orion Riblitz-Richardson. He supports the PyTorch developer infrastructure at Meta, and he's looking at ways to empower the community and core teams to move forward on 2.0, including the launch of the PyTorch Foundation and increased investments on our technical governance. And finally, we have Peng Wu, who supports the PyTorch compiler team at Meta. Our team, with some partners, have built many of the key components of 2.0, including the Torch Dynamo graph capture and Torch Inductor backend. So thank you for being here with us today. So first, what is my code doing differently when running 2.0 compared to 1.x? Natalia.
So this has been covered in a lot more details in the presentations this morning, but very briefly, when we are running the program with PyTorch 2.0, first Torch Dynamo acquires the trace of the program in a sound way. Then it is sent to AOT dispatch to trace through the backwards, and then the obtained trace of forward and backward computations is passed on to compilers that are generating efficient code. And that pretty much leads to user experience where you can run your programs as you wrote them with minimal changes and get a better performance through generated efficient code.
Thank you. But I want to get started with 2.0. Like, how do I install it, and are there any additional requirements?
So there is no real additional requirement. So 2.0 is not yet ready, but we have the features that was announced today available in the latest nightlist. So just go to pytorch.org website, find Getting Started guide, and just download the latest nightlist. And if something doesn't work, let us know. Because I believe there would be some.
Perfect. So then, like, I've got 1.x code, and I want to migrate it to 2.0. What do I need to do that? Natalia.
It's pretty simple, as has been shown in this morning's presentations. You just wrap the function or model that you want to optimize with torch.compile API. There are a few switches that let you fine-tune what exact compiler behavior you want to see, but the default options are expected to give you a pretty good speed up, even without fine-tuning.
All right, so I want you all to try that soon, right? Now, Peng, how does distributed training work with 2.0?
So PyTorch 2.0 right now supports FSDP and DDP APIs, but the other distributed APIs like distributed tensor or PP or tau have not been supported yet. And also with FSDP and DDP, there might be some other limitations like manual checkpointing. So, but this development is fast moving, so just keep on checking on our progress, and if you find a problem, found an issue on GitHub.
Thank you. So what should I do if my previously running code is crashing with 2.0? How do I debug it?
So, well, there are two ways of doing it. First of all, you can disable 2.0, just remove the decorator or pass an environment variable that completely disables tracing. But if you discover an issue, please report it back to us. There is a minifier tool that was mentioned earlier today. Use it to like minimize the reproducer and send it to us. It will be very interesting to see what can go wrong.
Perfect. So what are some of the challenges of supporting a broad set of models with compiler techniques?
Well, one big challenge is in the question. We want to support a broad set of models, and that means that we need to support great diversity of different operations. We need to support those operations in very different combinations and still generate the efficient code. So the way we are doing this is, first, we are reducing the number of operations that compilers need to support through the decompositions. And that way, we reduce the operator set from 2,000 operators that PyTorch supports to something much more manageable, like 200. Then we've developed our compiler with the breadth-first approach. We aim to support all or almost all of PyTorch operations. And that means that we are creating lowerings for all the classes of operations, 200 or so, that remain in the trace after this decomposition process. We are handling pointwise operations, which are really easy to handle, reductions that are slightly more complicated. We are handling indirect access operations, such as scatter and gather. We are handling implicit and explicit broadcasts, slicing views. And that gives us pretty good coverage for all the operations that we are encountering in the wide set of models. Then after this decomposition and lowering process, we actually need to generate an efficient code for the loop IR that we've obtained. And here is where our code gen backends come in. We have a nice separation of concerns where the inductor itself is handling lowering to loop level IR, and then we are offloading the code gen generation itself to establish tools that are known to do a good job of creating efficient code. In particular, that allows us in Inductor to generate much simpler and readable code and offload the performance complexities to the compiler backends that we have. People who are looking at the Triton code that we've generated usually say that it's pretty simple and readable and one can understand what's going on in the kernel. But the actual magic that would go on to turn it into a performant code that will be executed on the GPU is substantial, and it's just hidden from the view of the users. And I think that this structure with nice separation between the lowering and actual code gen is something that makes both the developer experience for Inductor better and user experience.
Thank you. Peng, this question is for you. What explorations are we allowing as backends for PyTorch 2.0?
Yeah, so I translate this as the integration points for backends to PT2. We actually have two main integration points. One is at the right after Torch Dynamo. So if you have a mature backend that can handle a lot of ops, you can integrate at that level. So basically, we hand the graph over to you, and you compile and execute. And another integration point is deeper into the stack to integrate at the Torch inductor level. This is suitable if you have a new backend and you want Inductor to take care of more of the things. And also we have a third option. If you do have a mature backend, but it only handles a subset of ops, we are experimenting with a hybrid model where Inductor handles part of it and will also offload the part that you are good at so that we can have two backends in the same place. Again, go to the blog post where we will have more description on where to integrate and when.
Great, thank you. Switching gears a little bit here, we moved to GitHub first development. And Nikita, can you tell us a little bit about this project and about PR best practices and maintainer best practices in general?
Sure. So like if you want to, what changed with GitHub first is that before that, to merge your change into the PyTorch code base, we first need to go to the internal integration at Meta. But as we move to Foundation, as we move to GitHub first, we can just allow everybody to propose a PR and allow anybody outside of Meta to become a maintainer, so be a reviewer for the change that is proposed, and landing this change without any intervention from a Meta engineers. That allows us to move much more faster and build a more diverse ecosystem.
That's a pretty big change. We're giving the power to maintainers now. So talking about how this works and governance in general, Orion, can you tell us more about the difference between the PyTorch Foundation business governance and the technical governance?
Yeah, absolutely. So in business governance, I think you heard a lot about just now around PyTorch Foundation, Linux Foundation being involved in a lot of those pieces. Technical governance really is not changing. The idea is to continue the active development we have. That being said, though, the foundation makes it so that everybody can be even more committed to open source PyTorch, right? The fact that we are in the open, we are being developed together. So that means that hopefully more companies, teams are contributing as well. So that's part of this.
Thank you. So talking about contribution again, how do we empower others to be maintainers of PyTorch at the same level as engineers of Meta?
Yeah, so the first one is actually GitHub first, as Nikita talked about. I think without that, a Meta engineer was involved in every thing that was committed to PyTorch historically. This is a big deal, but we've changed that. And so the next steps are really to put more of the things that we're working on in the open, be that release schedules, be that priorities for work streams, all these kind of things. So this is a work in progress right now, but it is what we're looking at.
Okay, thank you. And our community is what makes PyTorch strong here. And Nikita, can you tell us a bit more about submodules and how they help contribute to the PyTorch strength for the ecosystem of the community?
Sure. So like PyTorch is built sort of on the shoulders of the giants. We would not be able to build all the ecosystem if we could not rely on other great libraries that provides foundation for what we do. To give an examples, we have like basically algebra libraries. We have some quantization libraries. We have point-to-point communications between like accelerators. And we rely on all this like contributions from other people and from open source community in general to provide like a reasonable performance experience even for the eager mode. On the other hand, like we want to encourage more contributions. So if you have something that like you think that PyTorch community in general might benefit from, but you don't think it is ready for the general consumption, create a submodule, create an extension that would naturally evolve and help people like make PyTorch available in the new domains.
Thank you. So we actually have a couple of minutes for questions for the audience. If anyone has any questions, I can repeat it for everyone online. All right, so now it's like really future looking. Bit of an open-ended question here for our speakers. Beyond 2.0, towards 2.x, what are you most excited about?
I can go first.
Yeah, why don't you go first?
So I'm more excited about the kind of things that we can do with compiler that we haven't thought of, because I do feel from the first principle point of view, if we can generate more code, more kernels, there could be other use cases. So this is really open, and I trust the team is able to come up with something that's really surprising.
Yeah, just briefly, I think the thing that's been so important for PyTorch in my mind is the usability, the debuggability. So that plus performance is really what it's all about. And then platforms. Which platforms do we support?
I want to expand a little bit on Peng's answer, and I'm excited about the code gen for the new types of operations that we'll be able to implement, such as, for example, the operations on the lists of tensors that will allow us to speed up the optimizers, the sparse code gen, the code gen for nested tensors. I think that's going to make PyTorch much more valuable as a research tool.
And I'm excited about PyTorch being available on more and more platforms, right? It would be great to see PyTorch in the space and PyTorch on our watches.
Thank you. I know I'm excited the most of seeing even more contributors coming in on our platform and helping build this future together. So thank you for the panelists. A little round of applause. All right. Good.
It's been a stellar 6 years since the launch of PyTorch, and this fall we had something big to celebrate. On September 12th, PyTorch moved to a new independent PyTorch Foundation under the Linux Foundation umbrella. Let's look back at the key moments that got us here. In 2016, Meta AI researchers set out in collaboration with the AI research community to build a better framework for AI research.
We had a great project, but we always thought about partnerships and community first. And I think that was really the secret to the success of PyTorch. There's this seminal tweet by Andrej Karpathy. That was kind of this moment that woke the research community up and said, the cutting edge is going to be built on PyTorch.
In October 2018, At the inaugural PyTorch Developer Conference, PyTorch 1.0 was released, with the goal of building a unified platform for research to production.
We did a lot of scrappy work to make that one happen. And it was at this place in Dogpatch where they have raves. It was crazy. People connecting, people building stuff, coding, showing each other their Jupyter notebooks. Like, it just felt like PyTorch, right? When you think about the research community, 80+% of top conference submissions being built on PyTorch, you know, research begets research. People build on your work, and I think that the more PyTorch gained traction in the research community, the more researchers built on it, and then, you know, they created this flywheel. That was an incredible period between 2019 and 21. As a team, we're all just in awe of how fast the platform is growing, how fast the community is growing.
It's actually literally being used to further the exploration of space and the discovery about how we all got here.
Now, some 2,400 contributors have built more than 150,000 products. PyTorch has quickly become a leading platform for AI research. The future of PyTorch is an even greater collaborative community. Anyone can have a voice. Anyone can contribute to the project, from research to art. The future is open source. The future is PyTorch 2.0.
Hello, everyone. Great to be here. I'm Raziel, Media Arts and Director.
And my name is Christian. I'm a data scientist.
We are coming from Los Angeles, California. Right now, we are 15 people and speak in 15 languages and in 10 countries in a small studio, and practicing last almost 8 years using data and AI for public space, public art specifically. Our journey started as personally 14 years ago with pure data. The software opened my mind, the idea of using data as a pigment or painting with a thinking brush over the years. Our studio heavily focused on creating pieces across the world, the art for anyone, any age, and any background. So our purpose is not specifically focus on gallery or museums, but make art that are hopefully understood by the humanity. And we try to make mostly works in different orientations, focus on architectural scales, large scales, public space where there is no door or a ceiling, where there is no beginning and an end. And we try to create public experiences in the center of AI and data. But our journey is pretty much focusing on art, science, and technology, and trying to create AI, neuroscience, and architecture, and trying to understand the deep discourse and context about how humans, machines, and environments are coming together. And our pieces are in airports, such as like in SVC. We have some people miss their flights while looking at the artworks, and there are experiences in public spaces. But the whole team is generally using light as a material and trying to use expressive meaning behind information and how the technology is leading us as a humanity in a new direction. And our work also focuses on immersive environments and try to make impact through in real-time activations, and try to educate also public through understanding and explaining the algorithms behind many works you are seeing here. But I think like many creators, I was very inspired 2015 summer when this image truly transformed many of us. I'm working with computers since 8 years old, but never able to imagine that one day that this can be a tool for artists. And thanks to Blaze's team at Google, 2016 February, I started to become the first artist in residence at Google team that was allowed me and everyone at the studio, and actually Soumith's very exciting connection with DC again happened back in time. But as a studio, we focus on one idea, not necessarily deep dive into this rabbit hole, but really understand what does it mean to be a human and how we can use information, knowledge, and wisdom as a whole common theme, and how we can interact with latent space that is just kind of a critical thinking brush, I guess we can say. And over this study, what was really inspiring me, this beautiful book, story about Library of Babel by Borges, and the idea was, can we create this library of future one day that every single information may survive and every single human in the world can access? So we tried to create the very first, I think, application in 2016, create this a public library on a public data in a public space that you can go enter this room, and when you enter, you can interact with 1.7 million documents in real time. I think it was the very first time Levin of the Tail shader ever used for such a big image data. And we were able to classify this information thanks to Mike Tyka and his guidance. It was a real-time application, both in the physical space, also in the virtual space. And we were able to even like lerp between multiple different, lower dimension reduction of this archive. But we were speculating what happens if there is no search bar, and what happens if an information in a library where we learn the truth can dream. If a machine can learn, can a dream question? So I think we're just obsessed with this idea of like how we can turn information into knowledge, eventually wisdom, but how can we do it through not personal data, but using collective memories, specifically many different information. And I think that was a time, again, thanks to DC again, 6 years is AI is like 60 years, I know, but this moment was super exciting. It was the first time we were like training this moment, like getting this like latent walkthrough on the DC again, but the question was like, this is a beautiful information, but how can we turn this into a more three-dimensional pigmentation, and what else can we do with it was a much more challenging question. And I think here, thanks to Christian and many other our team members, the last 6 years was very inspiring, and we so far download more than 3 billion images and trained more than 100 AI models. And maybe Christian, please.
Yeah, so the last few years, we've been working really hard on building pipelines to visualize and explore a bunch of different data sets. Mostly we're focused on nature, culture, architecture, just other fascinating areas like that. And of course, thanks to an amazing team, and PyTorch in particular, we've been able to go from some very humble beginnings of just using VGG16 and StyleGAN, and we've been taking this from about 10,000 images, 20,000 images, and now we've scaled and trained over 100 neural networks on more than 3 billion images since 2016. We create a bunch of different tools, mostly for data visualization. So this is a bunch of graphs. We have an amazing tool called the GAN browser, which we'll show a little bit later. We work with image embeddings, we work with audio, we work with text. Really, really heavily focused on data cleaning as well. Super important for the GAN pipelines. Creating tools like that is amazing, and honestly, thanks to PyTorch, we've been able to scale this and deploy it on hundreds of cloud computers and work with people all around the world.
I think as our projects got deeper into the remembering and transmitting knowledge, and after AI, we thought more about how memories, in this case, collective memories, which is like the leftover, I guess, memories in our life. We thought that how memories were actually not static like recollections, they are something in flux. And I think, as Carl Sagan also mentioned, we believe imagination can also push us to a new dimension. So last several years, we really focus on this data pigmentation idea. Very obsessed with fluid dynamics, more than, I guess, now 12 years. We learned that actually every information, every archive, and every, basically memories of this collective context, creating a different behavior. So we really focus on, now, last 8 years, different models of fluid dynamics, both in real time, pushing computer graphics, and try to create these new ways of data pigmentation. We work with brain data, EEG, fMRI, DTI, heart with skin conductance. We work with, high-frequency radar activities of the surfaces of the oceans. We work with urban culture, and as you may see here, the next one, which is the exciting one, even like New York, for example, 4 years ago, 113 million images of NYC in this data set.
This was a particularly great project for us. This was the first time we really worked with a really, really big data set. I think actually at the time this was the largest data set used for a piece of public art. So this was a great accomplishment at the time. To get to this stage is a lot of work, right? Of course, it starts with data collection. Then it goes into classification, image cleaning, and then finally GAN training. And so this tool you're seeing here is actually, oh, wait, can you go back a second?
Yeah, that tool was creating these outputs, by the way, sorry.
Yeah. So this tool, what you're seeing on the left here, is actually a clustering of all of the GAN images. And so this is the GAN images in latent space. And so the output on the right, as you traverse through the latent space on the left, you'll actually see the GAN image change.
And actually, the cleaning data process and getting really attention to curation brought us its beautiful outputs through different realities. But I think what gets really inspiring is how can we use machine learning algorithms not only just create the art or the context, but can we create a kind of a narrative, a scenario, by truly being true to this context of algorithms we are using, libraries we are using. So the project kind of created this very fun, imagination, what happens if an algorithm becomes a space. For example, with G16 here, we are very obsessed with these deep neural nets. What happens if you can fly in it and somehow but feel connected with the machine mind, and if we can understand this neural net architecture as a space, as a sculpture, then like can we step inside the GAN algorithm and somehow feel the fluid, interpolation between like latent spaces in 18-channel projection and 32-channel sound. And by the way, the sound is also like based on like back in time RNNs, like we work like with the like TV station sounds and radio recordings and many others. Like this feeling of like stepping into this new reality, kind of an artificial reality. But what was amazing in these exhibitions, we always show where the code comes, the contributions, and the algorithms, where they're connected. And I think these exhibitions created a safe and secure space. People felt connected and meditated, and we got incredibly positive reactions across the world and across like different culture. So we learned that opening the behind the scenes open source culture and defining the context truly make a difference and a positive impact. And I mean, not only just that, for example, we are recently working with like beautiful data sets such as in Rumi, Persian poets, 19 language of Masnavi. Maybe Christian can talk about this part too.
Yeah, so what you're seeing here is actually dimension reduction. So for this specifically is, we work with images and audio and text. And we go through, we do classification for depending on the different data set, and then we go through a process of PCA and then UMAP to actually create these 6-dimensional visualizations. So now here's another one from a project we worked on recently for Mozart. So a lot of this is audio data. We also have a set of images for this as well. This is a terrific pipeline. Of course, one of the really important things for us to do is this data exploration. And often we find ourselves working on unsupervised learning rather than supervised learning, because when you work with these public data sets or you work with things like Mozart or something else, it's so much more valuable to see what you can actually learn from the data rather than what you can try to force the data to conform to.
And many of these research also goes back to the researchers who have been putting this data together. We try to share like our findings and if there's anything unique for them, and try to make engagement with the academic context who is giving the data to us as well. But at the end, like we found these forms as like kind of a sculptures or data universes which represent the information in like 6 or 7 dimensions. But at the end, maybe we can see X, Y, Z, RGB, but in the final context, I feel like there are like kind of universes that we can fly in and like understand the meaning of information and knowledge. And of course, the imagination like goes a little bit more exciting when we start thinking beyond that. For example, these are last 3 years of research, a pandemic research, that we were super inspired by nature. Like I think and then the inspiration in nature and the idea of like metamorphosis became a very fun research. Like here we have this beautiful data set of 75 million flower archive, cross-checked by the Smithsonian 16,000 species. We made this like another like a generative model. But what was funny is like what happens if we just not only create, by the way, the sound is also like generative AI as well, but what happens if we can also feel the scent of this AI? So thanks to friends at Firmenich, last 3 years, we are working with their amazing AI called Charlie, trained on 500,000 molecules. Unfortunately, this AI is left over because there's a very expensive molecule creator that none of the brands can use it. But we thought, what happens if we take this idea and run their 14 unique molecules through this like mini machine, and when you enter this space where the machine can dream these flowers, and the sound and the scent of AI. So right now it's inside London, open and free for everyone, and if you're interested and happy to share. And we found that it's also very similar that where the metaverse becomes inspiring, that physical and virtual world collides, and the AI demystifies the reality around us. And we get a beautiful reaction as well, and then so far from any age, any background, people are truly enjoying this experience. And this model, not only just in an immersive room, just recently, we are exploring this same idea thanks to, again, PyTorch, the speed and the process that goes beyond this is very intense. We are right now running the same idea on a real time on a stage in performances. And also this, by the way, performance has a scent as well. And we are right now seeing real time how, again, thanks to PyTorch implementation on a DJX station and running pretty much real time while they are performing. And we also took this idea, like what happens if we take the same idea maybe on a building. Here we are watching in Berlin in real time, again, running the browser, this time using the weather conditions, such as the Berlin local nature data with the Berlin local weather data, and we are giving a life to a building through the same model as well. And the other, maybe the last project that we would like to share today, which is right now in New York at MoMA. I think it's the very first time generative AI is publicly available and in the collection of a museum. They would like to share this project as well.
This is a particularly exciting one as well. For this project in particular, we're actually using real-time GAN inference using audio data and motion tracking data from the lobby itself and also weather data outside. For myself, I think we really started doing this in 2016, and over the course of time, obviously I've seen PyTorch grow a lot and implemented PyTorch everywhere. We've done some great work in that time period as well, and I'm super excited to see what's coming next for both PyTorch and us.
And our curators, Paolo Antonelli, Michel Coe at MoMA, trusted the process and gave us the entire MoMA archive. By the way, MoMA is a very visionary institution. They open sourced their data in 2016 on GitHub. So it was a very visionary institution. And what we did is took the Agnes Gand open lobby. On the left side, you are seeing a 25 feet by 25 feet media wall, which is an 8K by 8K resolution. And we have to upsample our, first of all, neural net to be able to create a real-time application. Also, in this image, if you look at the ceiling, we have a real-time camera and a microphone and a real-time weather API from the literally 3 buildings right side. Sorry, we are getting a real-time information and literally real-time like inference, this kind of artwork. These are like 3 different UIs that is running on a real-time engine. When you go to the artwork, you can real-time see what exactly that given time that we have these clusters on the upper left you can see, and then kind of like machine serendipity or kind of machine imagination can plot new ways of like creating new artworks. But the fun was like they were truly looking for not realistically finding the same pattern, but the curators were pushing us for the fantasy, like dreams and hallucinations, which was much fun than just trying to mimic the reality and try to create another Monet or like a Starry Night, but more about what else can we do with that and how the machine, maybe creativity become a part of these new latent walks. And we also took this challenge and look at with the curators to give meanings to this like unknown universe. And even though we love Stable Diffuse, Midjourney, DALL-E, and we were very closely working with all these friends, we found this interpolation language and this true control much more has a fidelity and much more connection with the poetry inside the data. And eventually, you may be seeing this a lot, but in our work, we are really like taking the raw outputs from the neural net, but always try to give this kind of data pigmentation where 100+ million molecules shape-shifting through like certain fluid dynamics behaviors, and we found much more fun and again like diversity through this research. And if you go to the lobby, you will be able to see 3 different artworks, 2 of them completely generative, and 1 is a pre-computed. And this is Christian, by the way. And one fun data from the security team at MoMA, we believe their data more than ever because they're there for 10+ years. They said it's the first time they are seeing bigger reaction than their famous work, Van Gogh's Stair Died. And it's the first time they are seeing all the ages engaging with artwork publicly. And it's a very exciting for the MoMA, for the institution, and trying to make this accessible for humanity. I think as a finale, we can easily say that AI and creativity opening a beautiful like senses, and it's pretty clear that in every engagement and every different public art creates a big impact. And today we would like to show about and share and also call for action, I guess, from a community like yourself. We are opening our own metaverse museum or virtual reality museum in Los Angeles next year. And we are a small group of people, but we believe that bringing attention of the open source community to our research may bring much more impact than creating another a cheesy model of business. We just didn't want to do that, but we would like to create something purposeful and meaningful as a mean of art experience. We have 2 big dreams that we'd like to show today. One of them is mental health. We believe that right now we need some different ways of thinking about the mental health context. We are heavily researching about how to quantify the impact of AI art in the human mind, and can we bring this to the across the world and as free as possible? And we are looking for support of this specific research. And secondly, I think this is really the most, I guess, spiritually connected project. I was very fortunate to live in the rainforest in Amazon in Brazil with a beautiful and very challenging, takes 14 hours to go through this snake Amazon River, and live in this Acre area with an amazing divine humans called Yavanava people. They were 1,200 people. And this is Nishiwaka, and it is Putani and his wife, and these are the leaders of this small tribe. And what we are hoping is, instead of creating another just data set randomly, we want to co-create and work with these incredible people who have been willing to work together. You have to live 1 week with them before starting to work, but it's a very interesting world. There's no contract that we know, there's just really not a different spiritual connection. But our hope is co-create. And the number one problem we found that the language preservation. Unfortunately, there's only 57 people left that can speak this language. We are looking for support, how to preserve a language for indigenous people, and how we can open source for other indigenous people. And the second is how we can co-create something meaningful and purposeful Because the world has enough problem, and we would like to bring hope, inspiration, and joy with AI and art. Thank you very much.
Thank you all for joining us today, whether here in New Orleans or virtually around the globe. I know I can't wait to get my hands on PyTorch 2.0 to try it out. Also, I'll never look at space and art quite in the same way now. I want to thank especially the speakers and the PyTorch community, whether you're a researcher, contributor, ML engineer, or even a hobbyist. Please continue to use PyTorch. If you want to learn more about PyTorch 2.0, you can check our website. There's a specific page that we have for it with tutorials on how to get you started today, so you can get your hands on it. And so we'll also host a series of AMAs with our engineers to go more in depth in every one of the topics that we covered in the next month or so. You can see it on the website. So our program is at a close, and we hope you'll join us today for the happy hour that's powered by our friends at Google Cloud. Thank you again all for coming, and see you soon.
Nice job.